today we're gonna go, we're gonna have a long session for LeetCode, and I hope you'll enjoy, and I hope we'll learn and practice a lot of different LeetCode problems. Today my goal is um, review the question that I have solved before, especially in DP, like a dynamic programming, and maybe we can we can try solving some new questions as well. But I wanna review like a backtracking, dynamic programming, and solve new questions in graphs, and I also wanna practice like a binary search and then sliding window. Like these topics, like quite these techniques are quite nice. 2 pointers, and especially greedy, guys. Like greedy is my special topic. I really enjoy solving it. All right. Like we already have created um bunch of subtypes for greedy. We will try solving like a um two or three different um questions in each subtypes, all right, so that we cover almost all subtypes, because greedy is not single topic. It has its subtypes, and luckily we know those subtypes. Let me check my stream, and if its subtypes, and luckily all right, stream seems nice and fine. Um, and also let me update the title, I think, right? Um, Error question. bunch of bunch of question. Or don't type anything. Let's see. Which is nice. Let's start with knapsack problem, alright? Um, stream seems just fine. Let me open my creator dashboard, I think. And stream manager, yes. Alright. Let me organize. Alright, I have my chat over here. Alright, I guess we can continue, right? Everything seems fine. So, like, we can start with, knapsack, because I've been dreaming of this, alright? Solving this question live. And then maybe we can continue with, greedy problems, especially like I have solved, I've practiced like this running state before, which resembles to pre-order terrorism. I've solved a few questions here, what we can review and restudy, all right? Um, but I wanna start something fresh, something new. Um, Maybe we can start with this. But I also have, solved some questions um in this subtopic, which is orange, which is from Mark 21. Yes, we have even the animation, guys. Look at it, guys. Like we are we like I feel like I'm a director or something, by like for creating these like this kind of animations, all right? Let me also start um a background music. Uh Let me hear it a little bit. All right. We have our music, we have our animation, we have our chat over there. and time to solve knapsack. For knapsack, we can we can take our notes in capture area. All right. I use this capture area for, you know, storing like a random thing, but by adding tags, we can, like, I can reach the nodes I need when I want, basically. So, stream seems alright. Yeah. Um, yeah, we can start with, I think, knapsack, and also maybe we can start our Pomodoro resume. And it would be great if we have some sort of timer, right, guys? All right, let's start with knapsack. Um, for knapsack question, guys, since in our last streams we have we have solved backtracking, we have used backtracking approach, so that's why today I'm gonna draw a decision tree and wish and hope it will help. So knapsack problem is, guys, we have items, all right, and they have some values and weights, I suppose. All right. And let's say item one is, value 10 and weight 5. Item two, this is value, this is weight. Value 2 and weight 10, or let's say 5, 5, and let's say, I don't know. Like we can pick an example from web actually. Let me open one because numbers sometimes matter. Uh, knapsack, LeetCode, and the special part is this is 10 type knapsack 10, and we need to maximize. Like we need to choose which option, which combination of those, selection is better for us because we have knapsack and our knapsack has its capacity. All right. Oh my gosh, maybe I should just give me map sec 0 1 question with example input output. We need to create an algorithm to select, to pick an items that will give us the maximum value. You may say, why don't we just, um pick the items with maximum value? But in that case, maybe the maximum value, the item with maximum value is also, maybe beyond our capacity, or its weight is so high so that maybe we can pick other two items that their summation is higher than the biggest one. So that's why we cannot apply algorithm approach here. um yeah, let's see, let's have this for an example. I plan to dedicate like a 45 minutes at most for each problem, and then we continue with the next one. So, like, basically, guys, since we use backtracking approach, in backtracking approach we had our options that we need to explore, right? Here the options are these guys, right? For example, at level 1 we can pick like a um like a item with value 1, item with value 4 and 5, and so. And the thing, guys, the thing is, another thing, like, should we write the values or weights? Like, yesterday I used weights because this is our constraint, and we define our subproblems with weights. All right, let's say let's say we like, let's say we call our recursive function with, you know, um like a 10. All right, if our capacity is, starts from 10, we call this, and when we make a choice, our subproblem becomes like this. All right, so that the way you define your subproblem or problem is quite important here. And the thing we need to maximize is this. um but problem definition is made, or is structured, is built on top of weight, using weights. All right, like, this is uh, another thing, another important thing, because I used values and I realized, no, like, this is not the way. So we can pick the item with weight 1, or weight 3, or weight 4, or weight 5. So in the next level, guys, as you get it right, since it is 0, 1 knapsack, meaning that after you pick an item, you can't pick it again. So basically, it's gone. All right. So after picking one, our options become, as you get it right, like a without one, like a 3, 4, and 5. All right. And if we pick item, if we pick item with weight 3, and now um, our options are 1, 4, 5, and so on. All right. So in each level, like, as we go one level further, we need to shrink our options, basically. So we need a structure for it. All right. How can we do that? The one approach I know is like a kind of masking. All right. Let's say we have our for loop. All right. And these are our choices, and in our recursive function definition, we can hold an array. All right, and in that array we can add our choices. All right, and as we iterate um, all our options in a level, we can say if the mm, maybe instead of, or we can use an array too. Let's say if that character exist in temporary area, meaning in our previous choices, we can just continue. This is one way. Like, I've seen this method in permutations or combinations, some, I don't know, that kind of backtracking problem. This is one way. So that in each level, we basically, for example, in this level and in this subtree, we skip basically one using this method. Another method is like yesterday I studied like using for loop, and we basically assign um I think start, but I'm not totally sure about it. Anyway, so this is a decision tree approach. All right, but um like yesterday we discussed it with AI, and um it said that there are some reoccurring sub problems, um and we can optimize it. I don't remember it fully. Let's ask it. All right. This is one approach, and after this, I'm gonna show you the other one. Activate um, tutor mode 2, and now we are studying knapsack 01 question. And the thing I wonder is, like, I applied like a drawing decision tree, and in each level, our options are the items, and we define our subproblem using the capacity. And as we explore a choice, we the only thing we need to do is subtracting uh, the current choice's capacity from our total capacity. And also in our for loop, um, we need some sort of masking, um, indicating the previous steps choice, so that if, like, as we iterate, if we hit the current previous choice, we just continue and we skip that option with choice. This is one approach. And yesterday, I have discussed this with AI with you, and you said it has some flaws or some inefficiency in terms of time complexity, or maybe space complexity, because it has another solution approach as well, which is, instead of discovering all options, we just, um, in each decision, um, we just, I think, exclude or include. So in each level, we pick a choice, a number, all right, and we explore the verb, explore the subtrees, subproblems where we included that number or excluded. So decision we make is just exclude or include for each item, basically. This is another approach. So what I need to know is, like, on web, most of people applied the second approach. Why? So the important thing here is that, like yesterday, AI said that, does the order of selection matter or not? All right. Here, guys, in our knapsack problem, like, the order does not matter, right? Like, because in permutations problem, the order was important, right? Because it matters. But here, since we can pick randomly too, mm, we don't need to do this way. But still, I wonder, like, I want to compare in terms of time complexities. Because the reason why we can apply this logic, like exclude or include, is that order does not matter. So that we like, to make this structure, we need a for loop again, and in that for loop, we just, start from left to right. This is why we can use this. This is what I have studied yesterday, but let's see how this AI will respond to that. And also, I want to see the time complexities. So basically, let's continue with this approach uh, to create the recursive relationship, and then we can create the code for my first approach. So for these guys, for each item, we can exclude and include. These are two condition, two phrases that we need to create a formula, basically. To include, if we include an item, all right, we get its value, and the remaining subproblem that we need to delegate or we need to expect answer from is, since we define our subproblems with constraint, let's say our capacity is kappa, or capacity, let's say total capacity, or total total cap. All right, from total cap, we should subtract the uh, capacity of I. This is the phrase, or this is the definition of selection or including. all right? And this is one. The other one is we don't include that element. So yesterday I thought that like if we don't include something, we don't get its value. This all right. I understand that, but how should I represent not including? So basically, we need to skip it. But since I've thought you like from this perspective, um, it didn't click. All right, but here, since we go left from right, basically increasing an index would mean an index, and if you don't get the value, will mean you basically exclude it, all right? So for exclude step, we need to basically um so move forward. So this means that um we need an index. So let me type it here too, and meaning we moved forward, and this is our remaining capacity, and this phrase is our definition of subproblem definition. And here we move forward, but we don't get the value, all right? So that our remaining capacity stays, you guessed right, same. So this is one thing, like one phrase, one condition, and this is the second condition. So now the thing we need to maximize is, guys, you guessed it right. We need to find the maximum of A and B. All right. All right. Like to find a way to represent subproblem is a skill basically. And also yesterday I have struggled with how am I supposed to show that I included. I thought like we need to get the value. We need to earn, get the value. All right. This is how we get, and this is how we define our subproblem. And in most of the DP problems, guys, like this is a trick. All right. Trick number one. Um, especially one dimensional the dynamic programming questions, guys. The problem definition you need to create or come up is like it should be using index. All right, so index is like a fundamental thing that you're gonna see all the time. All right, and for two-dimensional dynamic programming problems, things got a little bit messier, but um, again, index will be one of the parameters. And for dynamic programming questions, guys, another trick is that you need to keep um, like number of arguments, uh, low arguments, low. All right, we don't need to have lots of arguments. Welcome, Americano wins. Welcome. How are you, man? See ya. Buongiorno. Today we studied, we started with, knapsack 01 question, which is a one-dimensional dynamic programming question. And we plan dedicating, let's say, around 45 minutes for each problem. And let's see how far we will go. And also, I'm doing good. How about you? I'm doing good too. I'm quite, excited for today, and excited for the result that we can get by the end of this stream. We're gonna cover a lot of different questions from a lot of different topics. Let's see. Um, Today we learn not Python. We practice LeetCode. Mm, Like, oh, alright. Practice. Pra, practica. Practica. Let me write it down. The title is not good either. So let me handle one thing before we continue, guys. Um, let's see. Like also really sorry if I'm a bit absent right now. I'm taking care of my sibling. Alright, alright. No worries. No worries, Americano. You have some responsibility. Do it. And I need to find um let me yes ah, okay, yes right, what was it? Um keep the number of arguments low. Yes, exactly. Oh, let me update the title very quick. Done. Wonderful. Let's check the title here as well. I think it is okay. Mm. All right. Anyway, by the way, what were those three German humors again? like, like, um, I will watch it again. I will watch the last stream again. Like, sadly, I didn't take notes, but I remember they were too long, and for German ones, they were about some, hospital and some health. And for Italian, the last word group we have studied was sounding good. So these two I remember. Motor permit, yeah, some you know, legit stuff. Yeah. Like a paper stuff, when you get a car, you need to, create some papers to get, some permission. Like real C2 level words. Thank you for that. Um, Today we also have some new chat comments, guys, which is, help. Um, what was it again? Help poll. Today you are able to answer my questions, and by the end of our stream, we will announce Hand of the King. All right. Um. So you can, like, while solving like a LeetCode problem, I may have some questions instead of asking AI or Google. I will ask to you, and as you answer, you'll get some points. All right? No, no, no. I can start the poll. So this is the definition of selection, like including or excluding. And also we can ask, what is this called? All right, because this like condition or you know mm, like a recursive relation. Because in house rubber problem, like we have a problem called house rubber where um like you can rob a house, but you cannot rob the adjacent house basically. So in that problem, guys, we were saying that like there are two states, or I don't know, there are two states. All right, one, you can you know rob the first house, and in the next, like the another condition is that basically you don't rob this house. All right, meaning you can start robbing from this house. So this is condition one, and this is condition two. And here, like the definition of this state is, you know, um, get the value from this. All right, let's call it I. Get get the value. All right, house I. Let me say, and delegate your subproblem. Delegate your problems to subproblem. And the definition of subproblem is, since you cannot solve this, but this one. So I minus 2, we were saying that our subproblem is, so this is our first state. All right, we get the value, and this is our subproblem. And in the second condition, since we don't wrap this house, we can start wrapping from here. And the definition of this is basically, imagine our problem was given us like this, starting from that. All right, so that the second condition is basically these guys. All right, so um the question we are asked was, find this one. All right, so the recurrent relation becomes, the answer to this one is basically maximum of 1 and 2. Let's not call it 1, but state 1 comma state 2. All right, um so the thing is, like, the thing we defined here is something, right? Because like, defining these two is distinguishable from writing these relations. And also the third important step is combining this. But most of the time it is maximum minimum. But the real recursive relationship is this. Our problem is defined like this one, right? which is which is awesome. So the thing I'm trying to say is that, like, these two is important too, you know. And you can ask AI, well, what are those? I mean, as as a terminology. Um, let's not read that part, but ask this. So thank you for explaining. And the thing we wonder now is that, for example, in house rubber problem, um, we have two states. First state is like we rub the last house, and the sub problem we wait answer from is I minus 2. And the second state is like we don't wrap the house, so that our sub problem becomes I minus 1. So the thing I wonder is, like, what are those called in terminologically? All right, the state 1 and state 2, because like a understanding or like a guessing or knowing these states is quite important. All right, because in our recursive relationship we basically combine these two. Like, are those like states or if statements, what are those called? Um, because in knapsack problem too, we have the same thing here too. Like we have two states basically. One is like, especially in our problem, first important thing is like deciding which kind of decision tree we're gonna have. Since in this problem the order does not matter, we can just apply exclude and include for each item, because these are the two options, like two possible options, two possible ways that we can explore. And after deciding our decision tree, now the another thing is defining our states. Basically, by state I mean we can, definition of getting the value, you know using the recursive call, and then not including, basically excluding. So these are our mm, definition or states, as I call it. But I think this is an important step to um, to be able to solve this type of questions. Can you please clarify a bit? Um, so while it is thinking about it, we can read um, what it has written, and then we can continue our next question. So great question, and your instinct that approach one needs masking as accurate threat to pull on. Yes, let me guide you. So we basically asked that, um, like if we design our decision tree like this, meaning that in each level we basically explore every choice, and as we go one level deeper, we just exclude one of the, you know option choice based on the previous choice. Find the duplicate in your own drawing. Look at your tree. Um, Look at your tree. Weights, yes. Path A. Pick item one level, yes. Pick item three at level two. Hmm. Pick item. So it says in path B. Pick item. Yes. So this is what I was trying to remember, but now I think I understand. So the point it is trying to get is that, guys, imagine you pick one and then three, right? So basically you picked one and three, right? And in another path you picked three and one. So the order is different, all right? And but the total value we get, and our subproblem definition, or subproblem, yes, subproblem definition is stays same basically, all right? Like there is no distinguish, there is no difference between these two differences, like different case states, in terms of, our remaining capacity and our total value that we get. We basically get value of 1 and 3, and so the value is same, all right? Value 1 plus value 3, and the remaining capacity is same. uh, Total cap plus, minus cap 1 minus cap 3. You may say that maybe it is not possible, meaning that, like, maybe after making one you can't just, pick 3, or vice versa. Yeah, so now my question would be this, like, what if, but the point it tries to get, um is this: the order doesn't matter, so we don't need this basically. All right, now I totally get it. This would work, like this decision tree would work, but it makes some additional or extra and unnecessary calls, all right? Like making call 1 and call 3 and call 3 and call 1. So basically, if you want one of the path, you don't need to do other one. But can we use like a memory, some sort of memory, to prove it? Um, like memorization or something. Let's see. Question for you. In the knapsack, yes, yes, now I get it. It isn't the same item, same total weight, same total value. Your three visits the set twice, basically. Once for each order you could have picked them. Your maxing only stops repicking the same item. It does not stop you from revisiting the same set in a different order. So that's the core problem. The knapsack problem cares about which items are in the bag. Alright? Oh, Hanger Hippo Redeem. Learn a word in Japanese. It's too early, bro. Too early. It's verb. Atata. Atata. Katata. I think. Hi, welcome. Welcome in, man. How are you? How are you doing? Today we have started our stream with knapsack 01 question, which is a dynamic programming question. Let's see. And let's type it down. Not a hard word, honestly. Yes, kind of. Yeah, yeah. Um, Let me Google Translate. It was warm. Let's hear it.
暖かかった。暖かかった。
Atata katata. Yeah, yeah. There are two parts. Like a big. There are two parts pronouncing atata katata.
暖かかった。
Atata katat kakat kakatta. Atata katta.
暖かかった。
Atata kakata. Yes. Two TAs, two KAs, and then alright. Atata kakatta. Atata kakatta. So thank you for the word. Today's first word. Hunger hippo. Let's continue, my man. This is the reason the state for memorization. So this is the part you can't easily see from the picture, and it's the real line. The whole point of decision tree is to eventually memorize, convert to DP. To do that, you have to ask what defines a subproblem, guys. So this is what I have mentioned earlier. A subproblem is defined, I mean, in this approach, like in this approach, our problem basically defined using index, all right, like a index and the remaining capacity or total capacity, let me say, all right, because when we first call this, it is capacity, but when we call this for like using our children, basically our subproblems, it means like a remaining capacity. But we may say at first call, starting from the first call, we may say it is the remaining capacity, basically. um yeah. Approach to include, exclude. At each step you decide one fixed item. So yes, so in the second approach the order is fixed since the order does not matter. Then move to I plus 1. The subproblem is fully described by, yes, I and remaining capacity, just two numbers. So the downside of DP is if the number of parameters is high, then DP basically cannot solve it, alright? So this is bottom up. Pick any remaining. What's the subproblem at the node? It says how you define your subproblem using the approach one. Which items are still available? Remaining capacity. Yes. But which items are still available depends on the path you took. Yes. It's an arbitrary subset, not a single index. To cache that, you would need a key of to the n possible item sets. The state explodes. It can't collapse into a table. I see. So basically, um, the first approach isn't, you know, doesn't allow us to turn it into DP. And the reason is this exactly. Which items are still available depends on the path you took. It's an arbitrary subset, not a single index. To cache that, you would need a key of to the n possible item set. So all right, this is cool. This is cool. Let me save it over here, and in the end of our stream, at the end of our stream, I will collect these. So all right, this is clear. So the next question we asked is um, basically what is these states? Are those called like a states, definition, condition? Like because they are something like a apart from the recursive relation, but not too far. Good. This is exactly the vocabulary that once it clicks makes every DP problem feel the same. You are mixing up two different things and separating them is the whole game. Alright. The one distinction that fixes everything. Node versus edge. Think of your decision tree. Nodes, basically they are states, a subproblem, where am I, described by parameters. These become your cache key. Edges, choices. Choices, decisions, transitions, branches. What can I do from here? Yes, yes, like I really like. So this is what we do basically, guys. Answering these questions. So the two things we are calling state 1 and state 2 in house Robert are not two states. They are like hmm like of course I know this, but the thing I wanted to ask is that here in a algebra problem, like we have we have these two possible states, all right. Maybe the AI didn't understand me correctly, all right. Or we shouldn't draw this like this. Like let's read it. Let's read it. The state is a single thing. I. The choices are rope, and skip. You were labeling the edges as states. The three-part vocabulary. Like we know this, guys. We know this, but read the recurrence out loud with one vocabulary. The answer at state I, the maximum over my two choices, skip, rope. So basically it says these two are not different terminology. All right. Basically, um, I still don't entirely get dynamic programming. It's just breaking a problem into multiple steps and caching the results. So it is about actually hungry repo, defining your recurrence relationship between subproblems. This is it. This is a recursive. I mean, you need to find the recursion relationship. For example, there is a climbing stairs problem where the relationship is, to find this one, like find this one, you need to basically find this subproblem and this subproblem and basically sum these up. So like imagine having a problem that you can define it using subproblem. So you so basically like when someone asks you like what is your name, you say, I don't know, like how would you answer it? Hmm. Like I couldn't get a real world example, but basically you define your problem using subproblem. Like the function is not something like um you know something like this, but instead of this. So we basically try to find a way to define our problem using the sub problems. This sub problem is basically our real problem too. So, so this is what we are trying to do right now. For example, in house problem, um, this is our first option and this is our second option. And as you can see, we have this one and this one. So our our problem definition is like maximum of house I plus func I minus 2, comma func I minus 1. I can explain like this, all right? Um, so basically, like you don't need to find the real formula or definition, but instead, how can I use my sub problem and find the real problem I have, basically. All right. Um, so the two arguments inside it are the choices. Mhm. You set first decide decision tree, then define the state. Your instinct is right. Here's a proper recipe. Identify choices. Yes. Define the state. Mm-hmm. Let's see this. We can continue. We can continue, guys. Um, let's continue with one of the orange questions we have, which is greedy. Actually, I have solved this, but let's see. Um, actually, I want to study more DP problem, but anyway, we pick greedy and then we go back. We go continue with DP. All right, was our first problem. So now a greedy problem, guys. Two city scheduling. A company is planning to interview two N people. Are you doing all LeetCode in Python? Like I'm using Java actually. I'm more familiar with it. But for recursive problems, we can use Python too. A company is planning to interview 2M people, given an array costs mm, costs I. So cost I is an array. Oh, I saw Python when I joined, so I thought it was yeah. Like I updated the title. Yeah, you're right. You're right. I forgot to update the title. Now I changed it. Let me check it again. Actually, we can try using like a Python 2 if you like. The cost of flying eighth person to city A. So basically, I like Java. All right, all right. That's even better. So basically, we have an array, guys. Let's say cost, but which values the I can get? Mm, let's say cost I has an array, and the first one and like length of 20. So this is for A, this is for B, mm, and this is the people. I think let's assume we have 10 people, and let's say this is person 2. All right, for person 2, the cost of like a flying person 2 to city A is 10. All right, and cost of flying him to city B is 20. So we have these values for all people we know, and what we need to find is, um, of course, with the minimum cost. All right, we need to move like half of the people to city A, half of the people to city B. But you may ask why half. Let's see the constraint for that. The cost of flying I person to city A is this one, and yeah. Return the minimum cost to fly every person to a city such that n people arrive. Alright, so basically half of people, will be in city A, and the remaining half, the other half, will be on city B. But here in here we have 4 people. Alright, let's see. So since I have solved this question before, guys, I know what to do. And like in this type of graded problems, guys, the trick I have found is like a thinking like a in smallest, largest. Like forget about the middle element, all right? We need to like a go either go all the way left or either go all the right. So in this case, like the way we can use to apply this smallest largest trick is that what would happen, like imagine what would happen if we move every person to city A, all right? We would get cost 0, like a cost 1, right? 2, let's say we have 5 people or 4 people. We would have these costs, right? Or even let me type it down since only one person here in the middle. So imagine we moved like a every person to city A, so there is no one in city B. So here the total cost is the summation of these costs, right? um Now, like, now the thing we need to find is one which one of them we should move to city B, all right? Since we want our total cost to be low, we need to find the people that with smallest cost for city B, or it is same for city A too. So if we carefully select the correct people to move city B, then what we'll end up with is the correct, like optimized or the best thing, all right? But now the remaining question or remaining decision is, which one? Let's say, do we like should we use this person 1, 2, or 3, or 4 to move the city B? The formula, like, and also in graded problems, guys, like there are some like formulations, like let's say summation or subtraction, like stuff like that, all right? Some weird, like this is another trick. So here we need a formula to which one to move to city B. So let's think about it. So cost, actually, the structure we have is an array. So costs, it is not cost, it is costs, and this give you an array, all right, which is let's say 10, 20. So this is cost for A, this is cost for B. Let me 30, 200, 450, 30, and 20. So actually I know the trick, but now I'm trying to remember. Basically, we should make, this maybe smallest ones in the city A, and move, for example, let's keep, you know let's keep, this is not the correct way, by the way, actually, but let's keep A here, and maybe this 30 here, and move, you know the highest cost to there. But this is not correct. This would not be correct, um because why? Let's say this is 20, and this is 500. All right, if we move, no, no, but let's say this is 40. All right, and this is 500. Since in city A its cost is highest, we move, let's say we move it to city B, but there its cost is even more terrible. All right, so that's why it's better we keep this person in city A. All right, even though the cost of keeping him or her is highest. So this is why we cannot, you know um, make the smallest one in city A, because the smallest ones may not be in the smallest one in the city B. Right, we need to care about as well. For example, like keeping this person in city A is 30, and keeping it in city B is 200. So like apparently, all right, clearly, not apparently, clearly, we should keep this person in city A. All right. So now the smart formula, guys, the smart formula. Let me think. Um, which ones should we move? Maybe I can I can start the poll, and let me try my uh, poll command. Help poll, and the question: what is the formula to decide which one of these people from city A we should move him to city B? I think, yeah. So, like, we need some sort of formula, like that we can make a decision on. Um, let's do some subscription. No, now I kind of remember, guys. We need to see the moving cost. All right, like if we keep person zero here, all right, or move, in terms of total cost, we would get, like, moving it, like moving this person to city B will make our total cost worse, right? By what? By 10. And so keeping this person is city A or city B. So if we move this to city B, our total cost would be, this bad, worse, this much worse. So this would literally help us, because the cost of keeping it here instead is too high. So we have to move it to city B. But the in terms of total cost, we would get like a plus 350, right? So moving it will give us minus 10, plus positive 10. So meaning that now in greedy, guys, the decision we can, like, the way we decide is basically, you know, as I said here, where here, like a smallest and large. So basically we sort, all right, like, but you may ask, what should we sort? Like, in some of the questions, you should first find the formula, which is in this case, we almost find we have almost find our formulation, all right? The formulation is, you know, putting every person into state A and um, calculating the difference compared to moving them into city B. And we're gonna sort these, and then we're gonna make our decision based off the order. Like if we sort these, let's say, uh, let's start with the smallest one, minus 170, minus 10, and 10, and plus. So basically, after sorting these, now our decision will be either picking the, you know, from the, you know, left part or right part, because the greedy approach means that, like I find this resemble to like in our organelles, right? In our cells, we have like a mitochondria, like some, you know, some organelles, some other organelles, and like these are cells, but there are some, you know, uh, other entities, right? Like a small, and they don't have like a complex brain or something, but they basically react to, you know, sun or light or the temperature, all right? So I find greedy to, you know, quite similar to these um, creatures basically. So its brain is basically just, you know, sorting and you know, either selecting the smallest one or the biggest. So nothing more than that. But you are the one who is responsible for giving it that kind of sorted array. So in our case, we should, like, we thought muted. All right. Um, what do you mean by muted? You can hear me, right? You can. Um, so, oh, sorry, that was no worries, no worries. Um, like, you are the one who is responsible for creating that sort of logic, all right? Because in most of the grid problems, you should, like, you basically process and analyze and make the problem and turn it into a basic, like this stuff, all right? Basically, here, the decision we make, guys, most probably we should, you know, move the highest one, all right? We, after sorting these differences, we basically um pick the highest n. This is the approach. And let's see the animation, guys, because we have it, luckily. It is cinematic. So we have city A here, all right, and city B over here, and we have our people here, all right? And cost of, you know, making this person at city A is 10 and at city B is 20, all right? So the decision we need to make is which one should go to city A, which one should go to city B. This is making my yeah, yeah, like, this is not an easy question. This is not an easy question. But like the thing I'm trying to capture is the idea of greedy basically. Idea of greedy is like the best side, the hard part with this type of questions is for each greedy problem, guys, like they have different kind of formulations, all right? So there is not a single formulation or idea that we can apply. But my goal is uh, solving questions from each subtype of greedy, so that at least when I see it, I can identify, I identify which sub problem it belongs to, so that I can pick my tools correctly. Because, for example, this problem, uh, basically, like it has its own unique approach, which is basically, moving everything in one side, and then selecting correct ones. But that selection is based, like, made upon a formulation, and finding this formulation is important. But also, like, each of these is hard, all right? Finding that formulation, and also, like, t- to know that you need to move everything, every person to one city. Like, this is an approach too, all right? Because we don't basically select one and move it somewhere, like select this one and yes, you should go there, and select another one and yes, you should go there. No, we don't do that. What we do is, like, collecting everything, all right, and put it somewhere, all right, society A, and then think, let's see the animation, let's see animation. So as you can see, we moved, guys. Let me even make it bigger. We basically moved every person to city A, all right? So, like, this is a approach. This is approach. So now we need to, like, we calculate the differences, all right? Differences, like, as if, what would happen if we moved there. So these are differences. So to greedy problem, for greedy problem to function, we need to sort them, and then mm, we either will, pick the smallest two or the highest two. Like after getting this step, uh, things will be easy, apparently. Uh, Apparently, LeetCode 45 jump game 2 is a good code. Yeah, yeah, we have this in our problem list too. Yes, like um, it is which sub problem type? Let me show you. It is um running state, kind of sub problem. I mean, greedy problem. We have this, like, it belongs to running state. So greedy reach and running state, like a cadence and jump game family, basically. So the question we are solving right now is, like, belonging to opportunity cost and competitor type. Like, you can take a screenshot of it, or maybe, I can prepare some notes for you too, on my YouTube channel and on my website. But these are the subtypes, and we need to know every subtype, guys, because every subtype has its own unique approach. Even, like, even in the same subtype, sometimes you are not able to, understand or solve, find the technique. um let's see, we're gonna handle this, so let's see the animation and then go to the next subtype question. So we move every element, every person to one, and we calculate the difference, and we sort those differences, and we basically get the, highest to person, and move it to city B. So basically, now we know which one should go to city A and which one should go to city B. So this is how we solve this question using grid approach, which is awesome. Grid is not a, quite smart technique. You basically sort and this, select the, smallest or highest, but the process until getting there is real and important, basically. So maybe we can go to the next subtype, which is fuchsia, I think. I think this one, container with most water. Actually, I have solved this problem before. uh Maybe we can select another one, trapping the rainwater. Let's see. Actually, I can mention about this one, container with most water. We basically, like, in 1 minute, like, understanding this question, like, takes a lot of time, but let me summarize it in 1 minute. So if you don't understand in 1 minute, this is just all right, right? So we have like this type of structure, all right, and basically you pour water in it, all right, and the thing it asks is um, like from where to where if you put water you'll get highest amount of water. And uh, the thing you may say, why not pull you know until here, right? mm, that's a valid question actually. Let's see the question definition. Of course there is a constraint about it, but let's see the question. So why not just so why not, because the endpoint will can maybe very low. Imagine this is the first, and then this one, and then this one. All right. So basically, you are trying to find the you know range or start and end indices where you pour water and you get highest amount of water. All right, because if you pick this one and this one, you wouldn't be able to go above this line, I think, right? But actually, like if we pour water here, like this one, right, we would have something like this one. So I think the position where we fill is kind of different, but let's read it. You are given an integer array, yes. There are vertical lines. Find the two lines that together with the x-axis from container such that the container contains the most water. Like actually, the way they put the question is like not clear, because it's also important that how you pour the water. If you're pouring the water from here, apparently, you would get something different, right? So uh, that's all right. But the thing it tries to get is that basically pick two one and imagine you fill somehow, right? Um, and actually it is about it is asking about the max amount of. So um so if I don't know, guys, if we start pouring water from here. Yeah, all right, I get it. So if you start pouring water from here, basically you would get this part, but in that case you would have selected this index and this index. All right, so the question asks from reverse order, let me say. But the idea is you basically select two indices like a start and end, and find the maximum amount of water you can fill in. Don't worry about how you fill it yet. All right. The idea with this, guys, now we need to make a selection, right? The selection of start and end, but we don't know how we can do it, right? So like, should we select the highest one and the smallest one, or like we don't know the solution, the logic. But with greedy, like we should create a formulation. And for this question, the first thing you need to do is the area calculation. All right. By area, I mean the amount of water you can trap, basically. So it is the difference between these two indices and the minimum of these two edges, these two lines, basically. All right. Because let's say we picked this left side and the right side. All right. The the maximum amount of water you can pour into here is limited by the minimum, because beyond it, if you pour more, the water will flush away. So the formulation is basically, let's say, and index minus start times the minimum of, let's say, line 1, line let's say line start, comma, line end. So this is the formula. So formulation. So this is the first thing you need to do. So for each, as I said before, like for each greedy problem, like there are different type of approaches, all right? Because in the previous question, we didn't have such formulation. Like we have formula, but this formula is for sorting. For the for the problem itself, we don't need a formulation, all right? We have people, and we basically move them somewhere, some city A or city B. But here we start with creating our formulation, because now we need to maximize, maximum of it, maximum of it, yes. So now the selection part is like which one we should pick, like which two lines we should pick. We don't know, but we can apply two pointers, all right? And let's say you start from leftmost and rightmost. Now the idea is calculate the amount of water you can trap. Start, let's say, leftmost and rightmost, all right? You start from here, leftmost and rightmost, and calculate this one, all right? Calculate the amount of water you can trap. Water, amount of water. And should you move the left pointer or right pointer inward, all right? This is the decision you need to make. And here we have another logic, like this is the hardest one among these all processes. Should you move left or actually it doesn't, like you don't know if the left or most, but the thing is you should move the smaller one. Like this is greedy, guys. Like you don't make decision based on like should I move left or move right pointer inward. No, the idea is you should move the smaller. Like if leftmost is smaller, then you should move it, or rightmost is smaller, then you should move it inward too. Why why the explanation for this is that as like lies in the formulation we have. Like formulation we have is subtracting, like taking the distance, all right? Taking the distance and then minimum of the left or right, and multiply this, right? So as we move inward, we basically like our distance will be, you guess is right, smaller, all right? Like it doesn't matter if you move left pointer or right pointer, right most pointer, but the distance, like x distance, will be smaller, right? And our goal is find a better choice. And to find better, we basically, the only case we have is like if we move smaller, all right? And if the next one is higher, so that we may have a chance to find a bigger one, right? I mean larger amount of water. So you may ask, like, what would happen if we move the larger, I mean taller one inward? Let's see what happens, because in the real interview you will have to try everything, and you need to basically create an idea. So what would happen if we move the higher one? Let's see here in this case, like this is this, and let me also make it more clear. All right, let's see, this is small, all right, this, I mean short, and this is high. Just got back. What is the goal of this problem? The goal of this problem is trapping a lot of border between lines, and this is a greedy problem, and we need to make a decision. Like there are lots of combinations here, right? Like we can pick this one and pick this one and calculate, or let me even take a screenshot and create a summary about this problem. So this is a greedy problem and we need to make a decision, all right? Like the question asks, what is the maximum amount of water you can trap? So basically if we select this one and this one, guys, all right, the amount of water we can trap is this, right? And if we select these two, the amount of water we can trap is this, right? Or let's say these two, like we can pick this one. So the question asks that, like, which pair of these line we should pick so that we get the highest amount of water we can trap. So the approach we are applying is two pointer, all right, and we basically start from, like, we have our left pointer and right pointer, and we move them inward based on a logic, all right. Now I'm explaining that logic. So um so what would happen if we decide to move the taller one inward? So, like, in that case, let's say we move, let me use another color. Let's say we move, oh, capito capito. So let's say we move this, like, a taller one, all right? This is taller and this is smaller. Like there are two cases, right? When we move taller one inward, we either encounter with even smaller than taller, or not even, maybe we can find a, a taller one, even are taller. So these are two cases. Let's analyze these two cases. When we find smaller one, all right, and our small, like, left pointer stays same, right, at this position, and we find a smaller one. So let's look at this guy. Like, the amount of water we can trap is has become, radically, um, you know, like, look at it, guys. It is too, you know, small. I mean, look at it. It is nothing. So it is obviously not a good choice. All right. I mean, but we don't know it. Basically, we basically analyze every possible option or every possible condition, and then we generalize it, and then we say that this is the, graded approach, and this is the proof. So this is first case. Like, first case is, like, we move, our rightmost, like, a taller one, and we find a smaller. Let's see what would happen if we find a higher one. Like, we move taller one inward, and we encounter a bigger one than it. So in that case, the thing is, guys, since the limiting factor is this, like, a between these pairs, since the limiting factor is, um, you know, the smaller, so this didn't change again. So, like, moving to taller line doesn't give us any better result. Gazie Duje. So, like, moving the taller one doesn't give any better result. All right. And so we basically, proved that moving taller isn't the option for us. And also, but let's say, do we have any better result moving this, leftmost or smaller, not leftmost, but smaller line inward? Like, do we have any chance to find a better result? Since our goal is to find the maximum amount of water we can, collect. So imagine we move a smaller one inward, and again we have two cases, right? We can encounter a higher one, or even smaller than that. All right. Let's start with smaller then. So our first trapping water, like amount of trapping water, is this, right? This amount of. And what would happen if we encounter even smaller than that? So our amount of water will be quite terrible, right? So this is one case. This is one case. But the last case, guys, last case, which is we move smaller pointer inward, like a smaller line inward, and we find, guys, let's look at it. Let's look at it, guys. We find, let's say we find the Godzilla. Let me draw let me draw um let me draw Godzilla, right? Like, I mean, like, oh my gosh, like huge, I don't know, like oh my gosh, like this one, right? Like, I don't know. Imagine this as Godzilla, right? So we moved like a smaller line inward, and we are so lucky that our next line is so high, so that, let's look at it, guys. The amount of water we can trap into here, although the distance between like these two lines, effort is much appreciated. Thank you. So although the distance between two, like, our new lines is smaller, basically the new distance is smaller than our previous, since we moved one step inward, right? But the high difference is too high, to that much, that we have a chance to find a better, better combination. So basically, in this greedy problem, first thing we have done is, deciding to, like, this is the formulation we want to maximize, and then we basically, like, decided magically, I don't know why, but magically we said that, yeah, we can use a two-pointer approach, like, starting from left and right. But in that case, which pointer we're gonna move inward? All right. Actually, it is not which pointer, but which is the, smaller. So we basically tried, moving the taller one inward, and what we end up is, like, we are not getting any better result. So we stopped, we killed basically the idea of moving the taller pointer, and we tried moving the smaller pointer, and we saw that there is one case, that the Godzilla case, guys. We can call it Godzilla case, that if we move, like, let's say we move the smaller one inward, and the next line is so high, and we get, a better result. So basically, in the code solution, um basically this is what we are gonna do. Like, this is the core idea. And yes, so during the interview, guys, we need to explain like this, right? Explain every case and every reasoning. But what if there are two lines that are very high, but say 7 indexes short, and then there is a smaller one that lasts up to 12 indexes, and the smaller but longer. Man, for your question, we have Stream Arena, and we have our chat. So you should draw what you mean and share with us. And let me um, share the room code, because I understand nothing. I'm sorry. um, Let me copy. Like, the thing you are trying to tell, I guess. Like, I get it. Like, you are still thinking, like, is there a case that we may miss? Mobile support? Actually, no, no. I haven't updated. Sorry. Like, I have created some new chat comments, but I haven't updated. This website for mobile. Um, no problem, no problem. Thank you, thank you, thank you for your understanding. Yesterday I was outside and I haven't opened my laptop. So Americano, the thing you are telling us is about thinking an edge case or something. But with this approach, we basically cover all of them. All right. This is the beauty. This is the beauty of greedy. I've done this. I've done what you just told us. All right. I thought like maybe we have a case where maybe smaller and higher, and we move inward. Maybe we move right, not like outward, not inward. So this approach, Americano, believe me, covers Samsung. Oh my gosh, they really want me to buy. Yes, yes. Um, tell us when you are out. I am explaining something for you. So the idea is, guys, like okay, this two-pointer approach covers every possible case. All right, so we don't need to worry about anything. All right. So Americana, the thing I was saying is that like this two-pointer approach basically covers every possible option. All right. This is the beauty of greedy and this two-pointer approach. Like we don't need to worry about what would happen. What would happen if we have like a maybe like a smaller one and then the higher, but and then maybe getting like after the smaller one we get small. So we basically covered every possible case over here, right? Because we said that we have two pointers, and like we don't move the left pointer or right pointer inward, but we move the smaller one. All right, because this is the only case where we may have a chance to find a better option. So we basically eliminate all the remaining bad options. Like this is the BD, like BD of using greedy approach basically. So like yes, basically we cover everything Americano. All right, by everything I mean like of course that there isn't like two like a million uh possible options. Like we have like like we can move the higher one inward and we may see a smaller than our higher or even higher than our higher. Like we have two cases here and we have two cases over here for our smaller one too. We basically let's say um, thought about four different cases, right? Yeah, we don't have like a million different, but like the first time I approached, like I've seen this question, I thought that like, oh my gosh, there are too many possibilities. Like because I was thinking about like a brute force, all right, brute from like I was looking at this problem from brute force um approach or eyes, all right? And in brute force, you basically need to try every pair. But this is not a good way. And in during interviews, obviously, they don't want you to use this, right? But in greedy, we basically eliminated these two options, and here we eliminate one of the options, all right? And we focus on only one good option that we may give us a better result. This is the BD, and this is the Godzilla, guys. All right. So let's continue with this one. It's actually trapping the rainwater. I don't wanna study with water anymore. Best time to buy and sell stock too. Oh my gosh. Maybe we can continue with this one, guys. What do you say? I don't remember the sell stock one, but let's see. I have sold it, but let's see. I finished the diagram on the arena. Let's see. Um, espresso, yeah. Trusted, and chat. Now I think you can paste it, and I can drink a bit water. Like, do we have a system for maybe? Yes, I think we have it. Sad. So we don't have it here, but maybe, guys, most probably here. Sad. No. Where did I solve that problem? Um, Maybe here. Yes. So what I have done here, let me review a bit before starting. Oh, to live code. Sorry. So in live code, oh my gosh. So you are telling us that let me make it bigger. So let's say we have line 1, line 2. So line 1 and line 2 are larger but has smaller total area. Yes. S1 and S2 are shorter but has, yeah. The stream delay here is a bit so around 10 seconds. Oh my gosh. So um so the idea here is that we already cover this one too, because we are using max max method, and this behaves like a memory. So we have it in our result. Capito. Buongiorno, man. Yeah. Um, grazie. No worries, man. So basically, guys, let me review and let me also restart our tracker. So we're gonna solve the best time to buy and sell stock. This is easy, but I guess it's not easy. So let me review and remember the question. So we have some prices over here, um, and we are trying to find, um, you know, best day to sell. Basically, we need to buy, you know, like a small day. I mean, and sell when the price is high. All right. And we need to do this in ON. Um, well, what were we doing here, guys? Let me let me remember. Like, oh my gosh, like I have solved this question before, but you just forget. Let's see, like best time. So we need to we need to think about the thing we need to max, like we are maximizing basically. So um like we have a buying day and selling day basically, right? um but the thing is, guys, like we are going like a on, so output is only for the selling time. Like imagine like you bought a stock on day 2, and if you sold it at day 1 2 3 4, if day 5, all right, if on day 5, um you would get this one. So this is how we calculate. Let's assume like this is the best way, but let's assume you buy on day 1 And if you sell on day 2, then you would get -6. Correct. Yeah, yeah. Oh, hungry hippo said 10-second delay. Americana living in the past. Yeah. Um. So guys, now like what should we do, guys? Let me end the poll. Um. What was it again? Poll end, right? Yes. Now the next question is, what are we maximizing here? So you can answer, guys, and as you answer you'll get some points, and by the end of this stream we're gonna announce our hand of the king in the north, guys. Like I created my SQLite database, so like even after stream, after the stream, like the answers you give will accumulate, and your points will accumulate. All right. um yeah. So like this is to buy best time to buy stocks. I think this is the question we are solving. Best time to buy and sell. Maximize profit though. Yeah, yeah. So we need to maximize the profit basically. Yes, like this is good. This is good. Yeah. Basically, like yeah, we need to maximize the profit. Thank you. Thank you. You got 1 point. Wonderful. Um so profit is calculated by subtracting, right? So imagine we have a for loop. Um you know, like we need another pointer, right? But now, as I put the nested for loop, now I made it brute force. We don't need to, like, we shouldn't try every possible pair, guys. Like we shouldn't do this. No. This is big no. No, guys. Come on. We need to use greedy. So we need to maximize profit, but how, guys? I don't know, guys. Come on. Liability minus revenue profit though. Um, yes. Uh, but the thing is, the way we calculate, like, for us to calculate this profit, guys, we need two things, right? So that's why I type the second for loop. So we need two things. Oh, guys, now I kind of remember what I have done, uh, like solving this question before. Like like Americana. The problem I'm trying to tell you guys is we need two things, right, to calculate profit, because what the first thing is buying day, like buying, all right, first day, and the second day is the, let's say, selling, all right. So we need to hold these 2 days and then subtract and then calculate profit. But the thing is, if we do that, we have nested for loops and it becomes insecure, and Google won't won't hire us, right? If you solve this problem with brute force, they won't hire us. So we need to find a greedy approach. That's what I'm saying. Find the smallest number and the largest number after that. Actually, Americano, you are just my amazing engineer friend. You are just brilliant, all right? Let me type it. Let me type it like a brilliante. Anto, all right? Antonio, gracias. So you are a brillianto, right? Because you made me think that, like, since it is greedy, we need to think about the smallest and highest, like smallest and highest. So, uh, so as like, and we need to do this while we are going on, meaning we start from zero and we don't we don't look back. All right, we start from zero and we don't look back. So but the thing you said, American, is I think like instead of holding these 2 days at our hands, all right, what we need instead, now I remember, uh, maybe maybe the minimum day, like a smallest day. Like imagine guys, just imagine, just imagine. Let's take a screenshot over here, paste it over there. Guys, hear me out. So imagine instead of holding 2 pointers, right? Because 2 pointers become, insecure, and Google look at us like like this, right? If we do this, we like the idea is we don't need 2 pointers. Like at least we need to find a way where we don't use 2 pointers, 2 different pointers, right? And as Americana said, we need to think about smallest and the largest. So imagine we have a single pointer P, right? And imagine we are on day, let's let's make days start from zero, right? Day zero, day one, day two, three, 4, and 5. All right. So instead of having 2 different pointers, let's say we have only like single pointer, and it is on day two. Um, if we know, guys, if we know, like from previous days, right? Well, oh my gosh, Americana again started with what ifs. What if it is 3, 10, 1, 4, 3? So day zero, day 10, day one, day two, 3, 4. Smallest is 1, and largest after that it is 4. So 1 minus 4 is 3, but 3 and 10, 3 and 10 gives you 7. So smallest doesn't work that well. No. Um. So like what I can tell Americano is that um we need to have a history or memory. All right. I love using these terms like a history, memory. Right. So this will help us basically. Imagine we are at day two, and imagine we know the smallest one before us. All right. Smallest before us is 1. All right. And we basically can subtract us from the smallest one before us, which and this will give us um, 4, right? And we can store this in our global, like somewhere, right? By global I mean um, like we have a reference of an array that we store all of our values and we don't change it basically. So we get 4 over here. This is nice. I think this is the solution, by the way, guys. So imagine we are at day 3, right? We are at day 3, and the smallest before us is again 1, right? And we subtract it, and it is 2, and we don't need to store it because it is not bigger than the our previous 4. So let's move it. Let's go to day 4. And day 4, what is the smallest one before us? It is again 1. So guys, so this is the idea, guys. So the idea is, like, when I saw this question, I thought that I need 2 pointers, all right? Because I need to subtract them, right? I need to subtract, one from other. So, but at the end, what I have learned is I don't need to have, actually, we kinda, but not in that way. Instead of having, let's say, pointer 1 and pointer 2, what we do instead is, like, we go forward, all right? We go on, meaning we have single for loop, all right? And we don't look back. The idea is, of course, we're going to have a pointer, but the thing that we subtract from is not going to be another pointer, but instead the minimum value before pointer, all right? This is the history, guys. This is the memory, as I call it, history or memory, as I call it. So, like, um, so in each step, in each step, guys, we check our um previous smallest, all right? I mean, smallest that comes before us, all right? So, so to find the maximum profit, we basically take any value and subtract the minimum before it. So this is the formulation, guys. All right. So this is best time to buy and sell stock 1, and now it is time for us to solve a second version. And let me restart my timer and let's solve it, guys. Let's solve it. So now that we know how we can solve its first version, come on, man. Again, we have prices, which is awesome. You are given an integer. Yes, we have our prices. On each day, you may decide to buy. Yes, yes, yes. You can only hold at most 1 share of the stock at any time. Yeah. However, you can sell and buy stock multiple times on the same day, ensuring you never hold more than 1 share of stock. Find and return the maximum profit you can achieve. Did you understand anything, guys? Like, we have our prices, and now output is 7. Like, I guess in the first version it was 5, right? I guess, guys, now I see. No. Explanation. Buy on day 2, like this is day 1, day 2, 3, 4, 5, 6. Buy on day 2, which is, price is 1. Yes. And sell on day 3. All right. Yeah. Then buy on day 4 again and sell on day 5. So we are again kind of going this way and in ON, but we have some more choice to buy and sell. In the previous version, we were buying and selling only one stock, but here we can have a buy and sell multiple. But again, we need to uh, respect the time, right? On each day, you may decide, yes, 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 you can only hold, at most one. So basically, we're gonna have like a we will be able to hold only one stock at a time. So we're not gonna buy, let's say, three or five stocks at the same time. All right. After selling one, we can start buying. We can start buying again. So um, all right. So solve it, guys. Let me ask the second question. So, question is that, guys, what is the um what is the formulation of this question, or let me ask. No, no, no. I want to ask good question, not something silly. So even asking a correct question is kind of hard for this problem, right? So like to get help from you, what should I ask? Like this is something. So maybe, guys, like let me think. So we basically should go on, and again we have profit to maximize, and the decision we make is selecting. So in the previous question, we have only single pointer and a memory, or let me call history. So in the previous problem, we have like a single pointer and history. So here, most probably we're gonna make use of these parameters, basically, right? These ideas, these parameters. So here, let's try applying this same logic, and what we what we will have. All right. So um, so starting from day zero, guys, we need to know the smallest value before us, right? Smallest value before us. And let's say we are in day two, and the smallest before us is 7, and if you subtract them, we are gonna have -6. All right, this is our starting point. And as we iterate through, let's say we are in day 3, and the smallest before us is 1, and we subtract and we get 4. All right, but mm, but like to have this 4, we basically bought, right, and sold, right? So we buy at day 2, and we sold at day 3. So now we have ability to do this once more, since we sold. So how do we exactly know that we have sold or not? Like, and also we can do this as many times as we like, right? I mean, after selling, not selling, after selling uh, a stock, we are now able to buy another one. But the thing is, should we? Oh my gosh! Like, where and when? Like, which one is exactly? You know, like basically, guys, like there is phase one. I mean, phase two, and maybe even more. All right. Phase one is, you know buy and sell. So after selling, we can start again, buy and sell, and again, and then again. But the thing is, we don't know where it's gonna be. We don't know where, we don't know when, but we need to. We need to code it. So if value is negative, empty or sold. If value is negative, reset to null before buying. Um, Resetting. All right. So the idea of reset, I really like it. But do we have something to reset? Oh, yes, you are brilliant, Americano. You are brilliant. Yes, we have something to reset. You may ask, what is that? It is, guys, imagine that you are brilliant, Americano. The idea of reset is the key. All right. Let's imagine, guys. But 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 the thing is, we don't know where. But maybe it is not important to know where. We just like I mean like Americano, I really like the idea of resetting, but think like imagine we are at day two. So at day two, like we basically calculate, right? I mean calculate and find -6, right? This is the profit we can get. And we store it in our global variable. And at we are day three, right? We basically subtract one to five from five. One is our previous minimum, and so we get four, and we store it. But do we have some indicator that we we sold? I mean, what I mean is that like because at day five, Americano, at day five, we have we may have like a 6 minus 1 and we may have like more profit, or guys maybe oh Samsung again. Since it's smaller or larger, so it will become negative after selling. It will become negative after um tell me when you are free. um so I think, guys, we should think about every case as we did in water with most container with most motor problem. We need to think about cases and we should create a logic. Like we should say this and this, therefore we should only care about that because, like as Americano said, if we sell and if we start a new phase, a new window, um now maybe we should update our like a like a yeah, like we should update our minimum, our smaller, right? I mean basically we should imagine as if our sub problem is kind of this one now, and maybe if we solve this part too, and we may we can add what we find there from the previous result, and they can accumulate. Yeah, maybe this is the answer. Maybe this is the answer. Um, yeah, just updating the minimum. But when are we gonna update the minimum, right? Because in the first approach, yeah. So the question is, um, when exactly are we gonna um update the minimum, or start the next phase. Start, navigate to next phase. Navigate to the next. By the time you see me message, it's like already done. Oh my gosh. All right. All right. I guess you are back now. So the idea is like, when exactly this is gonna be happen? This is gonna, or maybe we can do this for every selling, right? And after every selling, yeah. Yeah, maybe this is the way. I am indeed. Yes. So, do we have no? So maybe guys, I can take a screenshot of it again once more. So the idea I have is, guys, as Americano said, like we should reset, but I asked when, and now I think it doesn't matter when, just do it every time. So what do you mean? But what I mean is that, um, like we are going on, we have a for loop, and in each step we have our pointer, like our pointer points to here, and we have a minimum, all right? And we basically, okay, subtract, I mean p minus minimum, we basically we are trying to basically maximize it, right? This is the formulation, and now we have another thing that telling us after setting you can start again. So um oh my gosh. So after selling we can start again. So imagine, guys, imagine we are at index 1, right? Imagine we are at index 1, all right? um and the profit we have is -6, right? Hungry Hippo, I tried this problem. I knew my lead code was rusty, but wow, it's worse than I thought. like like the greedy problems, guys, like are something different. Like it is quite different, you know. But we're gonna handle this, guys. We're gonna handle this. Um, I've been doing too much web dev. Like we need to do LeetCode, we need to do web dev, like we need to know Python, Java, and then Go, and then some a little bit Node.js. All right, we need to know some AI, we need to know some ML, right? We need to be a good communicator, right? Um, but we're gonna do all of them, guys. We're gonna do all of them. Just relax, just relax. We basically like imagine at day one, all right, day zero and day one. At day one, our profit is -6, right? But the thing is, guys, in the first version of this problem, like what we had there was, you know, trying basically we buy and sell only single one, but here we need to do it twice or maybe even more. Like there is no limit to that. Only limit is end of uh end of the input array, right? End of the input array. But now we need to find a way to describe a selection, but we don't know which one. I mean, we don't know the best selection, right? Because best selection is, I mean, buying on day one and selling on day six, basically. So this is the best. But by the way, guys, if we do that, we don't get like there is no possible way we get 7, because after like after buying at day 1 and selling at they did this day on this day, only one day remaining, and we cannot buy and say sell it in this on the same day. So basically our result is 5 here. So this means that we need totally a different structure, because this, I mean, so this means that the thing we need to maximize here is kind of different, guys. It is it is it's something. So however, you can sell and buy the stock multiple times on the same day. Buy on day 2. Yeah, buy on day 2 and sell on day 3. All right. So we just don't buy at day 1 and sell at this day, right? We don't do that. Yes, we don't do that. Then buy on day 4 and sell on day 5. Let me take a sip. Oh my gosh, guys. Means we lose profit though. Don Capo would be mad. Who is Don Capo? Is he the boss? Oh my gosh, guys. So but the thing we like I have realized, guys, like we cannot um we cannot let me type the days too, guys. Like this is uh day 2. So this is day 1, day 2, day 3, day 4, day 5, and day 6. We don't do like a buy on day 2 and sell on day 5. Buy day 2, sell day 5. Like we don't do that, because we would get only 5, all right? But what we do instead, something different. Buy on day 2, like like these two, and buy on day 4 and sell on day 5. Like this give us 3 and this give us 4. But the thing is, how do we know exactly when to start our next day? So basically, guys, we don't know it, all right? Because we are greedy. To be able to like greedy, we need to think about smallest or largest, and maybe sorting, I don't know. But smalls and largest, like this is the idea. I need to find a different courage, amico. My brain is too no, no, we're gonna handle this, guys. We're gonna handle. So the idea with greedy is that thinking about like a smalls and largest, right? Like we need to put this question in such way that picking smalls and largest will give us the correct result, right? But how? Yeah, this is the structure of greedy. But how, guys? How are we supposed to put put this question in such a way that only picking smalls and largest will give us? So let's see, guys. Like I like the programming part, not the thinking part. Yeah, yeah. Um, guys, this is easy. This is easy, guys. Um, so like at least we know that like our program doesn't need to know when exactly start and when to stop, and where to start phase 2, all right, or passively phase 3, because our input can be larger, input array can be larger, but the idea will encapsulate every possible state. But the thing is, like how, like in the first one we had one pointer and one history, and maybe here we may have again a history. It is easy. You better pass first try after saying that. Yeah, yeah. So like, I mean, it should be easy for us. This is what I mean. It should be easy for us. Um, like only thing we have, guys, here an integer array. So how come, like, how bad, how hard it can be? Can it be, right? Like we have an integer array. um, like we have prices. Oh my gosh, guys. 7, 1, 5, 3, 6, and 4. This is our array, and we are iterating, and we basically calculate the profit. So the profit calculation should, like, we should have a system for calculating profit. Like this is one thing we are sure about. And to calculate the profit, we have a system called, I mean, a pointer and minimum, right? And we are going on. So these stuff we know. Like, let's say we are here, um, and our previous um, buy is minimum value, integer minimum, right? Let's say minus infinity. And let's say, like, let me type the day, right? Day 1, day 2, day 3, day 4, day 5, day 6. So let's say we are in day 2. Um, the minimum value we have is now 7. But when did we exactly update the minimum value, guys? So as we iterate on each character, we also immediately update the minimum so far, um or minimum so far. All right, as we hit each element, we update minimum so far. So imagine we are at day 2, and minimum so far we have is 7, and our profit is minus 6, right? All right. So at day 3, our minimum so far is 1, and our stock price is 5. We calculate the difference, and now the difference is 4. So now the profit is 4. Let me type it with, so profit is 4 here. Here is minus 6. Here is actually, we don't have it, right? Because, yes, we don't have any profit, because it is not minus infinite or something, but we cannot just solve it without buying. And but if we buy in the same time and solve, the maximum profit is 0, actually. Yeah, we can do that. It is 0. So at day 1 our profit is 0, at day 2 it is minus 6, at day 3 it is 4. um at day 4, our minimum so far is still 1, and our profit is, you know 2. All right. And here max profit is 5, and here it is 3. So it is correct, right? How did it get that 7? By summing them up? But which one? So the 4 one and then the 3 one, I guess. So let me mm, explanation. Buy on day 2. Hmm. This is not about profits, I think. Let's see. Let's look at the, if we sort them, guys. Do we have, are we getting something meaningful? Let's say -6, 2, 3, 4, and 5. Like the profits that we can get. Let's see. Let's pick red. So buy on day 2, which is here, and sell on day 3. Yes. So like this is basically getting this profit. And day 4, which is this one, and day 5, which is this one. But hmm, we calculated difference, and it is like these 3, and these 2 are giving us, these 2 are giving us um not 2 but 4. Oh, so basically calculating, comparing with the minimum so far, we don't use the minimum so far. But actually, we have now local minimum so far instead of global. Global, we have local minimum so far. Previously, we had one global, and we are making every calculation using that minimum so far. But now we have global, I mean local. But the thing is, oh my gosh, guys, how should we sort? Like, actually, here, do we have something like a, do we sort? No. Like in the previous version, we had, one pointer and one minimum so far, and we basically subtracting and storing the maximum. So here, I guess sorting won't help us. Oh my gosh, guys, like this is, so so the thing I don't understand is how exactly we decide here. Like, because instead of buying on day 2 and selling at day 5 and getting 5 total, maybe we also do this, but in our result we have 7 instead of 5, because we, our greedy approach covered the case where we, where we buy and sell twice. Let's see. Where is the question again, guys? You are given an integer array. On each day, you may decide to buy, or on each day, yes. You can only hold at most one share of the stock at any time. So it enforces us to sell before buying it again. However, you can sell and buy the stock, yeah, multiple times on the same time. So after selling, you can buy, it means. Yeah. After selling, you can buy at the same time. Find find and return the maximum profit you can achieve. Maximum profit. Mm, to maximize this, we don't we don't have only one profit but multiple profit. I mean, we we will calculate the profit multiple times. Oh my gosh, guys, I don't know. Like, this is like even backtracking problems are easier than this. Come on, what is the idea, guys? Like, is it like minimum, some maximum? Like, do we have some sort of array or something that's store and telling us to divide? I don't know. Like, which question is this belonging to? Um, this is fuchsia, two pointer counter greedy, two pointer counter greedy. But trapping rainwater. So if I can use two pointer here, counter. What does counter grid mean? Um, counter grid. Oh my gosh, what is this, man? Counter grid or two pointer. Like, can we use two pointer approach here, guys? Like, where can we start from, left and right? Like, it can't be. I mean, like, the idea of, you know buying and selling multiple times, like breaking every possible idea. The solution to this problem makes me mad. Is it too easy? Like, is it because it is too easy, or it is too hard? That's why it makes you mad. That can be both. Um, do we use two? It is a lot more simple than you think. Like answer might be easy, but finding it is quite hard. Like, I had this issue in database lecture in college. Like, when I look at the queries, like, they are one line, two lines. That, like, when I look at them, I can understand them. But during the exams, like, finding or coming up with those queries was hard. Exactly. That's why I hate this stuff. I overthink way too much. Yes, yes. Like, the one thing about, like, another thing about lead code problems is that you need to pick right path basically while solving, because, for example, even the you know the like, this problem was hard. I mean, like, I couldn't solve this problem at first, right, when I first see it, because I thought, like, too many there are too many options, like, too many pairs, like I can pick this one. I mean, like, I can pick that one and that one and this one and this one. So how am I supposed to shrink the options so that, you know, like, I can come up with a solution, proper solution? But here, if we apply two pointers and we analyze every case and we create our formulation to calculate the water, and we come we we said that we should move the smaller one inward. I mean, like this looks nice. This looks nice, but here, I mean, cheat a bit. System output an answer. If you could make Azure records inside LeetCode, wire up API to query ChatGPT and output answer. So Hungry Hippo says that the solution is much easier than I thought. I'm thinking at least I want to frame that, like the thing I find hard here is like after completing one phase, right? After completing like a buying and selling, like of course I know that I don't need to know where exactly I'm gonna start again. So like at least I know this. And like the thing I find it hard is that um actually yes, so starting again, how can we probe it? I mean, how can we limit our algorithm so that it won't calculate 1 and 6, but instead it will try 1 5 and 3 6 so that it gets 7. But maybe in that case, like I have an answer for that too. Maybe it just doesn't, but since it tries every stuff and it stores, we have it. Samsung again, greedy buy and sell, too much work. Have cloud make the records with your account. Um, oh my gosh, guys, how many minutes it's been? Oh my gosh. I guess I guess now it is time to start the tutor mode because there is no there is no infinite amount of time. Um, Thank you. Now it is time for us to solve this greedy problem, and I have reviewed its first version of it, best time for buying and selling stock one. In that problem, I know like in the solution, we figured that we don't need to have like two pointers, but only one pointer. All right, we like solve this problem in ON, meaning that in a single for loop and in a single iteration, like this is important, single iteration. So we don't look back, right? So in each iteration, the another thing we need is not another pointer, but instead a history, as I call it. All right, um, like minimum value that we have previous before us. So at each element we just update the minimum so far if we see the minimum, and also we subtract you know uh, previous uh, smaller than the current number, and we store that profit. And this is like I quite understand the idea of not using two pointers but only one pointer. But here I need you to um, activate the tutor mode 2, and instead of giving us the exact solution or exact hint, you need to guide me and you need to put my thinking in a way that I can come up with the solution with myself. But like I mean, like we have solved the first version of this, but how on earth I can like we can just solve the second version of this problem? Like the place where I find it hard, I mean complicated, is that like our algorithm shouldn't um pick day 2 and day 5 and find 5, right? But instead it should do this in two phases, meaning that buy and sell instead of only single buy and sell. How can we limit that? Let's see, guys. Um, if you are worrying about picking when to buy and sell, don't. Um, yeah, like picking when to buy and so without knowing. That's interesting. So another thing I want to add before sending a request to AI is that, like, the thing I know about greedy is that, um like, we should put, or we should transform the question in a way that, like, only thing it does is like a calculating, you're using the smallest or the largest one. But here, like, I cannot find the smallest and largest thing, because um like, I don't see any connection between phase 1 and phase 2, right? Like, I mean, what are we calculating, and what are we maximizing here? Like, here again we are maximizing the profit, and to calculate the profit we need two things to process and subtract. So in the previous version we had pointer, a single pointer, and history, meaning the previous smallest number. But here, if we apply that again, we are, like, we cannot directly apply it, uh, or can we? Maybe I should, maybe we should focus on using the same approach we have used in the first version, but maybe slightly change it. But the thing is, if we apply the same logic from the previous, like, first version, we cannot end the phase and start a new one. Or maybe after calculating the difference, after calculating the profit, like, maybe after calculating profit in each step, we may just start again, right? And my friend, amazing friend, um, Americano, told me that, like, in the beginning of this question, he told me that, like, resetting something, maybe maybe resetting the minimum value, like minimum so far value, maybe we need to update it. And my another amazing friend, Hippo, told me that I shouldn't worry about when to buy and sell. I shouldn't care about. But the thing is, like, I need 2 days to subtract, and maybe, like, I should calculate profit for each day, right? Yes, yes. I think we should we should calculate profit each day, and then we assume, like, we should branch and we should save it there, and maybe we should branch, and in the another branch we should act as if, be like, we as if we start buying and selling, and again, and in the another one we should continue same as if, in the first version of this problem, right? I think this is likely buy and sell number one, but instead of when do I buy and sell to get the max profit, this is when can I buy and sell to get any profit. Yes, like, I mean, multiple times, but yes, like, you're right, but how? um, like, guys, let me, like, I think, I don't know, like, let me copy paste over here. The thing is that, let's say after calculating the profit on this day, right? Day 0, 1, 2, 3, 4, 5. After calculating profit at day 2, we branch into two paths, all right? And in one path, we reset our min so that in day 3, what you have, like you may have like a day, like a minimum so far 1, which is, min so far as 1, all right? Or you can maybe resetting to minimum so far to 0. So min to 0. Yes, these are two ways, and we need to keep exploring these two options. Like I said, the answer will make you mad. Oh my god, it's been, oh my gosh, oh my. So let me send the message then. So because we don't have all the time in the world, we already spent 1 hour this problem. Like, I agree with you, Hunger Hippo. The answer might be so simple, but coming up with that solution is hard, right? We have 17 hours to solve. No, 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 no. Like, we cannot just dedicate a lot of time to single problem, because we need to discover, we need to solve. Like we can dedicate 1 hour, or even better, 45 minutes each problem, all right? Above it is waste of time, basically, because there are a lot of questions, hungry people. There are a lot of questions. Believe me, believe me. So let's see how AI guide us, guys. Let's see. That's one way to remember it. You'll never forget the solution you said. Yeah, yeah. Like, I won't forget the solution I spent 1 hour or 2 hours either. Or I hope so. So let's see. You have done ton of real thinking here. Let me help you sort it, because you actually have two different correct ideas tangled together, and only one of them is greedy. One you are after. First, separate your two ideas. The branch, save it, act as if we start again idea. That's a real solution, but it is dynamic programming decision tree road. Yeah. We just talk about. Yeah. It works, but it is not greedy. Park it. Two, maybe just reset and reuse version 1's logic. That's the greedy seed. Follow this one. Your friend Hippo gave you the key. Stop trying to decide when to buy and sell. That instinct is correct, and it's the thing blocking you when you say, I need 2 days to subscribe. Maybe it might help if I say, think of this as sliding window of size 2, compare I and I minus 2. Um, like, if I need to do that, I mean, if I only need to compare, these, like a consecutive two ones. Um, but are you talking about the prices or profit wise? I mean, like in the example, the profit was something like consecutive, but there may be some cases where the days are not consecutive, right? But you are telling me that sliding window of size 2, mm, should I apply, like, should I create a profit table, like a profit array, max profit? But even in that case, yeah, maybe I should create, like, because I have created that uh thing. I mean, this is the profit, right? I don't know, maybe apply this to slide here. Like if you have 1 5 10 2, say 1 10, no, 1 5 10 2, buying and selling 1 and 10 has the same profit as 1 and 5 and 5. Oh, this is an observation we had to uh, make it, guys. I mean, hmm. So you are telling me that the answer is the same as the version 1. All right, all right. So like the thing is like making this observation is hard, you know. You need to try and observe and come up with an idea. I guess the answer is same as version 1, right? Like 1 5, you get 4 and you get 5, I think. Yes. Hmm. But the thing is, I mean, no, it is not same as 1 because here it is 7. Let me read what AI said. The one left over from version 1 that's trapping you. In version 1, history was minimum so far. You looked all the way back to the cheapest day. We are trying to drag that same tool into version 2 and it is fighting you. Here's the question I want you to sit with. Don't answer me, answer it on paper. In version 2, do you actually need to look back to the cheapest day ever? Or only back to yesterday? I guess what AI asked now and what Hungry Hippo said is the same thing, but how? How, guys? Like, apparently, we don't need to check the, you know, previous cheapest day, but only back to yesterday. Like, how, man? Like, even after seeing the, even after having a hint, still I don't see it. Why? Like, because Tornata, Koso Meso Persa, what did I miss? You didn't miss anything. You didn't miss anything. Um, like AI and Hungry Hippo said that applying sliding window and thinking about only consecutive ones um, is the way to solve this problem. But I'm trying to understand is how on earth would it help us, right? Or only back to yesterday, like how it can't be possible, it can't be possible. Like maybe like I can buy on this one on this day and I can sell on this day, and buy on that day and sell on that day. Like I'm just saying, I don't know if I can hint anymore without just giving the answer. Yeah. Like, but the thing I'm trying to understand, Hippo, is that like wouldn't like wouldn't this option uh be possible? I mean, because we are calculating the profit, and like imagine we have lots of days, all right? Imagine we have lots of days. Like I can buy on this day and sell on this day, right? And like buy on that day and sell on that day. If you were to use a for loop to iterate this, how would you tell if you make a profit between yesterday and today. If it is higher, I mean, if the previous day, let's say price of X or A, and if today's day is higher than it, for example A plus 1, then it's a profit. It should be bigger than that. Yes, all right. So this is the basic idea. It should be bigger than that. So this is the foundational knowledge. This here, right, Trey. Um, so it should be bigger, but you are telling me previous day and today, so consecutive days. You are telling me that. But what if I bought, at that day and sell in that day? So we are looking for accumulative profit, not max profit. Yeah, yeah, yeah. Accumulative profit. Yeah, yeah, yeah. Hunger Hippo told us something something good. Like, yeah, yeah. So this is important. Accumulated profit, not max profit. Um, so I guess that's why you are telling me that like we need to think about consecutive ones. Hmm. Like the answer is Hippo. Answer lies in understanding accumulative profit, and also like this is the first idea, this is the second idea. To to get the profit, today should be higher than previous day, and we are looking for accumulative profit so that for each day, now I get it. Hunger Hippo. Thank you. So since we are looking for accumulative profit, guys, only thing we need to do is, you know, if the day is higher than previous day, um, just sell it. But in that case, we would we would we would have to buy on each day and sell in the next day, right? Or we may have exactly. So like we have an input, like input array. So here prev is 0. We we take, since the prev is 0, we don't process it. Here prev is 7, which is again smaller, we don't process it. Here it is bigger, we process it and get 4. Here it is you know since smaller, we don't process with this one. Mhm. Here it is bigger, so we process. Here it is smaller. So the realization is, guys, since in the problem it says that you can buy and sell on the same day, right? On or at on the same day. On the same, like this is like this one is the one that makes this question, makes this approach available on the same day. On the same day. On the same day. So this knowledge changed everything basically. All right. Thank you. Thank you, Hungry Hippo. Now I get it. Uh I don't know, man. Like accumulative profit is the key here. And also you can buy and sell on the same day. Like as we read it, like we should have like a thought about its meaning, because in the previous version we let's check, check in the uh in the previous question, choosing a single day to buy and choosing a different, guys look at it, choosing a different day in the future to sell that stock. All right, this looks so different from my solution. um so in the first version, guys, the day we buy and sell are two different days, right? Two different. So that's why we need a history knowledge, history information that comes to us, right? But here in this question, we can uh, we can buy and sell on the same day. So that's why I don't know, man. This is still not fully sit, but let's continue. Like on single word can change the problem completely. Yes, yes, yes. The hardest part of LeetCode is figuring out what they want from us. Yeah, yeah, yeah. So that single word changes the problem, because like as we read the question, like we don't care about that word very much, but as you said, one single word can literally, drastically change basically. Yeah, let's see what AI said. So trace it by hand. Take the example for each day, compute today is like AI says that like compute today and yesterday, but and write down only the positive result. Now add up only the positive ones. Why does summing each little daily climb give you the same or better money than hunting for one perfect buy low sell high window? Hint: the problem lets you buy and sell on the same day. Yes, for free. What does that permission buy you? Like yes, trace the table. Yeah. Um. So thank you for that, but like still I didn't understand it. Like because the in the first version we cannot buy and sell on the same day, but here we can. So this changed a lot apparently. Um, but can you please clarify again why on the first version we needed an information like history information, all right, which is minimum so far, all right? But here we can apply consecutive. So I think about it is mathematics and numbers and how they function. Um, but the thing is like you gave me like a number like an input array and you just told me just calculate today and yesterday, right? Like this is not the way, like a pedagogical way to teach. Like why would I um try today and yesterday, given that I already know the first version, right? In first version we needed a history, like instead of another second pointer we needed um a history, like which is peer order, like which is like peer order, right? Like show me the way pedagogically, right? So we have a keyword here which is pedagogically, that makes AI um while explaining stuff, it adds some reasoning, all right, and it divides a single information into steps, and instead of giving the last and core idea, it also shows the reasoning behind it, or give some example, like a simpler example. So this is the keyword I like using it very much, guys. um so like I wanna understand, I wanna see the intuition that I should have as I see that I can buy and sell at the same day, on the same day. First problem, you wanted max profit, so it matters when you buy and sell and need to compare days. For this one, it doesn't matter. If you have 1 5 10, buying and selling for max profit is the same as buying and selling 1 5, 1 5 and 5 10. So yeah, so this is, I guess this is another important thing. Yeah. Let me paste it. Actually, even here. And the other thing you have said is this. Let me paste it. Yeah, you. That's why I said it's accumulative. Yes, it is about accumulative rule, I think. I see. Max profit. So even though you want to apply, even though you may want to apply, different days, at the end you're gonna have same thing. So it only matters if you have a profit of any amount. I will understand. I will internalize. Let's see. So you write to push back, just compute today minus yesterday was a what and not a why. Let me drive it so it's forced, not guessed. And you have already named the key fact yourself. Version 1 forbids same day, yes, buy and sell. V2 allows it. That single change is the whole story, yes. So the one thing that changed, how many transactions you are allowed. In version 1, exactly one. Yes, so we have unlimited number of. Um, uh, so it only matters if you have a profit. Yeah. So every difference in the algorithm, including why the history shrinks from min so far to yesterday, yes, falls out of this one line. Watch. Yes. Why version 1 is forced to remember minimum so far. Yeah. Why is it forced to remember? In version 1, you get one shot. Stand on day J and ask, what if I sell today? Your profit is, yes, the price I bought at. Yes. Since you only get one buy, you want it as cheap as possible. And it must be somewhere before today. So the best you can do selling on day J is this one. Today's price minus cheapest price on in days. Yes, so yes. Like this is it for version 1. That's why you must carry the global minimum of the pass. Yes. So yeah, like I understand it. The single transaction rule reaches all the way back, all the way back to the cheapest day. Because you only get to pick one buy and you'd better make it lowest, means so far is a direct consequence of only one transaction. The arithmetic that breaks version 2 wide open. Telescoping. So now the heart of it. Forget code, just numbers. Suppose prices rise 137. In version, you would buy at 1 and sell at 7. Yes. Now look at the. So now this is exactly what Hungry Hippo said. I think once you see the solution, you will instantly understand. Yeah. So now look at this identity. So yes, this is what exactly Hungry Hippo said. Um, like we try to apply the logic, same logic as version 1, and it says that it shows this identity, which is um, you know calculating the consecutive ones will give us the whole. The big jump equals the sum of the daily jumps. The middle number 3 cancels out. Guys, I had this in prefix sum too. It's about canceling out, guys. Oh my gosh, guys. It is about canceling out. So, like in prefix sum, there's a formulation, but instead of memorizing the formulation, if you know they cancel out, you can create the formulation in case you forget. You sold a 3 and rebought a 3. This is telescope. What does it mean by telescope? This is telescope. It is pure arithmetic, always true. Yes. So buy at 1, hold, sell at 7 produces the exact same money. But the thing is, guys, I have no idea what's talking about. So, so the thing is, guys, um, the exact same money as this chain it says. But here in our answer, all right. So we since we can apply multiple times, I mean, um, so here, like in the example, we don't see the canceling out mechanism exactly because the phase 1 and phase 2 has two different starting point. The first starting point is 1 and the second starting point is 3, so we don't see the canceling out clearly. But let's say we had 10 over here, right? And in that case we would have like a, yes, we would have 5 and 6, right? 1, 5 and 6, which means 4 and 1, which is 5, which is same as selecting 1 and selecting 6. But this doesn't cover the, this doesn't cover where the start point of these two phases are different. I need to see it. I need to see it. So the thing it explains is canceling out. I understand it, but maybe the like for me to internalize this, maybe the accumulative logic is um, good because like accumulative and also being able to do this again and again. But I don't know. Oh, I I have no idea. Yes, so Suka Dushe, I'll be excusing myself early today. No worries. Americano means redeemed Rosemary Olsenif to make my brain cell, function a bit better. Thank you, Americano, for these rosemary oil sniff. Like I really like smelling this. So now now my brain cells are functioning better. Let's see. Yeah, it cancels, like we understand it. Yes, here's where version 1 and versus version 2 splits. That chain uses two transactions with the same day rebuy. All right, in version 1 the chain that chain is illegal. You only get one transaction, and so you are stuck holding across the middle, and you must find the one best window unit means so far. Yes, in version 2 that chain is perfectly legal, unlimited transaction. Yeah, like it is explaining one aspect, which I totally get it now, which is awesome. Thank you for explaining. But the thing is the thing is instead of doing that one, we we do this one and this one. All right, that permission Hippo told you about, don't worry about when to buy and sell. This is exactly this, because you can decompose any strategy into daily trades that sum to the same total. You never need to think about long windows at all. So the decision collapses to each day independently. Once every strategy is just a bag of one-day trades, each consecutive pair becomes its own independent yes or no question. When prices rise, the daily trade is positive. Take it. Mm, Why today why is never arbitrary? It's literally the one-day trade. Your history shrinks from minimum so far down to just yesterday's price because unlimited, unlimited number of transactions plus same day decompose into daily trades. Each day only cares about the day right before it. Oh, thank you for the explanation, but in the example you gave, like I can see the canceling mechanism. But um but in the example for this input, right? We have different pairs. Like we don't cancel out anything. There can be some cases where we literally cancel out. All right, I get that idea. Like three is there in phase one and phase two, but here, like I don't understand it, man. How how did we conclude that only calculating the consecutive ones and picking the positive ones is the way? I know it has something to like it has really something to do with um, being able to buy the stock multiple times on the same day. I mean, selling and buying the stock multiple times on the same day. But like, I also understood the canceling mechanism. But here, for output 7, we don't cancel out anything. We picked 1 and 5 and 3 and 6, right? So there is no cancel out mechanism here. But I guess we use this because we know that we need to calculate the consecutive ones and increasing ones. But how did we conclude that we need to, or like calculating the consecutive ones is the way? I don't know, guys. Like one little thing, and then I will continue with our next question. But like I wanna see it, man. Let's open the next question, which is lemonade change. Like I have solved this question. I can solve another valid parenthesis. All right, so I'm kind of familiar with it. So maybe we can go another pattern, which is rows. Monotonic stack greedy. Oh my gosh. So remove k digits. I think I have solved this problem before. Let's see. But guys, do you see it? Like, for example, here, like, like, this is two pointer counter greedy sub problem subtype of greedy, and like look at how much differ, even how much problems differ even in the same subtype. I'm not talking about greedy like a general type, but even its subtypes differ a lot. Like like the approach we have used in contain with most water is quite different than the approach we have applied on best time to buy sell stock 2. It is too different, man. And maybe my next question will be, how on earth these are in the same subtype? Let's see. My next question is that how on earth do they belong to the same like subtype of grid? I mean, um, here we have like a container with most water, and they they belong to the same subtype, which is two pointer and counter grid. So how come? Because in container with most water we had like we were like we applied literally two pointers and always moved the shorter side inward. So here we sum every positive day-to-day delta. So I mean, what is what is the resemblance here? Like I made AI to gather same type of same subtype of grid problems, but even they differ a lot. So stop, look closely at the traits yourself picked, because here's the punchline: they are the consecutive pairs. They've been doing the method without noticing. So your own answer is already consecutive. You said buy at 1, sell at 5. Yes. Yeah. That's one day trade. You said yeah. Also neighbors. Mm, so your optimal solution is literally take the positive consecutive diff. Then my question is that what would happen if we have this one at day one? All right. Then find it. Come on. Then find it, man. All right, all right, all right. Let's see how it will answer this question. Come on. Like AI doesn't understand me at all, man. My question is that what would happen if we have this, all right, as an input? Come on, do this. Oh, maybe again you would say since 1 and 7 is consecutive. But what if they are not consecutive? Oh, in that case, we would chain. Oh, now guys, the real answer, guys, real answer. Like let me tell you something. Let me tell you something, guys. So the thing is, guys, hear me out, hear me out, hear me out, guys, 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 guys. Now I have understood. So the first thing we need to know, guys, is like a chain mechanism, all right? And we can, buy and sell on the same day, right? On the same day. So like this changes everything. So we need to be aware of it, right? Chain. So the other thing is, guys, even AI doesn't answer it correctly. The thing is, guys, imagine you have this, right? Right. What would you do? You would, you know, like like there are two possible ways you can do. You can buy and sell on this, right? Which gives you 6, right? Or you can immediately, use consecutive like chaining, and you would get like a 4 and 2 here and 6 in total again, right? In two ways, like in consecutive or in, one step and two step, you are getting the same result. So it doesn't matter the order of these numbers, basic. I mean, not the order. And also, if we change the order, would it matter? Let's see. Of course, it would matter, right? Because this is literally a different question. All right. So the thing is, if we have like this, it doesn't matter if you do consecutive or one step because they are same. Yeah. But this is when it gets bigger. What if it doesn't get bigger? We would have like calculate this one, 6. But what if like we have 3 here but 7 here? So we would, calculate this one, right? And 6. Oh my gosh. Look at it, guys. We have 2, 2, 2, and this gives us 6, 2. So what I mean is that we need to try different cases and see we can do, consecutive one. Because in tripping water problem as well, we tried different cases and we literally saw that the only logical move is moving the smaller one. And we have the proof of that. In this question too, we have to try different cases and see and prove it basically. So, but I was stuck at, how do we start? And Hippo said that you don't need to. Oh my gosh. But in that case, there's a different approach. And that different approach is taking consecutive ones. All right. Let's see. Oh my gosh. I've been talking all the time. Let's stop it. So good eye. They look nothing alike on the surface. But what did I ask again? Yes, on the surface, like how they resemble to each other. The question was that because even in the same um, sub problem, subtype, they differ a lot. So it said that they look nothing alike on the surface. You're half right to be suspicious. That label has a slash in it. He has 2 pointer account already. So it's not one shape. It's two cousins under one color, and your two problems to sit on opposite sides of that slash. Hmm. Container with most model was 2 pointer. All right. The counter half. One forward accumulator. Yes, this is a term. This is a terminology we need to get familiar with, guys. One forward accumulator. But we had this accumulator in pre-order too. I guess it was not accumulator, but something else. So don't look for identical mechanisms. They aren't any. There aren't any. You are grouped by a sharp gridded justification style, not by the same moving parts. Hmm. Shared by gridded justification. Oh my gosh. Grid, gridded justification style. So maybe guys, we we are the champions, guys. Right? Champions of LeetCode, right? So I really like the term greedy justification, guys. Save it. The shared spine. They already in meaningful order. You never sort. Yes. So I like thought about we have thought about sorting, but that wasn't an option for us, right? Container. Hmm. So index exposition of all, index the day, one linear sweep. Yes. Running state, 2 pointers walking inward, one running profit total. Yes. Each step makes an irrevocable local decision. Discard the shorter wall forever. In our question, take or skip today's delta forever. Hmm. That decision is justified by an exchange argument. Shorter wall cannot do better than now. Positive step always helps, negative never. I think another thing we need to, you know, get familiar with is this one. Um, Positive step always helps, negative never. Um, so basically, in container problem, we went you know on from n square. So this is huge optimization, and here we have this again. So deepest common thread is thread for the exchange argument. The thing I offered to show you last message. So both problems look like try every pair and both collapses to one pass because at each position you can prove a local move is safe to commit and never erased. Spell out the exchange argument in each. Yes, stock 2, each one day delta is independent. Taking a positive one always adds money. Skipping a negative one costs nothing. So commit per day, never look back. Same no regret local decision. Like, all right, guys. I think we have spent enough amount of time for this problem. We get it. So it is in even in the same subtype we have two different things. One is two pointer and the other one is counter gradient. All right. Monotonic stack. So maybe the reason actually I have asked this, right? So why they land in this one, not the other colors? This is the part that makes the taxonomy click. Look at what trait one rules out. Internal scheduling, sort and pair. You must sort first, then sweep. Fuchsia, the data is already in the order that matters. All right. All right. So this is why we have these questions in this subtype. So data is already in the order that matters. It's because in some of the greedy problems we need to sort them. All right. Positions on the x-axis, days on the calendar, characters in the string. Sorting would destroy the meaning. So you exploit the existing order with a pointer counter sweep. That's a real membership test for this family. Is the input already meaningful order? Guys, that's the good question to ask because in the knapsack problem too, the order does not matter, so that we literally go like an ON from starting from left to right and processing each number, each element, each item, and deciding whether we are including or excluding that item. So the order doesn't matter. So in today's stream, in the beginning, like the first question was, um, knapsack problem, and there too, I saw, like we've seen this, meaning of order or importance or main value of ordering there as well, because based on that, the approach we use changes. So I sweep it once with on state and exchange argument. Mhm, I see. That shared prerequisite plus the no regret sweep is what makes them the same subtype. Not the fact that one uses 2 pointers and the other uses one counter. Hmm. Actually, now can you please explain why we use the term counter greedy in this problem? Like in the container problem, I can literally see 2 pointers, but here what is counter exactly here, right? And also, what would you put the first per version into, like, which subtype you would put the first version of this problem into? Let's see. So our next question is that, guys, I think this one. Remove k digits, and the problem is that is this one. So given string num representing a non-negative integer, an integer return the smallest possible integer after removing. We don't understand anything. Let's look at the example. So remove the three digits, 4, 3, and 2, to form the new number, which is the smallest. So we're gonna need to remove k number of, after removing k digits. Yes. And we will remove the leading one and the number. Note that output must not contain leading zeros. All right. So this is a case that we need to handle. Um, like which one? Oh my gosh, guys! Like, I don't like this greedy at all. Like, greedy is stand like quite different topic, guys. Quite different. Look at it, guys. Like, this doesn't resemble to like a binary search sliding window. Two pointers. This is something else. Like, we need to remove k digits, but which digits are they exactly? Like, which digits are we talking about? Let's look at it. Oh my god. 1, 4, 3, 2, 2, 1, 9, right? And I guess I may have an idea, guys, right? Because since we are now working with numbers, each number had, like, now, guys, another thing that I learned today, guys. Does the order matter? Like, today's important thing is, does the order matter? So this is the thing. I was like, because even in knapsack problem we've seen this, because since the order didn't matter, we just start from left to right, right? We just start from left to right. um and here, like, again we see, like, but here, guys, order matters, right? Why? Because each number has its value based on the decimal point, right? I mean, the position. And we don't move numbers. Actually, maybe order does not matter. I mean, we just, like, we already don't change the order of numbers. But what I meant was, I think, for example, we don't remove that one and keep that one, because, like, 4 is both bigger than 1, and more importantly, um it is on the left side. If it was here, we wouldn't care about this very much. Yes, yes. So we have two cases, right? uh, the the comparison compare and the digit location digit location, I don't know, maybe decimal and digit location is also matters here. um and we need to remove k number of digits. We need to pick which one. So again, like we need to pick or select, but the logic we use for selecting is greedy. And I think we're gonna do again on. Which subtype was it again, guys? Monotic stack greedy. So we need to use stack, I think. Why and how? I don't know. So do we have something to read here? I get it. So I guess the last question I have asked is why they different? Why do they different? I mean, stock one and stock three. What no. What counter means? I guess we have two questions, right? Yes. The first answer is what counter means in stock two. The counter is just single running tally you accumulate into during the sweep. Single running tally you accumulate into during sweep there. Here. The profit total. Hmm. So this is our counter, I think. Bump the counter. Like when I saw counter, I thought about 1, 2, 3, but it doesn't for iteration, I guess. Counter greedy, you walk the array once, and the greedy decision at each step: do I add to my tally or not? No two pointers, no sorting, just one scalar that counts up as you commit each increment positive yes. So the classic sibling is valid parentheses, where the counter is yeah. So where stock one belongs, and it is not fishy. Yeah, stock one transaction minimum so far is blue. Yeah. All right. So like even like we have stock one and stock two, right? And they belong to different subtypes, guys. So all right, like I'm kind of familiar with this approach, like running some because it quite resembles to pre-order, um, but not the so other. Um, so now maybe you should run some checkpoint or some skill to save our process and save our thought processes, right, into uh, related lead code folders. Because now we will start studying a new question. Let's send it, and also maybe I can just increase. Hmm, but you don't hear it, I guess, right? Hmm. There's an issue with my audio, but how about now? Anyway, all right. Now it is generating necessary files so that next time we will remember what we have thought and how we have thought. Now monitoring stack grid. So maybe we can just open and see the structure it has. Monitoring stack is a specialized stack data structure where the elements are kept in a specific sorted order. Specific sorted order, guys. Like these terms seems, helpful, might helpful for us. Either strictly increasing or strictly decreasing from bottom to up. All right. Types of monotonic stack. Increasing stack. All right. Before pushing a new element, pop all elements from stack that are greater than the current element to maintain increasing order. So let's see. Monotonic stack. Monotonic stack in six. Should we open this? But you don't hear, right? Oh my gosh. Another. Bro, bring more conceptual. Oh, actually, guys, we can create our own animation, but let's see. We have stack, all right. This is increasing, this is string. So we have an array. So in our question, we have our number, yes. Template for implementing the monotonic stack pattern. Oh, actually, hmm, I think it is better that I just, you know, run that command to reset my OBS. I think we have an issue. Let's run it. Can it be because of the storage I have remaining? Let me check, guys. Hmm, maybe it is because of that. Let me handle it, all right? Because when I have low amount of storage left, OBS starts behaving strange. So, all right. Now I'm trying to solve the OBS issue that I have. I need a minute, guys. Hello. I guess we have an issue with the background sound, and I need more disk space, I think. All right, while can I? So now you are seeing. No, I think it is kind of stuck. Hmm. I think we can take a break now. Um, let's make it let's make it 1 hour because I need to fix it and I don't know how much time it will take. So let's take a break for 1 hour, or let's make it 50, but let's see, all right? See you after the break, guys. I hope it will switch the scene. I guess we are back, guys. Welcome, welcome in. Instead of taking a long break, guys, since we don't need any break, we're gonna continue. All right. And now I thought that it would be great, like for this problem, since we don't know the stack, monostack for this problem. I figured that we can immediately, you know, talk AI. And how are you? I hope you are doing just fine. Now, I want to study this problem. Like we are practicing greedy approach. Um, but the thing with greedy is it has its own subtypes, and this subtype, this problem belongs to um monostic, I think. Now, explain thing without giving me the real answer. All right, like I think we activated tutor mode 2, right? And yeah, explain this pedagogically. I want to understand this fast. So, like, since there are tons of questions, guys, um there is nothing wrong with learning things fast. um yeah, we are big, right? So, and also resume the Pomodoro. We have lots of them today. And the topic we have now is uh, monostic problem. All right, we updated the topic. Yeah, let's see how AI will guide us. And also, yeah, how about it? Yes. So, doing great. Thanks for asking. And yes, Tutor 2 is on, albeit the intuition with you, and hand you the turns rather than the answer. You're right that this is the roles monotonic stack branch of greedy. Let me get you to feel why before you touch any code. First, foundation. What does the smallest even mean here? So here, um, yeah, it is about the decimals, right? Let me also ask it. Oh, I actually not here, but here in another session. What is equivalent of balsamic dairy in English? Let's first find the terminology. Place value. Oh, all right. It is place value. So the place. So we have, let's like 1 4 3 2 2 1 9, and we need to remove 3 digits. All right, and there must be a formulation or logic for picking them and selecting them, right? Which three of them will be? So our goal is to find the smallest one, right? To find the smallest one, like for example, removing this would give us, I mean, like a -1. So removing this would give us this one. Removing 4 would give us, you know, this amount, and so forth. So it is obviously not, selecting the smallest one here, but I guess there is another logic here. But AI said that what's the meaning of smallest even here, right? So the meaning of it is like There's a reason why we need to use stack, right? Because after removing these numbers 4, 3, 2, like 1 is still, you know, at the front. But let's see this. I have um honestly, frankly, don't have an idea how to implement this like a monosig thing. So that's why we're gonna learn this, right? So we need to be fast. Let's go. So what does smallest even mean here? Before an algorithm, pin down the goal precisely, look at the inputs. You remove exactly k digits from a string length of n. So question number one is, guys, answer this in your head. After you remove k digits, how many digits does the answer always have? Like the remaining ones, obviously. What do you mean? It's always n minus k, a fixed length. That single fact is the whole key. Oh my gosh. Like I don't see any special thing about this, all right? Um Fixed length. Because the length is fixed, comparing to candidate answers is just left right digit by digit like dictionary order. So because the length is fixed, yeah, comparing to candidate answers is just left to right digit by digit. So the leftmost digit matters infinitely more than everything to its right. Get the most significant position as small as you can, then the next. I think this might be idea, but I feel some recursion vibes over here, guys. Recursion vibes. I feel some recursion vibes over here. Hold on to that. It's the lens for every decision you'll make. Now the local move. Let's read example one together. Um, so we have our number. It is an integer array, right? No, it's a string. Doesn't matter. So walk left to right and ask at each step, is this digit helping or hurting the small leftmost goal? So now, guys, like we have said, our goal. Our goal is the leftmost digit matters infinitely more than everything. So the most significant position as so we need to set or get the most significant position as small as we can. All right. Our goal, like obviously this is a goal, but since we are extracting, I thought I don't know. So maybe, guys, at least in this greedy question, defining actually in every question it is important anyway. So we basically want to make our leftmost digit small as possible, small as possible. Mm, yeah, but how? Like the how part is always harder one. So it's the lens for every decision you'll make. Now the local move, and hold on a second, guys. I think now it is it is better. All right. Now the local move. Let's read the example one together. Um, yeah, so walk left to right and ask at each step. So since we are like, we need to obviously make this in ON, right? And we need to decide at each character, basically, right? Step. Is this digit helping or hurting the smallest leftmost goal? Smallest. For example, we are at 1, it doesn't hurt, but this Hmm. I guess, guys, like now I feel like what would happen if we, you know, s- get rid of the ones that hurts us most. All right. How about that? Maybe that's a good idea, right? Let me check the stream once more, guys. I mean, in this session, I guess it is nice. Yes, yes, yes. I can hear. So, um, the idea, like, what would happen if we, get rid of all the bad numbers that we hate most, all right? And if we get rid of them, you know, get rid of the topmost three. Hmm. So instead of which one to get rid of, we here at this stage, at this yeah, now we we have answer, and the answer is we need to get rid of. Oh, thank you for the follow. Welcome in, welcome in. How are you doing? We are studying greedy monostate problem. Hi, King. Welcome, welcome. How are you? How are you, man? Hi. I hope you are doing fine. Today we are studying greedy, and today we started solving some a knapsack problem in the morning. Still it is morning, but early morning. Now we are solving some greedy problems, and this question is one of the you know monostack subtype of greedy problem. And now, the question we have is this: remove k digits. The problem we have, maybe it is a good idea that I put my the question somewhere appropriate on the scene, so that um everyone can see which problem we are working on at the moment. So the problem is this, and we are trying to find which numbers, which digits we need to get rid of, given k is 3. All right. What would happen if k is 1? So it has some k's. Forget about leading zeros. But here, I guess I'm getting idea, but still, it doesn't fully clear. So 1, then 4. So the digits are climbing. A climbing pair is fine so far, and the small one is already on the left. So, and then 4 then 3. Now it drops. Here's the tension. So basically, guys, we basically um, you know evaluate every possible case, right? Like, we basically started from left and leftmost side, and each in each step we need to make a decision, right? And we make this decision based on the comparison. Let's say these two, right? But also, like, there is a place value. So, like, here 4 is bigger than 1. So it means we shouldn't change like, we shouldn't swap these two, because if we do, then, or no, 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 our goal, guys, our goal to make our leftmost the smallest one. All right. It is about, so we need to have the goal clear. So our goal um is this. Yes, get the most significant position as small as you can. So I think I have, like, I pasted this as goal. Yes, this is the goal. Make the most significant position as small as possible. So when we find, but, like, there can be different ways of doing that, right? For example, swapping that one or swapping that one. So I mean, the goal is there, but the way we do may vary, right? Let's continue. So 1, then 4, the digits are climbing. A climbing pair is fine so far. Why? The small one is already on the left. So our goal is to make the leftmost one smallest, all right? But the question I have is, why do we compare the consecutive numbers? Because we may use swapping operation as well. Let's see. 4 and then 3. Um, so here's the tension, right? So as soon as I see the word tension, the water problem uh, be solved. Like I remember that, all right? Because their only um, meaningful move was I mean, you know, move the smaller one inward. Because in in all other cases, uh, it they weren't a good move, all right? So this was the only case we may have a larger container. So you got a bigger digit sitting in more significant position than a smaller digit right after it. Right, it's like this term is important because we are comparing values. We are comparing consecutive values. So question two, this is the core. Sit with it. All right, you are allowed to delete a digit between the 4 and the 3. Which one should you delete to make the number smaller? And why does the fixed length inside from question 1 force that choice? Hint, imagine both outcomes, okay, this one and this one, and compare them at the first position where they differ. They differ at here. So the twist that forces a structure, not just a single pass. Here's why this isn't one pass and never look back problem. All right, I I like the term it used because the previous question we have solved using that approach. Suppose you just deleted the 4. Now the digit before it, 1, yes, sits next to a brand new neighbor, yes, and after the next deletion the neighbor changes again, yeah. So question 3, when you delete a digit, the digit you previously decided to keep might suddenly become a deletion candidate too. So you need to be able to reach back and undo a keep you already made. So this is where we decide that we need to use that kind of data structure, which is monostic, all right? What data structure lets you look at the most recently kept item and throw it most recently kept item and throw it away if needed? It's the monotonic stack, half of the answer, but I want you to name it from question 3, not me. So your 3 reasoning tasks: confirm the answer length is fixed, leftmost dominates, and state the rule for which digit to delete when you see a drop. Like I don't understand this part at all. Name the structure that lets you undo previous skips and explain why you need. Mm, to be honest, I kind of feel lost because in the example you gave, what I see is like we basically we are trying to make the leftmost part bigger. I mean smallest as small as possible. But and then you mentioned about something, okay, after like deleting something, the neighbors change, but I didn't get that part, and I didn't understand why we should use monosig stack because like you literally said to reach back and undo a keep you already made. So, but first I need to understand this phrase basically, right? Um, And also you explained we cannot solve this problem like in single pass. So this realization is also important. But what forces us to do that? I didn't get it. Yeah, you need to clarify. So, like, honestly, I didn't get, you know, any, just a small amount of knowledge and information. So our goal is make the most significant position as small as possible, but it is about how we do it, right? And how do we do that? Now the local move, another term we use a lot, local move. Um, Walk left to right and ask at each step, is this digit helping or hurting? This, like now I see that I remember the gas station problem, like helping or hurting. But gas station problem had running state approach, which is a different subtype of greedy approach. So, um, all right, let's see. And I have started the timer. We have 20 minutes left. You're not lost. You actually got the goal exactly right. Make the leftmost as small as possible. The only missing piece is the mechanism that achieves it. Yes, we need that. So your two confusions, neighbors change and undo a keep, are really one single idea seen from two angles. So the example that shows everything. Forget it's too gentle. Use this one. 13572. So walk left to right and keep a list of digits I have decided to keep so far. Um, so we decided to keep it. So like the word decided is a strong word here because greedy and dynamic programming questions are similar. So we kept this, right? And since it's climbing, looks fine. Yes, looks fine and looks fine. All right. There's nothing wrong with that. So far, every digit looked perfectly fine when you first saw it. Each was bigger than the one before. Hmm. In this question, guys, I mean for this question specifically, maybe the way so maybe in greedy problems like in general, we just maybe we can try like a arbitrary or random order numbers and see and apply the question uh, apply the what the question asks and see how it behaves and how would we have to behave differently, how we would have to different behave differently. Yes, so because here for example, and if the k is 2, we would need to move on these two, right? But if it is change, if it's like this, again same. But if it is like this one, since after 4 we are decreasing, mm, anyway, I don't know. I mean, what I meant is like trying different inputs and see how they differ basically. But pure climbing, no reason to delete anything. Now, here's a realization you are missing. The 2 is tiny and it just arrived at the right, but you want small digits on the left. Look at 1357 followed by 2. That 7 is a big digit sitting in a significant position. There is a much smaller 2 right after it. The 7 is liability. Delete it. So in our like in this example we have 2 at the end. First 4 doesn't cause an issue, but the 2 like we can use it better. Or actually the position will be same, but we can pick or we can delete another. All right. Now watch what neighbors change. Yeah, so where were we? We were talking about 2. Yes, here's a realization. 7 is liability, deleted. Spent 1k. So we are deciding, I mean, we are deciding what our liabilities are, basically, right? Maybe I think yes. So now watch what neighbors change mean. So delete 7, kept 125, found 35, and now 2's left neighbor is 5. Hmm. 2's left pointer. Now I'm thinking that what about the right neighbor? But I think we don't care about it. So basically, guys, I can take a screenshot of it and paste it and see what this is, right? All right. Let's make it a little bit bigger and check. So we had like a 1, 3, 5, and 7, and 2, and 7 was here, liability. So delete 7. Now 2's left neighbor is 5. Yes, it was 7. Yes, 2 is smaller than 5, smaller than 3, smaller, no, greater than 1. So delete 5. Oh, like we make our decisions based on this comparison, apparently. So when we have a number, a digit that is smaller than its left neighbor, we should delete it. After deletion, our data structure should support us. The next should give us the next neighbor, right? Like this is literally the function of stack, right? And since 2 is still smaller than its left neighbor, we remove it 2, and 3 is still, so like this is how it functions. But how did we come up with this idea? I mean, we had a number, right? We had our number here, and our goal was, making the leftmost digit as small as small as possible. Yeah, but the way we do is finding the first smaller one. I mean, as we go left to right, when we see a number that is smaller, all right, it is where we need to delete its left neighbors. I think this is what I understood. But why? So all right, so now watch what neighbors change. All right, so like this data structure is like this, literally tells us use stack, use stack, use stack. All right, this is screaming for us to use um you know stack. All right, let me use my eye drops. So now your 3 confusions answered. Yes, why do neighbors, so yeah, I like we understood that part. Reach back and undo a keep. Look what just happened. You had already decided to keep 3, 5, and 7. They looked great at the time. Then 2 show up, and you had to undecide all 3. Hmm. I get it, but like this term, which is, they looked great at the time, is, you know, is another logic to build, right? I mean, we should have a logic to do this, and that logic, I think, if they are increasing, they are in the correct position, basically. Oh my gosh, guys, like this is this is something, guys, and we're gonna understand it, guys. All right. So let me drink my water. So basically, guys, imagine you have a number 5, 6, 7, 8. All right, and let's suppose case one. So we need to remove one character, one digit. But which character would it be? So now we start defining our goal from, outer perspective, which is our overall goal is making the leftmost digit as small as possible, right? Leftmost digit. So yeah, and so like we know that we need to, iterate through numbers, basically, and in each step we need to decide. And let's say we see a bigger number. So now we are evaluating our options, like our cases. We may have a bigger number, we may have a smaller number, right? Let's say 5 and 4 and 7 and 8. All right, and let's suppose case one. So 5 and then 4. So now, obviously, 5 is in the place where we should remove, right? Because we literally have a smaller one and we can replace it with this one, right? Yes. So when it is bigger, there is no issue, right? I mean, each consecutive ones, if they are bigger than each other, while we are going from left to right, there is no issue, right? But again, even in that case, what would happen when we hit the end? So we should remove the rightmost one. No. Yes. Yes. Yes, we should remove the rightmost one. So so when the number is smaller, we should get rid of this one. So I guess these are two cases, right? How many different cases should I care about? Thank you for the explanation. Now I wonder how many different cases I should care about. Because let's say our input was, 5, 6, 7, 8. In that case, numbers are in increasing order. So I guess there is no issue. I mean, and we should remove the, rightmost one. But let's suppose our input was 5, 4, 7, 8, and in that case, after 5 we have 4. All right, but and since we want our leftmost digit to be small as possible, we should get rid of this 5, right? But the thing I want to understand is like there is mathematical version of this, and then there is code version of it, or let me say math, or maybe logic, or maybe pseudocode. All right, maybe pseudocode, and then the real code. Like these are the phases. Now in this question we know that on the leftmost part, we need to have like as small as possible. But like like the DP problems, like even N Queen's problem is kind of easy, Like I don't know, maybe it is because I understood the depth search and recursion very well. But um here I don't understand it, man. Because, for example, in most like a container with most water problem, we literally had the cases. Like I could literally show like from like using two pointers approach, like, and also we had our formulation to calculate the water, all right? And we thought that what would happen if we move the right move pointer and what would happen left pointer, and the logic there was moving the smaller line inward. So like I don't know, maybe it is because I understood the question, but like here, like we have lots of numbers, like this is what I mean. We need to, like, I need to localize. Yes, I think the issue for me is, localize. Maybe I should read a book on grid, I don't know. Because the way I understood recursion was reading a book about recursion. But here we have lots of numbers. And maybe the point I struggle with is localization, knowing what to decide. Because in DP problems, in backtracking problems, we don't care about all input. We only care about part of the input, right? So like the part where I struggle now, guys, is to which numbers or which, like, how many different cases we have basically. All right, like it is kind of recursion. It looks like a kind of recursion because in recursion we delegate our responsibility to our sub problems and we expect them to solve the sub problem, and then we do some process with the return type of our sub problem. In DP, we use that subproblem to generate ourselves to find the formulation of the main problem. But here, like, I understand, it's at least I can see the reason why we may need to use stack, because it says as we, let's say this is 2, as we hit a smaller number, now we should remove, all right? And after removing, since our new neighbor will be 7, like we need a system, like we need a data structure that will make 2's left neighbor 7. All right, this is basically stack, because in stack, if you move, like, imagine in stack you have, let's say 4, 7, 8, and as you hit 2, which is smaller than the last element, which is the top element, we basically remove it. And after we remove it, we basically have like a literally 2, 7, and 4, right? So they are now neighbors. So now I can understand the reason why we use stack, but I don't understand the greedy approach over here. Like I understand our goal, our primary goal is making the left part as small as possible, and we iterate basically. And like someone should teach me or show me why we only compare the consecutive ones, because we literally we could use a swapping operation or something, because I have seen lots of questions, all right, where we use swapping. For example, the what was it again, heap question, for example, right? We basically swap, and there are some array questions, right, where you literally can swap any number from any position with any position. So like AI started explaining things like comparing the consecutive ones, but before that it should show me why I should do that. Maybe the maybe the maybe the optimal way of doing that, just like a swapping in any number, in any order, in any position index. You just diagnosed your own problem perfectly. It's the most important sentence you've had this problem session, the whole session. In DB backtracking, we don't care about all the input, we only care about part of it. This is exactly the skill you already have, and it works here identically. You just haven't spotted local frame yet. Let me hand it to you, because once you see it, the loss of numbers feeling disappears. The localization, you only ever look 2 digits. You only ever look at 2 digits. In recursion, Your local frame was current node plus carried state. Yes, yes, yes. So in recursion, this is the way how we do it. You never stare at the whole tree. Here's the same shape. In recursion backtracking, we like the one current thing, yeah, current node. In container problem, the two pointers, yes. Remove k digit, it is the incoming digit d. Alright. The summary pass, so carried arguments, yes. The site you kept, and here it is stack. Alright. What you ignore, the rest of tree, yes. Your recursion handles it basically, yes. Everything outside, yeah. Future digit, the loop feeds them one by one. Alright. I guess guys, like I can take a quick break. Let me uh let me go into break with 15 minutes, alright guys. Um 15 and yes. I haven't read it fully. But the thing I wonder is like maybe comparing two consecutive ones, we could just maybe use a swap method or something where we can just swapping any number in any index basically, because in heap for example we have this, or in some array problems we had this. So there must be a reason for us to compare the consecutive ones, or like of course I can understand the reason, but what I am asking is that more like there's a reason, there should be a reason why comparing consecutive ones is a correct way or is working for us. All right. So um yeah, could you please clarify? Maybe it may be because like we have a for loop basically, right? And using a for loop we need to you know evaluate or process each number at each index, right? But still, like, because if you use a single, like if you are gonna do this in single pass, right, then swap operation doesn't sound a good operation, right? Because you don't have a hash map or something, right? Maybe you can reach the elements from each index, but you are doing in single pass. So maybe that's why the consecutive option here, especially in this problem, maybe a little bit better than swapping, right? So there is a leading, there is a reason, there is a logic behind every step, and now I'm trying to understand those guys. So press enter. Welcome, welcome. What you are using for note taking? For note taking, I'm using like a, you mean the this notability app, or are you asking the tablet I'm using? It's a graphical tablet that I'm using, and it is Notability app. I really like drawing because I'm a visual learner, and I need to draw things, and I need to write things down, and this really helps actually. No, there is the other one. Oh, this one you mean? This is this app that like I created this app using cloud. This is a note application for you know taking notes using lots of images, and in each image I can have a voice note, and I can add some related images too. I'm using it for especially LeetCode because in this type of questions I need to you know take lots of screenshots, lots of voice notes. It is on my GitHub account, if you mean this application. This way, it is ordered and I can reach the node I'm looking for fast. I have tried using Obsidian, but it doesn't work for me. There I couldn't take, like when I paste an image, I don't see the relationship of it with the previous nodes. I wasn't able to paste, audios, and there is no tagging option for audios and images. But here, like I can I can make a search, for example, last assigned, which is let's say composition, all right, for example inheritance. So when I click on it, I can fetch all the images that I have pasted with this tag. So this helps me really. This way it is organized. I don't need to worry about a note that I have written 5 years ago. Let's say, all right, because I have tags, I have captions, I have colors. So yeah. So for this specific problem, cool. Thank you, thank you. It is on my GitHub. If you like, you can use it too there. Excellent question. This is the deepest why you have asked, and the answer cuts right to what kind of problem that is. Let me give you the real reason. Because your single pass, no hashmap gas is close in separate but wrong on the cows. Alright. The core reason This is a delayed problem, not a rearranged problem. All right. Actually, we can, we can take a screenshot because it seems helpful. Swap belongs to a different family. Oh, I see, I see. I see. Since we need to delete some numbers, basically we cannot use swap. Um, but I thought maybe alongside of deleting, we can we can do some swapping. But in this question, swapping is not the option, guys. Come on, swapping is not the option because after even deleting, let's say for 3 2, um the left, like the one is still on the leftmost, right? So the relative order is like they stay same. So that's why we cannot just use swap. Why did I thought swapping could be a method here too? I don't know. Like the structure we have here is literally like screaming us for using stack. But my second question was, why do we compare the consecutive ones, and also why not use swapping too? But now it is clear that swapping is not an option for us. But read problem statement. Alright, alright. So yes. A swap would be illegal here. I get it. We get it. Now, what consecutive actually means here? You have slightly mislabeled it. Let's see. You said comparing consecutive ones. Careful. The comparison is not like consecutive. Uh, it's stacked up or incoming digit. Stack adjacent. And another term that I really like, guys. Stack adjacent. Stack adjacent. Like that's a good term. Even let's make it, this one. So basically we're not uh, evaluating the consecutive ones, but the stack adjacent ones basically. So let's say we have this in our stack, and the event the incoming is 2. Compare 2 with 7. All right, and then pop 7. Compare 2 with 5. Are not input neighbors position. Yes. So you are comparing across the stack boundary, which can reach for back into the input. The point isn't neighbors in the string, it's the most recently kept digit versus one in my hand, guys. Oh my gosh, guys. Oh my machine there, guys. Let's paste it, and let's give some colors to it, guys. Let me give these 5 colors. So let's see. The most recently capped digit versus the one in my hand. Why comparing only that one boundary is enough? Here's the elegant part. The stack is always kept monotoic, non-decreasing. That invariant means every digit already buried in the stack is, oh yes. So like I have seen this logic before. I have I have like I have this logic before. I don't remember if it is. Oh, actually, it was in trees, guys. I suppose. Yes. In a tree problem. As we go one level deeper, we already know that our parents are, let's say, smaller than us, right? So that's the invariant. So they're already in a good order. No liability can hide inside the stack. Yes. Like this is. Yes, this is good. This is good. The only place evaluation can appear is right at the boundary, the top versus incoming. Um, so correcting your guess, you reasoned single pass, no hash map, so swap is awkward. That's why we use consecutive. Yes, flip the casualty. The reason is the subsequence constraint, delayed only. order frozen, swap forbidden. It is delayed only, order frozen, and swap forbidden. So that's swap forbidden. So therefore, so plus the monotonic stack invariant, only the boundary can violate. So a single pass is a gift that falls out of those two facts, not just the justification. Even with full random access and a hash map, swapping would still be the wrong tool. Yeah, so yeah, get it. So now what do I have as a question for this problem? We like first thing we have done is determining our overall goal, which is making the left making the leftmost part as small as possible. And then we have talked about stack, but the thing is how we connect these two. Like what is the implementation? Like I also like I understood the stack movement, but we like when we apply a for loop, we literally go from left to right. So it means that basically as we go from left to right, we basically add a number into our stack, like at the current number in our stack. And if it is larger than that, we keep adding. And as we hit a smaller number than the stack adjacent one, guys, like I really like the term stack adjacent one, then we like it is time for us to remove, all right, an element. So that means that, guys, k that like cannot be like any number, right? So like the value of k, I mean, should picked carefully. Like where is the so num consists of only integers. Num does not have any leading zeros. Like only constraint about k is this, but I mean, can it be like can there be a case where let's say k is 100, where the input size is quite low? Anyway, so that's the case. Maybe we can add the base case at the top, saying handling these cases. But I guess now we got the core idea with this question, right, guys? We've got the core idea. Moving on. So thank you. I guess we had the core idea. So now wrap up, generate the documents in a corresponding folder for this question. But like when we start thinking this, like when we understanding this question using stack, like when we apply stack, I really understand. But yeah, actually the question I had, guys, is I at least what I mean now was um, why do we compare the consecutive ones? But now we learned that we're not comparing the consecutive ones, but stack adjacent ones, right? That's the difference. So like I really like the idea. So now we're done with this question, guys. We can move on. Remove duplicate letters. I guess it is in again monotonic security. So like I've seen this type of question asked during an interview in Turkey. Yeah. So let's see, guys. Let's see. We need to get familiar with this subtype of query, right? Let's copy the. Let's take a trick. Oh my god. Let's take a screenshot. Yes. So and paste it over here and maybe even over there. Let's see, guys. Let's see. So now that we know we need to use a stack, it's a big advantage, all right? Because most of the time you don't even know which data structure or which technique you need to know you need to use. So remove duplicate letters A, B, C, and returns in smallest lexicographical order. So guys, what should we do? Remove duplicate. So maybe the first thing we should do is just starting the timer again. And so remove duplicate ladders. So we need to let's see guys, let's see. We are here, right? So maybe guys we can take one more screenshot and think about duplicate, right? Duplicates, if it is a word. So duplicate rule, duplicate rule. So apparently, guys, we are getting rid of these two, right? But why? So let's see, we have B, so we add B. And we have C, let's add it 2. Let's add A2. So since they are distinct characters, we do not have any issue with them. Everything is just fine and we are happy. As we hit, like as we add B over here, then now everything falls apart and we are sad, right? This is just terrible. It's like a flower with this. All right, this is sad. This is sad. So what happens? Hungry Hippo. Have you heard of the Google Chrome extension Let Rooms? No, I haven't. Let Rooms. What is that? Lead Rooms. Chrome extension. What is that? Multiplayer rooms to LeetCode and the extension adds another panel. Oh, that seems fine. Actually, we have kind of similar stuff in, I don't know, here. You can join and, you know, uh, you can live code basically. And I can see all of your codes. It is synchronized. It is live. We already have this kind of, yeah. But I wonder how it handles. Like, is it, synchronized? We can try this out. We can give it a try. Thank you for sharing. Um, but like currently, I like maybe after like completing this greedy, maybe maybe we can try that sort of thing. Like because I don't know how would I solve this, you know, without pencil, without a pencil. So um, even even with pencil, it is still hard. So like yeah, from what I understand, you can look at each other's code, which would be interesting to see how other people do it. Yeah, yeah. I don't know why LeetCode doesn't have that built in. Yeah, yeah. Like LeetCode is an old website, and like I mean, it is there for a long time. It would be great if it has it. So what should we do here, guys? What happens as we add B? So we are having basically we are having duplicate and two, like we can create a detection system to understand if we have a duplicate, which like the structure we use is like using an array. And if like we can create an if we have like if it is bigger than or equal to 1, then this means duplicate. So but then what would we do? What would we be doing? What would we be doing? So we need to actually, guys, look at this output, that I mean the return value. Look at the order. We need that. So there is something about the order over here. And maybe it is because I mean Like, is it because we removed that part and used this? Or like, what I mean is that, like, if the input was like a c b, would the output be, I mean, like a c b? Would it be like that? Maybe first we should understand it, guys. Maybe we can just take a screenshot and see. We have duplicates like a C over here, there, and there, and there. So we should we can look at the last occurrence. I mean, we have B here and B here. So apparently this B will be, no. We have C over, like, why do we have B over here, guys? I thought we will have something like that, like a B C and then D and then A. I didn't understand the question. Given a string S, remove duplicate ladders so that every ladder appears once and only once. You must make sure your result is the smallest in lexical or among all possible results. But the thing I don't understand with this example is it is not A, B, C, D. Because no. We could put A in the beginning because after C and B we have other occurrences. Like we have C over here and B over here. So we can easily get rid of them because we have reoccurrences, right? But we don't when we don't have any reoccurrences, the position stays same. And look at this C. We have still another occurrence later so that we remove that one too, right? And how about D? So D, oh my gosh, now this should be there. Actually, yes, A, D, yes, yes. No, the output is A, C, D, B. Why? A, C. I don't understand, guys. Like, we like if it was A, B, C, D, then I would say okay. But like we have D over here and B over there. So like our goal, forget about this ordering issue. Our goal is basically remove the duplicates, right? And the question I have is like should this D be in the same position, I mean, right? Let's say it has to be, right? So we need to remove duplicates. But which duplicates? For example, we have here C and here and here and here. So which one? So based on the previous question that we have solved, maybe let's have some stack or something. And as we like since we iterating, let's add C, all right, and let's add B, and B is smaller, right? Maybe we can solve this in two pass. In the first pass we can create the occurrences array so that when something comes from like comes smaller, all right, Instead of adding it, we don't add basically, right? But if there is only one occurrence, we should add it there. So that's what I'm talking about. So maybe we need two pass. So um let's see guys, let's see. I don't wanna 10 minutes is enough. So now I want to focus on this problem, and the solution I came up with, like we came up with, is like a maybe two pass. In the first pass, we can create an array and store the occurrences of characters, and the second pass we can create a stack, right? And like based on the previous question that we have solved, like this is what I have, like this is what we have, you know, came up with. So as we iterate from left to right in the original input, we can add a character in our stack. And as if we see a number like a smaller, like in Lexo order, we just don't add it, right? But we can do this move only if we have another occurrences. So we have seen, like I don't understand because now maybe we should try some like in reverse order, and maybe as we add items to stack, that should increase, right? I don't understand. I don't understand. Guide us. Like I tried increasing or decreasing, but it didn't work. Like how should we use stack over here in this example, and why even bother using it? Because there must be a reason to use it, right? Like the reason should lie in the Lexo order, because removing duplicate is not a hard job. We can just store them and decrease the occurrences and recreate the output, but output should be in a certain order. Like the thing I'm trying to say is that I don't see any reason why we just don't um you know remove the duplicates right away and recreate it. But I guess it is about um lexicographical lexic lexicographical order, right? Let's see. So you are closer than you think. Here's the first thing you fix to fix. You keep saying two pass like it's array or stack. It's not. It is array and stack. Two tools doing two different jobs at the same time. Oh my gosh, guys. I like only question I know like this one where we use like two data structures is LRU cache. All right. Here we are using like a double linked list as well as hash map. I mean, I guess this will be the second one. Is array and stack two tools doing two different jobs at the same time. Once you see which job each does, your confusion dissolves. Let me guide you there. Start from what you already own. This is remove k digit skeleton. Same family, monotonic stack. The core loop is identical. Left to right, keep a stack. When the top is bigger than incoming, top is bigger than incoming. Let's say the C top is bigger than incoming. Yes, which is that. You want to pop the bigger ladder so a smaller one lands more to the left. You want to pop the bigger ladder. Bigger ladder. Which bigger ladder? This one? Your instinct, the stack should increase the monotonic invariant. Correct. So far, yeah. So now, key question. What does didn't have? In remove K digits, your license to pop was a budget. Pop freely until the budget runs out. Deleting was the goal. Here, every letter appears once and only once. Every distinct letter must survive in the output. So instead of having a budget, now we need like we have a rule that we can apply on each letter basically. Question one. This is the crux. So sit with it. In remove K digits, you could pop any digit you like. Not exactly, but in remove K digits, you could pop any digit you like. Here, suppose like I didn't like this analogy, but let's continue. Suppose the top of your stack is C, a smaller ladder arrives, you pop C. So guys, instead of heading A, or not adding A when we hit C, we just like when we face, when we like when the incoming character is smaller than the top, all right? We pop, but do we add A here too? And you pop C, but C never appears again in the rest of the string. So what just went wrong? And why was this impossible to go wrong in the previous question? In the previous question, you'll see it, you'd have destroyed only C, yes, and the output now can't contain C. In previous question, deleting was fine. Here, every letter is mandatory. So that question answers your only if another occurrence instinct. You were right. Oh, that's nice, guys. So you said we can do this move only if we have another occurrence. Yes, yeah. So pop the top only if top bigger than incoming and the top letter appears again later. So it will come back. Question two. How do you know? How do you know while standing at position I whether C appears later without looking ahead or reversing the string? This kills your maybe reverse order worry. You don't need reverse. You need to know the future count of each letter. So what's the cheapest way to have that ready before you even start the main loop? So it is talking about pre-pass. And then what like actually we have mentioned this, right? We literally mentioned about first pass and second pass because we literally need to know if that number occurs in the future or not. So basically we have the fundamentals, right? Foundation. But maybe the remaining part is how do we get this part exactly? In this order. Most probably again the text solves it, I suppose. And one thing to remember is that like instead of adding a smaller character, we basically pop and then maybe add, right? So when A comes after C, we basically pop C and then add A. So so that is your array of occurrences. Yes. So now you see its job. The stack does the popping. The count array licenses each pop. Yes, so like look at the verb. Um, yeah, verb it uses. So two tools, two jobs working together. So that's nice. One more rule, one more new rule. Each letter exactly once. Yeah. So question three. Incoming letter is B, and B is already sitting in your stack. Do you push it again or use the constraint one? So maybe guys, we should have another array for knowing which numbers or characters we have in our stack, right? Imagine we have like a lots of characters, right? Lots of characters. C B A minus A minus B, all right? Um, like let's say, oh, if if we hit B again, but there can't be any character between these same character, right? Or can there be? Incoming letter B, and B is already sitting in your stack, like sitting on the top of the stack, right? Do you push it again? Um, we must you like what must you do instead? And what tiny piece of bookkeeping do you need so you can answer? Is it already in the stack? Like I imagined using an array, but and then I thought, you know, since they are consecutive or like only way for them to occur is this way, so a consecutive way. So maybe if maybe we even don't need to have an array. So your three reasoning tasks. What breaks if you blindly reuse popping here? How to know appears later without reversing? And also for your second and the third questions, like for the second question, we have an array where we hold the frequencies, right? And for the third question, um, to know that the incoming ladder is already in the stack, but the thing is, we told that, I mean, we thought that, I mean, in our stack, like you know, characters are in decreasing order, right? So if we hit a character that reoccurs, it can, like there is only one way and it is consecutive. So the incoming character and stack character on the top of the stack and the incoming character should be same for this case to exist, right? Let's see, guys. Let's see. Um, let's see. Let's see. Let's see. Like how many minutes? It's been 23, I guess. So here stack will help. And now the beauty of this question is that we can use basically not one but multiple data structures. I don't like this one, kind of confusing. So like this is about stack and using an array for holding the occurrence like a frequency. Um, basically yes. But the way we build our stack is kind of matters, right? Let's see. Let's see. For example, let's say B and C. So let's say we have B in our stack, and when we try to add C, uh, it is bigger than B, so we should pop B actually, right? Pop B and it's C. And or was it when we find a smaller character? When should we pop? This one feels like it is easy to understand but hard to implement. Actually, for me, it is like implementation, like as like when you understand the core logic, I don't see um, implementation becomes hard because logic is hard for me. I don't have issue with implementation mostly. Let's see. Thank you for the explanation, but I didn't read what you have just written. But the question I have is like I tried to create the stack and I thought like should I, you know, pop when a bigger character comes like the incoming character is bigger than the top character on our stack, or should we pop when a smaller character comes? So because I don't have any reason to distinguish them, right? Could you please clarify it? So actually, I'm not even sure if I understand. I'm like I don't know, maybe 40-50% I understand. So let's see. Um, three things to tangle here. Like I understood the previous question. All right, remove k digits. Maybe that's because why you didn't understand, right? Here in this question, we were adding numbers into our stack, and when we see something bigger than us, we basically not add it basically. No, we add like here in this question. Like, have you solved this question? Remove k digits. Were you here? Like here, we have a stack, and we iterate through numbers from left to right, and we add numbers if they are bigger. Like if the incoming number is bigger than the stack, we add it. All right. When we hit something smaller than our stack, we basically um we basically don't add it actually, right? Or do we very popping? I guess we were popping, right? Which means like this one, popping the top and then adding it. And as we add another number, which is again smaller than the top, then we pop the top and add it here at the incoming here. And again, we hit a smaller, then we pop it and put it here, and then we have this. So I guess this is the answer, right? Let's see. Yes, this is the answer. The longer I look at it, the more I'm confused. Yeah, I did the digits one was much easier. Actually, yes. Like, yeah. But the first time I've seen the previous question, it was hard still. Like, this question was hard as well. But as soon as I, see how we, you know, use stack and how we pop, it became easy. But here with this problem, like again we have something like similar, quite similar, right? um we can still see characters as numbers, right? Now we need to build the logic, you know mm, when to pop basically. Three things to untangle here. You nailed two of them, and the third has a subtle bug in your heart. So point one, why not just remove duplicates right away? Yes, it's a lexicographic order. You answered your own question. Watch why nailed the duplication fails on example one. So if we remove all the duplicates, keep the first copy of each letter. Keep the first copy of each letter. It becomes BCA, and the correct answer is ABC. So we need to do something about order as well. The lexicographical order part is what threw me off. Like we need to put this, smaller number in front. Like it is like 1, 2, 3. Like it is like BCA 2, 3, 1, but we need to make it like a 1, 2, 3 basically. So if you think them as like a numbers, right? Think this as numbers. Take this as numbers. So sometimes you must throw away an early copy of a letter and keep a later one. So a smaller letter can move further left. So should I keep this copy or future one is the entire problem. Exactly why a stack with popping is needed, not a one-shot duplication. So yes, so this was a good question. Why we just can't use you know the duplication right away, but the order matters. And even in the order, the decision we make is like a throwing away an early copy of a letter and keep a later one, so a smaller letter can move further left. So basically we remove BC here. I was thinking alphabetical order, but Hungry Hippo, I was thinking alphabetical order too. Is there a difference between alphabetical and lexicographic order? And also, my amazing engineer friend Hippo told me that, uh, like, he told me something about alphabetical order, and I assumed, like, um, this lexicographical order is, you know, something same with alphabetical order, isn't it? Like, it should be same. You said like a ACDB confusion. So it is about the stack basically. Actually, that confused me too. That confused me too. Yes, yes, yes. I think yes. Yeah, you're right. You're right. So perfect. Let's strip everything as away and nail justice. Thank you, Hippo. You made me realize that, like, in the question, yes, that confused me too. But somehow I forgot that part and assuming it is alphabetical. So pop when a smaller character comes. About the part. Hippo is right. For lowercase letters, they are the same ordering. Smallest in lexicographical order comes first in the dictionary. The only nuance, lexicographic is the general rule for comparing whole strings. Comparing position 1, tie position 2, and so on. Exactly like a dictionary. But when you are comparing individual letters, it's plain alphabetical. So trust Hippo. um so oh, I see. Like did you understand, Hippo? I guess now I understand it. So we only need to compare two characters. We don't care about the alphabetical order or of A, C, D, B. All right, we don't do that. Only thing we do is like a making like a comparisons. All right, like making comparisons, and based on that we decide popping, putting. All right, and like this is the decision we do. We don't care about the word. I didn't get 100% myself. had to get help with the yeah, like if you understand this part, you understood. You will understand. We do the alphabetical comparison part only comparing two characters. Like this is what I understood. We don't care about the overall words order or value. We only do comparison between two characters, and we pop and then um add numbers. Yeah, we'll see. Let's strip everything else away. It's the heart of the whole. Pop when a smaller character comes. Let's see why we should pop when a smaller character comes. So basically, let's say we have C in our stack, and when a smaller character comes in, we basically um, pop C and add A, right? Here's the reason you said you are missing. Your goal is the smallest result, and smaller letters want to be as far left as possible. Leftmost position dominates. So when we have B in our stack and incoming A is smaller than B. So our goal here, guys, like a putting like a smaller character, like let's say a minus 100, minus 80 minus. So our goal is keeping lowest one at the low bottom, right? Yes, I guess it is correct, but let's give the example with like these numbers. Let's say 10 minus 9 and 8. If we have a number 1, then this should go down, which means on left, right? The ABC part I didn't understand because I missed the part about keeping relative order of the room. Like we will understand, guys. We will understand, Hippo. We will understand. A is smaller than top B. So keep as is. B then A. Incoming is smaller than top. Your goal is the smallest result. Yeah. Stack B, incoming A is smaller than top B. Pop the B, put A first. Popping the bigger top was the right move. So, alright. So imagine in our stack we have okay 8, 9, and 10. And when we pop and create our string, we will have 8, 9, and 10, and it is small. That's why we want smaller order. And when we have something bigger, we pop this because otherwise we would add this high number at the beginning. So we don't do that. We don't want that. So we basically sacrifice basically 8 over here and put 20 over here, right? I don't understand. So pop when a smaller character comes. Oh, like all right, this is wrong basically. Yes, because that didn't work. Let's see. Um, let's say we have 10, and when 9 comes, we don't want that. We pop 10 and 9 too, and then like if we do this, if we have If we have 10 later, right? Let's say 10 is here. And when we pop, again 10 and 10 will like again this will be like this. Like let's see. In stack we have B incoming A is smaller than top B. Pop B, put A first. I don't understand. So now the other direction. Stack A, stack we have A, incoming B. B is bigger than top A. Keep as is. Already smallest. The small letter is already on the left. No reason to pop. Just push B after A. I need to understand this part. This explains the stack logic. This explains it. Let's say in stack we have B, right? And incoming A is smaller than top B, yes. Keep as is, B then A. Pop B, put A first. Like, I don't understand what is written here, guys. So the rule, yeah, so pop while top is bigger than incoming. That's the asymmetry you couldn't find. It comes entirely from smaller letter earlier, smaller number. So the stack ends up increasing. Small at the bottom, big on top. So we want our stack to be like in increasing order, I think. We have this. We want this like we want it to be like this. You already know this rule. It is identical to remove k digit. Yes. It is kinda hot here, guys. Let me run the fan. Oh my gosh, guys, I could use a break right now actually. But I like after we come, I want to understand this uh stack part. How do we like how do we create our stack and how do we pop, and at the end what do we do with the last version of stack? Thank you, Hippo. Let me see brain power. Yes. Like even taking a short breaks like a 10 minutes 15 minutes, they are quite helpful to refresh, you know, because I want to understand it but I don't feel I don't feel like I have enough energy to understand how we structure this stack. Like I always have an urge to nap. Like actually if I wasn't if I weren't streaming I would definitely sleep a couple of hours for sure. Like but I'm pushing myself. So thank you Hippo. So like after the break we'll try understanding how we set up this stack. Like I heard sleeping after learning how to retain. Yeah. So so solve one LeetCode, sleep and repeat. Actually, yeah. Like, but like this is a good way. And also, if you don't watch any Instagram, YouTube, like a ridiculous stuff, uh, like if you only study and sleep, that's an amazing way to learn. Yeah. So because even in your sleep, your brain creates your neural connections and you capture the ideas even while sleeping. Yes, I totally agree with you. Also, fast way to burn out. Yeah, yeah. So like you need to find the balance. Yeah, yeah. Definitely, definitely. I hope I don't get, burnout. Let's see, guys. I'm quite glad, I'm glad you are here, guys. So like I like existence of yours makes me, motivated very much. So thank you. I appreciated it. I got I got really burned out. So like after the break, we're gonna feel better, right? Like the idea is simple, all right? Like it is either like a big number to smaller, right? Like this is the correct way. And let's say when we see a number bigger than us, I mean this is incoming, all right? Like let's say this is incoming, all right? If it is incoming number is bigger than the top, we pop it and push the incoming one, right? So like this is one way. Like I don't know which way we should use in this problem, but this is one way, I suppose. And the second way is like we create in like in increasing order, like we try to create a stack in increasing order, and let's say when we when the incoming number is smaller than the top, we pop and push the incoming there. So we have two, like these are the two possible ways, I suppose, but we need to understand. But can you take a break without thinking about this problem? i'm trying to I'm trying not to think about it. All right, I'm trying not to think about it. And I also do some exercises, and like I had a quick breakfast in the morning, but now I'm gonna have another. I'm gonna have the second breakfast. So maybe we can take a 20. Maybe it should like maybe 25 would be great. Like second breakfast. Yes, yes. Like I love breakfast. I just love breakfast. Like they make me motivated too. They make me happy if the breakfast is good. I like black tea, bread. But like the first breakfast I had was yogurt and olive meal. So thank you for the follow. Hi Perion RTA. Thank you for the follow. Welcome in. And now I'm gonna have a proper breakfast where like I have eggs, olives, bread, and black tea. Uh, hello, welcome in. How are you? We are trying to solve this monostack greedy problem, but I got a little bit tired. Now we are about to take a quick break. I'm good. I'm good. And you? I'm doing great too. Thank you for asking. I feel a little bit tired. I just want to take a break, and after the break, I just want to solve this question, which is about stack eggs and shakushka or bread with olive oil sound good. Yeah, like they sound good. They sound good. Let's see what we have. Like after this question, we can continue with the I guess teal one. Heap based greedy. Oh my gosh. Retroactive event scheduling. Hippo, what do you say about this guy, man? What do you say about retroactive event scheduling? Do you think that we can handle this? Do you think we can handle this? Like, I say good luck. No, man, no. You're gonna be here. You're gonna stay, guys. Guys, all of you. You're gonna stay here and watch me suffering. All right? No. Like that shouldn't be that hard. That shouldn't be that hard, guys. Come on. Retroactive event scheduling sounds cool, guys, doesn't it? Oh my gosh. Let's look at furthest building you can reach. Oh, let's see. Like what? What kind of question is this, guys? Let's see the question first and then take a break, guys. God, please help us. Like we have an animation. Like we have it, even an animation, guys. Come on, look at it. Do you understand, guys? We have Einstein and a girl, a woman, I think. And as we climb, we become Einstein and solve some, equations about the universe. I only have more questions. What is your favorite programming language? I guess it is Java. Yeah, I may say Java because like we learn Java in college, and it is my first language. I learned object-oriented programming there, so yeah, yeah, yeah. So, um, like you are given an integer array representing heights of buildings, some bricks and some ladders. You start your journey from building zero and move to the next building by possibly using bricks or ladders. While moving from building I to building like a consecutive, like a neighbor, if the current building's height is greater than or equal to next building height, you do not need to ladder or brick. Yes, that doesn't seem like a hard question, guys. If the current building's height is less than the next building height, you can either use like a one ladder or the difference, yeah, bricks, or one ladder or bricks. Return the furthest building you can reach if you use the given ladders and bricks optimally. So we need to make a choice between to use either to use one ladder or bricks. But how much bricks we have? We have 5 bricks. Hmm. Um. So I think one ladder solves us solves our problem to go to the next higher building. So we don't need to care about the height difference. So this is quite valuable. So this, like for example, this may mean, I mean, like we may count this as for, let's say, maybe 120 or 1 million bricks, because if say our current height is 1 and the next building is a 1 million, we could use a ladder and we could go there. But if we use bricks, we would have to use, I don't know, like a 9,000, 900,000. I don't know. I do mostly Python programming, also many other, but I'm more like a cybersecurity guy. That's nice. That's nice. Cybersecurity is like, it sounds cool, but I don't know that much. Python, like in this channel, we are learning Python too. In one day we saw LeetCode, and another we study and create some projects in Java, and the other day we study Python and building projects. So our schedule is kind of like this. So we are learning Python too. Nice, 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 nice. Um, so guys, I don't know. Like this is literally a good question we should learn, and this is about retroactive event scheduling, I guess, right? Yes, yes. Uh let's see the hint. Min heap of climbed gaps, ladders to top K, bricks for the rest. So this is the answer, guys. One, the project part is more, yeah, yeah. Min heap. Oh my gosh. I wouldn't say like I would use heap here. I don't know, guys. Like we can give this question to AI and make the AI as teacher and judge it. Because even understanding what AI, like the explanation that AI gives is kind of hard. So now we're taking like a 25 minutes break, guys. I'm gonna have my second breakfast. I'm gonna exercise a bit and come back. And when I'm come back, guys, we're gonna continue with this beautiful, amazing stack question, and then this we're gonna solve retroactive event scheduling. All right. Actually, it is either retroactive or event scheduling. It is most probably retroactive. So we're going to continue with retroactive subtype greedy problem, which is furthest building you can reach. All right. Take care, guys. I'm setting these as 25. All right. See you after the break. Yeah, I guess it is. All right. Hello, welcome back, guys. How are you doing? I just had my breakfast, like I just had my second breakfast for today. Feeling much better, much energetic right now. And now we're gonna tackle this problem right now, guys. This is this is gonna be end for it, all right? So, um when we before we take a break, we talk about the structure. I mean, how can we formulate this stack? And like it is either like a decreasing way or increasing way most of the time, right? Because this is the way how we basically use stacks, right? And let me, the song is also better good, right? So yes, I think you can hear it too. So now let's try understanding it, and let me also resume the Pomodoro. That's awesome. So now AI said that like pop while top is greater than incoming. Um, let's throw it. Pop while top is greater than incoming. Top is greater than incoming. So when we find something smaller than our top, we pop basically, right? A smaller letter just arrived. So when a smaller letter just arrived, we pop. A smaller newcomer evicts the bigger letters sitting to its left. Sitting to its left. So left meaning, guys, here left meaning down, right? Left meaning is down. So um the question we have was this one, right? So no, not this one. The second. All right. So our goal is to find A, B, C, I think. Especially this example two is what makes us, a little bit confused. So like let's try building this stack, right? This is the best way. This is the best way. Come on. Oh my gosh. Now the app app stopped working. So let me restart it, alright? Sometime it does this, and I just need to restart it. So we're gonna build that stack, and then we're gonna like understand it. All right. Let's see. Let's see. Which page? We have a lot of pages over here. If I paste it, yes. So now we have it. So let's say we have our stack right here, right? And let's see, we put C, right? And let's so and then when B is incoming, right? So we should evict the top basically, right? And put the B here. And why do we do that? Because I don't know. Let's see. Let's see what will we have. What will have. What will we have? Um, let's say we evict C and put B. All right. And A is smaller than B, so we evict B again and put A here. And then we see, like we have C, which is bigger than A, which is all right. And then D, which is all right. And then we see C again. So we should evict or pop the top, right? Pop the top. But we don't have any occurrences of the remaining, right? So maybe this is where we just cannot evict, all right? But then what? And then what? So We have C, B, C remaining. Hmm. So like as we have now like A, C, D, like this resembles to this part, but for the remaining part, I don't know what to do. So maybe we can just um, ask AI about this condition. So that's the asymmetry you couldn't find. It comes entirely from smaller ladder earlier, meaning smaller number. The stack ends up increasing. So stack ends up increasing. Yes. So our goal is to make stack increasing. To make it increasing, when we have something smaller than us, like smaller than top, we just evict the top. Since yes, we since we want to have bigger number, when we have smaller number, we pop and push the incoming there. But the remaining question now is what should we do with these, not like with these letters, with these characters, right? What should we do about them? But this is the question I have remaining. Um, so in the previous question you popped, yeah. So hippo is right. Lexicographical is similar to alphabetical. Alright, so thank you for the explanation. Now the thing I wonder, like the thing we wonder is that, like for this example, all right, for this example, like I didn't understand like how we build our stack. Like I understand the part where when incoming is smaller than the top, we evict the top and push the incoming to our stack. Like this part I understood. All right. Until we have like until we add D. All right. We add D, like we push D in our stack into our stack, and then we have now C, B, and C remaining. What should we do with them? Right? Because until adding D, like we could apply your logic, like evicting the top and pushing the incoming when you find a smaller, like when the incoming is smaller. Like I totally get this logic. But what about the remaining parts? I mean, yeah, so explain, clarify, please clarify. So let's see how it will answer this part. So like after after accepting that our stack should be in increasing order, now it is clear, it is more clear. But the thing is, what should we do with the remaining, like these letters, these characters, right? Because we can generate actually, and another question I have is like, how do we exactly generate this one? Like because in stack, we can just pop, all right? Should we put the popped element in the beginning? But in that case, we have the reversed version. So the next question I have is, how do we exactly generate this from the stack? Like adding into a stack is something, but popping and generating what you need from stack is something else. Let's see. You stop exactly at the most instruct in, instructive moment. All right. The part after D is where two new guards finally earn their keep. Pure epic logic alone would give the wrong answer here. Let me walk the tail. First, here's where you are. Frequencies precounted. Yes, so like here we have like we like iterated once in our characters in our list, let me say, and now we have the frequencies. We need it. We need this information to decide if it is okay to evict or not. All right. Because if we don't have the recurrences of that character, then we just can't do it. All right. We should accept and move on basically. So decremented as we pass each character. Yes. So it's a tag. We have A, C, ACD. Remaining input is CBC. So remaining counts, we have, yeah, two number of C's. One B is 0A, 0D. A and D will never appear again. So now the three remaining characters at one at a time. C position 5 already in stack. So now we need a structure where we can immediately understand if we have something in our stack or not. So in our first pass, we create our frequency array so that we now now we know um, if a character appears multiple times, and as we evict from our stack, we know that that character will appear again, so we are safe to evict. um but here we should also know if a character is in our stack or not. So the rule, each ladder once means you don't push a second one. Yes, so you also don't pop anything for it. So the C you have is already placed. Do nothing we want. So basically, guys, oh my gosh, why I need to. So if I put this here, hmm, let me make it this way. So so we have a structure basically, and it tells us we already have placed a C. But what about B? We don't have B. So but what will happen if we place B here? Because it breaks our rule of incoming being have to bigger than the top. So this breaks our rule. But for C at least, so we have like a C, B, C remaining. We understood the C part. Since we have C in our stack, we don't like we basically mask it and we don't use it. But for B, this breaks our rule. Let's see what will happen. Like what will we do? B is not in the stack, so consider it. Consider it. So top is the B is smaller than this, so your evict instinct screams pop D yes, put B earlier, get a small thing. But the check guard before popping. So can D come back? Can D come back? No. Yes, so no, because we don't have it. We don't have the occurrence of it left. So never mind. So if you put it down, it would be it will be gone forever. So the answer is required to contain D. So you are forbidden from evicting it. You are forced to keep D. Yes, like this is the word I'm looking for. Like you are forced because that there is a rule, but we like although we have that rule, we still keep going. You are forced to keep D and just append B after it. So your stack, so the array, like array kind of representation of our stack is ACDB, right? All right, so the left part is A, C, D, and B. All right, so all right, like as if we put stack like this, we can imagine it like that. A, C, D, and B. All right, all right. Why? It is because I think so. So now, like I think now we can answer my second question. My second question was, how do we exactly generate this? So basically, we generate it by like a popping character to the rightmost side, not the leftmost side. All right, because the order is matter here as well. All right. So C position 7 already in stack. Yes, yes, yes. And the takeaway for what about the remaining parts? After the evict logic didn't disappear, it got gated by two guards. So after D, it got gated by two guards. So um yeah, we skip it. We skip C's, and for B, we forced to push. Yes. So drop evict rule. You already mastered still. Yeah, yeah, yeah. Never evict later that you. Yes, yes, yes. That second guard is precisely what makes the final stack stop being strictly increasing. So I think this answers. I think I can maybe uh, make this. So I think this is an answer for your question, Ipo. This is answer for your question. I mean, now it should be clear how we end up creating this kind of output basically. So this is how we created this output. Which question? like like the question, like the stack monostack question, Hippo. This one. We used our stack and we made it increasing order. And as we have a smaller incoming um smaller incoming than top, we just evict the top and push the incoming. And when we have like a greater one, we just keep adding it. And when we have like a, oh yeah, I managed to figure it out, but it took a while. All right. And so when we hit like a some reoccurrence character, if we have it in our stack, we just don't add it anymore into our stack. So that's how we basically crash the duplication, right? But for that we need to have a system where it will tell us if we have that item in our stack or not. We need a structure, right, for that. um all right, basically our stack is in increasing order. When we have something smaller, we evict, push that. And we do this eviction if we have reoccurrence of that character basically. Because if we don't, we just forced to add the B. Like we are forced to add that character into our stack basically, right? Um yeah, so like ACDB. So our goal is to make our leftmost smaller. So we want smaller one in the beginning, like at the bottom of our stack basically. When it is in increasing order, there is no problem. But let's say um, we have A here, so it should be on the left side. So we are, let's say we have another B, all right? So when we have something smaller than us, we just evict and push A here. So this is the way how we do it exactly. But the thing I wonder is, like, let me draw it again. So we have like we pushed C, but when B comes, we evict it and put B here. And then A comes, and A is again smaller, we evict B and put A. That is good. So basically, but for it to be happen, I mean, like they should like D E. I mean not D F. I mean F E D, right? And C V. So I mean they should be consecutive to work, right? This is what I mean. But if we have like an E over here, then E will be there, right? Hmm. I mean, are we guaranteed to have A in the left side, in leftmost side. Let's see a like a's let's see, let's assume a's position is different, right? Let's say a's position different. What would happen there then? Let's say um let's say a is here, right? I wonder what happened. Okay, c b c d a b c. So oh my gosh. All right. Um, let's create a stack. We push C, and we have now B is incoming, and it is smaller. We evict C, we put B, and again we have C, which is greater. All right, and then we have D, which is greater. It is okay. Um, and then A again, but we don't have the reoccurrence, so we are forced to add A basically, and then B and then C. So basically B, C, D, A, B, C. So we're gonna have this. So A is not in the front, but should it? I guess not. Let's see what AI will tell us. I mean, if this is the input. Oh my gosh, it's been 20 minutes. Um, can you please solve this and show us the output? And after that, now we're gonna start that amazing question, guys, where we have Einstein and some letters, some bricks. Um, that's gonna be fun, guys, with Einstein. Let's see. I think we have done this correctly. And our next question is this furthest building you can reach. Like again, we have some decisions to make here. We need to find some greedy approach, like a finding local decisions that will, solve the overall problem as well. Come on. So, oh my gosh, the up to this BCDA. So we didn't remove the recurrence one. Sorry guys, let me think about it again. Um, like we have reoccurrences, right? Like we have B. sorry. Let me try it again. Like we should do it correctly. So we have our stack, right? And let's see. C, we have C three times, B two times, D one, and A one, I think, right? So we put C, and when we have B, we evict C and put B, right? All right, we've done it. And C is alright because we want increasing stack. C is alright. And then D, which is again alright. And then A, which is again alright, right? Yes, because we don't have the reoccurrences, another A. And for the remaining part, guys, we just don't add it because we already have them. I forgot to applying the, have that condition. So we just don't add this part because we already have them in our stack. So basically, our answer is B, C, D, A, right? B, C, D, A. Yes, B, C, D, A. All right, so now create like a wrap up and create our documentation and save our process like a thought process. Thank you. So for the next question, guys, we have. Oh my gosh. Let's take a screenshot and think about it, guys. This is gonna be fun, guys. Look at it. Like, what a fun question, right? Let me take a screenshot. So, if the current building's height is if the current building's height is greater or equal than the next one, like imagine we have a smaller building next to us, um you do not need to ladder. All right, this is good, this is a good case. Like we don't need to, like there is one abyss choice, we don't do anything, just an if case, like an if statement, and we're done, we're okay with it. So if the current building's height is smaller or less than, not smaller, less than next the next building's height, in this case we have two options, guys. We have two options. You can either use one ladder or the difference of height, not like this amount of bricks, which is the difference of these heights, one ladder or height. All right, let's see. We can restart, I guess. All right, so I guess we have the remaining part. Return what? Return the furthest building index. So we want to go further, like furthest, as further as possible, as far as possible. So we have some constraint. Obviously we have, like, our constraints are bricks and ladders. Let's see the example 3, because it is relatively easy example. We have bricks and ladders. Actually the decision is that when to use ladder and when to use bricks, right? Maybe the proper example is example 2, right? Options: bricks, ladders. So obviously a ladder is far more valuable than bricks, apparently. And let's say we have 4, oh my gosh, like, do I need to throw everything? 4, 12, 2, 7, 3, 18, 20, and then again 3, and then 19, I think. Oh my gosh. So as we have like a greater or taller building, right? When height is greater, look at the difference. The difference is 8, so we need to use 8. So we basically compare the consecutive ones, which is all right. For example, here we need 8, here we don't need anything, here we need 5. 5 bricks, and here we don't need it. Here we need 15. So actually our goal should be like use ladders for the highest difference, for the highest difference neighbors, basically. But how? But how? Like, again, I think we're gonna go in one pass, or and right. Or maybe in 2 pass. What do you say, guys? Do we need 2 pass? Like, only thing I think is like a running state, right? Which is pre-order. Like, this is what I no, which is post order, by the way. No, it can be pre-order, post order. Let's call it pre-order, because there is a history coming up to current index. So this is the idea that I'm familiar with. But here, to be honest, like, the idea is like it would be better if we use like the core logic will, if core logic is this, and our answer should be built upon this idea. We need to use ladders for the highest difference neighbors. All right. For example, here we need to use ladder here, but the thing is, we don't know if our bricks will be enough or not. Oh my gosh. So let me explain this to AI. So like we don't know, like, because if we just if we just wait for the correct moment, correct perfect moment, we may end up with not reaching that moment at all right. So we need to find the balance. So I guess this is why it is called retro restrict. I don't know. Let's look at it. um retroactive. Oh my gosh, not retrospective. Retroactive. mm, Retroactive. Let's see. Yeah, first let's take a screenshot. So we understood the question. Now we need to come up with some solution ideas. So now we started solving this question, and the idea with this question is that the ladders are quite, valuable or invaluable, like quite important, right, for us, because it maybe instead of being having you have to use 100 bricks, we can just use one ladder. Like it is too much valuable. Now, but the thing is, like we should obviously use ladder where bricks are needed most. All right. Let's say there's a place where like a 20 bricks needed, and where there is a need for, let's say, 100 bricks. So we need to use these ladders, um, um, you know, for those places, right? For those places. Um, but the thing is, that place can be or could be, very far away, so that it is not even possible for us to reach that moment, right? That place. So we need to find the balance for it, and I don't know how to do it, right? And obviously, for the neighbors where the next building is shorter than us, smaller than us, less than us, we don't need to use anything. So that's all right. We can just skip it basically, right? We don't need to do anything. There is one abuse option. We can just add an if statement, and all our problem is done, solved. But here, like, I mean, for cases where the next building's height is greater than the current building, now this is where we need to make a choice. And for greedy problems, I have learned that we need to think about the local maxima, I guess, or local minima, right? And for greedy problems, applying this local analogy, local approach will give will solve the overall problem for us. Let's see. Come on, transcribe. Come on. So, and the thing we know about like a pre-order or post-order recursion, like we have like in reverse linked list problem, we delegate our problem to our next node basically. And when that like a func node dot next returns, we expect it to handle and reverse all the remaining nodes. And for in-house rubber problem, we define our problem using the sub problems, and we have two choices here. And based on these two choices, we create our maximization formulation, or the definition of um, the index I at index I.
like a func I, all right? Our problem is solving func I. So basically we define func I using the subproblem, which is, one is getting the value and delegating the subproblem to I minus one. This is one option. And our second option is not robbing and robbing the last, like a index I, and robbing the I minus one. Sorry, this is correct, but in the first one it was I minus two, right? So this is what happens in house robber problem, right? I mean, um, what I what I'm trying to get is that we have some methods to like delegate our problems to our sub problems, all right? We don't need to think about all the numbers, all the heights over here. But and also this question is in like a heap based greedy, which is I mean it says retroactive or event scheduling. I suppose it is retroactive. um like like I don't know which data structure I should even pick. What is the need? So like only idea I am quite familiar with is like a post order, pre-order, recursion, all right, making like having a choices, exploring them. And I find greedy is like a prerequisite of dynamic programming, because like here we have some choices as well, but there is only one obvious one to pick, and we are now trying to find that obvious one. But somehow now like a backtracking and dynamic programming seems like a kind of even easier in some sense. But for greedy problems it is not that easy. Maybe for some of the great problems it is also about being able to select correct data structure, right? Because here it said like the title of it is heap based greedy. So like what should urge me or trigger me to think it is heap based? Let's see, guys, let's see, because in these greedy problems apparently we need to know, like we need to come up with an idea of a data structure that we can use here, or like a deciding which data structure is, I mean, well, suits well in our for our case basically, right? Let's see. Because like for example in backtracking I kind of know what to do. I should think about what my options are, and as we go one level down, what happens to my choices, right? So I'm thinking in this way, and also I can think about what my children will return me, all right, and so that I can process them. So I'm kind of familiar with it. I'm familiar with recursion, but here we have something different. Because for example in the previous question the correct approach is absolutely using stack. Without using a stack, like there is no way you can handle it, all right, solve it. um Here I guess like we have another data structure, but like I wonder if there is one formula for grid problems that we can apply, but I don't think so. Because look at the container problem on I mean look at the other problems that we have solved today. Like they are too different. Even the first, like let's say the buy and sell stock one and buy and sell stock two, even they are two, like they differ a lot. Like even though they share quite a common name, kind of same name, the subtype of the problem like is quite different, right? Let's see. So we have like you actually reasoned your way to the doorstep. Your instinct use ladders before the climb is the greedy principle. So yeah, yeah, this is the greedy principle. So use ladders where the climb is the biggest. Yes, it's the greedy principle. And your headline question: what triggers heap? Has a clean answer that connects straight back to the stack work you just did. Let me walk you in, please. Bitte. Por favor. So first, your instincts graded. So next building, next building shorter equal free skip. Yes, correct. That is periphery. Yes, exactly. So like one obvious choice over there. If it is not even a choice, action to take. Only climbs. It only climbs when the next um, building's height is greater than ours. Cause anything. So yeah. Ladders are super valuable. Spend them where the most bricks are needed, biggest climbs. This is exactly right. A ladder on a climb of 100 saves 100 bricks. On a climb of 3, 2, it weighs its power. Ladders belong to the biggest climbs. But the biggest climb might be far away and I commit before I see it. So yes, this is the whole difficulty. You discover climbs one at a time. You can't pick the biggest one. Yes, this is the idea. We can't just pick the biggest ones, right? So the real question is, how do I commit a ladder now, but stay able to take it back if a bigger climb shows up later? Yeah, like yeah. Let me take a screenshot of that part and also where it's summarized our instinct, right? This is also important, right? Tentative. Yes, tentative decision. Oh my gosh, like look at the move you already know. Tentative decision undo. So do we like we are familiar with this because of stack. Let me take a screenshot. Like tentative decision. I really like the term. Um, so the real question is, how do I commit a lot? Yes. So yes, remember you made a tentative keep and undid it when something better arrived. Same idea here. Tentative rule. Use a ladder on every climb you meet. When you have used more ladders than you own, you must convert one past. Yes, one. We don't know which one, but one past ladder decision into bricks to free a ladder. Yes, that conversation is the undo, and here's the one question that unlocks everything. When you must demote one past ladder used to bricks, which climb do you pick? I mean, that's a good question. Like we are literally analyzing and the question and putting it in a very structural way. Think it through. You would convert the climb where the ladder. You would what would we do? Like, it says that. So it says that like again we have like some smallest and largest approach, and we need to think about these edges. All right, when we are solving greedy problem, and here it says that use like my question was like, and my idea was use ladder when the height difference is highest, more or most. All right, but we don't know where it is yet. So the algorithm says that use ladder from the start. All right, lose ladder, you use ladder wherever possible, but when it is finished, use bricks. But which part should we use? I mean for bricks, should we use bricks for this part and that part? I think it is kind of greedy too, which means we should, of course, we should use bricks for the smallest height difference, right? Let's say the height difference here is 3 and height difference is here 10. We should obviously pick 3. So that we let's say we hold a minimum index, all right? and then we finished and we have another building to climb, we can just use bricks. I mean, remove the ladder. Yes, and which ladder? The smaller. So I really like the idea of using ladders immediately. Didn't your notes mention this problem has min heap? Yes, yes. In the problem, yes, we have min heap of climb gaps, ladders to top K, bricks for the rest. Yeah, yeah. So this is like I created these nodes in a such way that uh, with one liner, like this one liner, if you if let's say if you forget how you solve it, this liner will should be able, I mean, will help you, basically will guide you. But since we don't know, like since in the beginning of this question we don't, like I didn't know anything, this didn't mean anything. But now this greedy approach, like of course, like this can only help me if I know how to structure my greedy problem. Because like now I'm quite familiar with the structure, right? The thing, like the greedy approach we have applied here is, like this is like this resembles to this question, right? Like we have like a two city problem, right? Where was it again, guys? Merge intervals. I think two cities together. So let's look at it, guys. Like here in this question, um, like we need to choose like which person go which city, right? So, but the thing we applied is moving everything, move like I mean pick every person to city A. So like this is greedy. Like this is the definition of greedy. Like moving, like doing some, let me say, hardcore stuff, like not a subtle, you know you do some real job, hard job, without caring, basically. Like you put every person there, and then the formulation now is which ones you are gonna move to city B. And for that, now you calculate the distance, let's say differences, all right, and you move the biggest one. So again, like you do extremes, all right, the highest one, the lowest one, or all of them, or none of them. So you use ladders until you run out, yes. Then use min heap to replace ladders with bricks, yes. And then use the ladders again, or um. So yeah, we start with using ladders immediately until we run out, exactly, and then we use min heap to uh, find the minimum differences. This is where we're gonna put bricks. Yes, but I have a question there actually. The question I have is like, um, like what happens if, um, let's say we have another building here, right? I mean, like, is it guaranteed for us to be able to reach that far? I mean, maybe we shouldn't use um the ladders in the beginning, but maybe here, maybe at step 4, maybe at step 5, right? How do we know? Like, how are we make sure? I mean, how do we know that this greedy approach like will solve? Maybe the best combination is maybe start with bricks and then at step 4 and step 5. This is the question. Let me ask. Like this is the genuinely a good question. So my amazing friend Hippo told me something that made me think about why this greedy approach is working here. Like we start picking, like we start using ladders right away as we hit like a bigger, like a taller um building, basically, right? But what if like um as Americana told us, what if we have a situation where the optimal solution is, maybe start with bricks, and maybe at step 4 or step 5 use the ladders, but instead we like what we do now here, like using ladders immediately. But maybe your answer will be, that's why we have min heap, right? But and then, so basically using min heap, we find the minimum distance, right? Minimum distance, minimum difference, and we use our brick there, and so that we now have one more ladder, and we use that ladder somewhere forward, somewhere, far away, one step forward, by the way, not far away, right? um but how do we guarantee, so can you please clarify? So you use ladders until you run out, yes. um then use min heap to replace ladders with bricks, yes, yes. And then you ladder, yes, yes, we use that freed ladder again in the next available place. I think the reason to use ladder instead of bricks is because each ladder you put down, you track as a potential, could use bricks here, and add to min heap. Then you know which ones to check that could be replaced with brick. So quite reasonable. Quite reasonable. We literally mark those areas where we can, um, use bricks instead. Let's see. I guess. All right. So paste your answer here, Hippo. Let's see. Yes, like I agree with you, but I guess sort of like tracking visited nodes might be more complicated if you start with bricks. Maybe doable, but seems like it could be more. So like you sound reasonable, but like I think for me, like the idea of greedy is, like I'm trying to capture the idea of greedy, all right? We do extremes. We move all of them, we move none of them. And let's say in our case, the ladder was too valuable, right? Ladder is something like gold, all right? But the thing we do now is like a start with ladders, like this is literally extreme. So this is why it is greedier. So now, like I'm trying to capture the idea, right? Hippo and Americano are teeing up exactly the right way. The answer is the most beautiful part of this problem. Let me clarify the guarantee, because once you see it, the whole approach was inevitable. Your worry, um, your worry stated precisely. What if the optimal answer pays bricks on the early climbs? And saves the ladder for a big climb at step 4. But my algorithm grabs a ladder immediately. Here's a key realization. The algorithm does not block in early ladder use. Guys, look at it. Like this is the answer. The ladder assignment is tentative, like idea of tentative, like this is good, and keeps migrating. Watch it produce exactly Americano's scenario on its own. Um, Concrete proof: bricks early, ladder late, emerges automatically. So now we have an example here. I think this seems a good question to visualize, right? Yeah. So after the algorithm process each climb, this is always true. The ladders sit on the biggest climbs seen for so far. Bricks pay for all the rest. Like this is important, guys. This is invariant. Invariant means a rule that applies for all cases in each step. So we don't need to wait until the end of the our function. But invariant means in each iteration this is true. The ladder sit on the biggest climbs seen so far. Like look at the term. Like look how AI put words. Like this is the definition of what we are doing. The ladders sit on the biggest climbs seen so far. Seen so far, guys. Like we are iterating in a single for loop. I guess if you used bricks first, then it would just be a matter of using a max heap, so you can replace the biggest brick area with a layer. Brick, brick with layer. Yeah, maybe. I'm not sure, but maybe. Hippo. The push then pop min mechanic maintains it automatically. Push then pop min mechanic maintains it automatically. When a new climb arrives, if the new climb is the smallest, mm, like this looks good, guys. Let me take a screenshot. This looks good. Either way, after the step, the heap, the L largest climb so far always. So Y ladders on the biggest is probably optimal. The exchange argument. So this is the guarantee you ask for. A ladder erases a climb's brick cost regardless of the climb size. One, yeah, one ladder. Whether the climb is 2 or 96. Bricks cost, yeah, so to cross a fixed set of climbs with L ladders, the minimum bricks you can possibly use, sum of all climbs minus sum of all largest climb. Yes. Sum of sum of the L largest climbs. Hmm. Hmm. Look at this formulation. Sum of the L largest climbs. So that's why, like, when you put the question like in this way, like this screams, we need to use heap. Like this is heap, guys. We need to use literally heap. Oh my gosh. Swap argument. Suppose an optimal solution puts a ladder on a small climb while paying bricks for a building bigger climb. Swap them. Even the best possible allocation can't afford this building. No, alright. How do you guarantee? The minimum heap means your ladders are always on the largest climb you have encountered. Look at this, guys. Which is the probably minimum brick allocation. So the journey only ends when even the optimum runs out. Oh my gosh. Like I understand the idea of greedy, which where we do some extremes, but I guess we also should be able to put the question like in this way. To cross a fixed set of, maybe guys, we can start a web agent. Ask it why use ladders first instead of brick first, because apparently there are differences. um yeah, we can ask this. um like I think, um I don't know, like, yeah, that's a good question. Let's ask. Like the only thing I can say is we need to do some extremes, and that's why we start with the most valuable item we have, and then we iterate it. I mean, But let's see what it will answer. So like we are doing this tentatively. So this is another keyword, hippo. Like we add, like we use letters, but those letters are tentative. So um keeps migrating. And also this is also important. Tentative and keeps migrating. Let's see. Let's see. Sharp question. Sharp question. And the honest answer surprises most people. Neither direction is the correct one. They are mirror images. They both work. Mm. What is not non-negotiable is the heap, the reconsideration. Let me show you both. Then why letters first is the one usually thought. So basically, it says that we can start with bricks as well. So first, what's actually wrong is the no hip version of either direction. So we are gonna need this. All right, so we understand it. So naive version will both fail. Use all bricks, then switch to ladders. You burn bricks on whatever climbs come first. Yeah. Use all ladders, then switch to bricks. So yeah, this also bricks. So both name versions commit the resource to whatever comes first instead of the biggest climbs. Mm, I think this is the core of the core, like the biggest climbs. Like everything runs, around. I mean, this one. The heap is what fixes that. It lets you reconsider, so ladders always end up on the biggest climbs. So the direction is just bookkeeping around the same idea. Two valid formulations, genuine mirror images. So a ladders first, min heap. Like this is what you said, hippo. This is what you have just said. We can apply ladders first or brick first. It doesn't matter. What matters is that having a heap and knowing our max climb. um Optimistically give every climb a ladder when you have overcommitted. More laddered climbs than ladders. Demote the smallest to demote the smallest to bricks. Yes. Tentatively ladder it. Hmm. Smallest laddered climb bricks. I guess, guys, from now on, we're gonna continue with solving a lot of greedy problem, because imagine, like, I wouldn't say if like I wouldn't say we can use like a heap in greedy problem, because like the definition of greedy in my world was something like simple, but greedy is hard now that we see. So in bricks first, max heap, pay bricks by default. When bricks run out, upgrade the biggest brick climb to a ladder. Hmm. Biggest brick climb. And in the previous one, we smallest bricks. I'm demo the smallest bricks. Yeah. Because we don't want to use bricks, and here we want to use the ladder on the highest, like a biggest brick climb. Yes. So yes, I'm a hippo. Thank you for the idea. So basically, we can do both. We can do both. I thought I thought min heap is the only way. I'm sorry, but we can literally apply max heap too. Idea is the same. So letters first, the one everyone teaches. Why? The three reasons. Um, it matches the model you just learned. Tentatively keep, then undo the least deserving. All right. Tentatively keep. All right. So this is the thing I wanna keep here. Tentatively keep, then undo the least deserving. All right. So in A's, A says everyone gets a letter until I am forced to take the worst one back. Oh my gosh. So this is one liner, I think, guys. This is one liner. Everyone gets a letter until I'm forced to take the worst one back. Oh my gosh. Let's continue, guys. Let's continue. How 40 minutes, guys. Like this is normal. This is normal. This is normal. Actually, it is good. We are under 1 hour, so this is good. Hello, Madman developer. Welcome in, Tar. How are you? How are you? Today we are studying some, greedy problems that I am obsessed with because I'm seeing this um type of question asked during the interviews, and I wanna be ready. How about you? How is your day going? Oh, this is a hard question, guys. What do you think? What do you think? Like, do you know what does heart mean, guys? I don't know it. Do you know? Like, is it something easy or something? Like, is it does it share same meaning as easy? What do you say? What do you say? Hippo, where are you, man? Come here. I feel so alone over here. No, no, no. We can handle it. We're gonna handle it, guys. Easy, easy. We have find maximize capital, KW profits and capital. All right. Oh my gosh, guys. Hard means I have no, no, no. Like easy, guys. Easy, easy. We're gonna handle this. We're gonna handle this. No worry. Say it will be easy. All right. Say it will be easy. Imagine, imagine there is a easy sign over there, right? If you still streaming when I wake up, I will join. All right. All right. My final test is programming. Oh, all right, all right. Today we are studying LeetCode, but in next stream most probably we're gonna study some Python or something. 9 hours left. So it's already done. It's already done. Like that's good. That's good. 9 hours is nothing for us, guys. 9 hours are nothing for us. C++ on freaking paper. Oh, that is hard, man. Like writing on paper is always something. Good for me. So, I guess, guys, we can start with reading the question. We can start with reading, guys. Like reading is a first step to. So thank you, thank you, and now wrap up. Create necessary documentations in a corresponding LeetCode folder. In our LeetCode folder, right? Yeah, 9 hours is nothing, right? Make it 20. Yeah, yeah, yeah. So now, like, guys, if we handle like understanding these greedy problems, then believe me, I promise, we're gonna have 24-hour LeetCode problem. So because the part I find hard is like only remaining part that I find hard is greedy, all right? Because the remaining parts I have some ideas, all right? So if we handle like a solving like understanding like we have like a 75 questions here, and my goal is like a solving at least 3 questions in each section. If we make it like a 5 or 6, then that's a good number, and we can start our 24 hours long streams, because then we can study um oh my gosh, then we can study uh, every topic basically, right? Why it doesn't work smoothly? Anyway, we can do it. We will do it after we just um let me, where is my activity monitor? All right. Have you thought of setting up a Discord? Like I don't use Discord that much, but I have an account there. Maybe we can arrange some meetings there. That could be fun. That could be fun. My another friend also told me creating what is it called? Not section, but channel, I guess. Create a Discord channel. We can do that too. We can do that too. But the priority now is, guys, like completing these questions, right? Like after completing this question, we're gonna be so happy. We're gonna be so happy. I could teach you recursion. I could teach you backtracking, dynamic programming. I'm quite familiar with those. I could teach you trees. I can, like, we can study binary search, sliding window, two pointers. Like those are nothing. We can study some array problems. In arrays, we have like a different some different examples. I want to study arrays too, but um, uh, greedy, like we need to handle. We need to understand. I ask you for Discord to help you with the task list, and you disappeared. Yeah, thank you, Tar. Like I'm using Cloud actually, and I handle this using Cloud. But thank you for your kind words. Actually, the reason is I don't use Discord that much. That's why I didn't send you a message. But thank you, I appreciate it. I remember. Yeah, have Discord servers so you can do things like post LeetCodes and talk when not streaming. Yeah. So, like, actually, guys, I plan to create 1 minute long YouTube short videos and maybe like a 5 minutes and 10 minutes, but 1 minute is long. Actually, YouTube Shorts supports up to 3 minutes. But my idea is like after the stream, maybe we can summarize what we have just studied. All right, and summarize and put in a more polished way so that we can review easier. And maybe in the next, not today, but in the next stream, we can start with creating those videos, because after the stream I feel too tired and I don't want to create some another video. But during the stream we can dedicate 30 minutes, 45 minutes, and um, like I can create those videos and upload to YouTube so that we can review easily. All right, because like the time requires for understanding a problem is too like much more than reviewing after understanding, after understood. So yeah, so what I mean is basically we can summarize 10 hours long stream into 10 minutes, and that would be awesome. Not maybe 10 minutes, 10, 15, but 10, let's say 10 minutes. So let's see, guys, let's see, like let's start that tracking again. We have now 40 minutes, and let's start. Suppose LeetCode will start its IPO soon. In order to sell a good price of its shares to venture capital, LeetCode would like to work on some projects to increase its capital before the IPO. Since it has limited resources, it can only finish at most K distinct projects before the IPO. Help LeetCode design the best way to maximize its total capital after finishing at most K distinct projects. So you are given N projects where the ith project has a pure profit, yes, this profit, and a minimum capital of capital I is needed to start it. All right, like this resembles to gas station problem. In each station we need to have some positive net value, net gas actually. Initially you have W capital. When you finish a project, you will obtain its pure profit, and the profit will be added to your total capital. Pick a list of at most k distinct projects from given projects to maximize your final capital and return the final maximized capital. So do you understand anything, guys? The answer is required to fit in a 32 bits bit signed integer. So we have k equal to 2. W means capital. These are our profits, and these are capital. This is capital, and these are also capital. What do they mean? Like, you are given n projects where ith project has pure profit and minimum capital is needed to start it. Yes, yes, yes. So to start the first project, we don't need to have any capital, any money. We can just basically start it and build it and get some profit from it. But for project 2, we need one capital. But what does K mean here? It can only finish at most K distinct projects. So 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 I guess we can pick only two different projects. So like this resembles to gas station problem very much, guys. In gas station problem we had something similar, but there we had, we had some order, right? And to leave any gas station, we should have some net positive gas, right? This was the idea. But here, the order doesn't matter. We can literally pick any project, and only constraint here is our I guess it was W, right? Our current, initially we have W. So our constraint is we need to have bigger capital than the capital I project, for example, to get um, to get the profit from it, to get profit from it. So initial capital is 0. We can pick only 2 projects. We should pick wisely. We should pick wisely, all right? Um, which project, all right? Abby is like, all right. So now, but let's see what we know about greedy, all right? What we know about greedy is that like a smallest, smallest, and the largest, all right, and the largest. So we should do some extremes, and what extremes we have here? Maybe start from left. Like would but left and right doesn't mean anything here, guys. Left and right, I mean, they don't mean anything here because the order does not matter. Order does not matter. I mean, maybe we should sort them first. What do you say? Maybe we can sort the projects, but then we should match the capital with them too. If sorting is not an option for us, what extreme we can apply here? Oh my gosh, guys. I don't see any extreme here. I mean, leftmost, rightmost, picking everything. All right, we can start with, mm, you know, doing every project. I mean, forget about K. I want to do every project, but I can't because there is a constraint W. Oh gosh. What do we do, guys? Like, should we use stack? Should we use hash map? Should we use two pointers, guys? Come on, guys. Give me something. Give me something. Two pointers, heaps, all right? Binary search. What do you say, guys? Binary search. What does we know? Like a sliding window. Oh my gosh. Sliding window. Uh, Three. DP. Backtracking. Is it graph? Is it graph? No, I don't think so. Um. So basically, for us to be able to pick a project, we need to have the necessary capital. Maybe we can define our subproblem using capacity, and inside it, let's have a for loop and iterate from left to right. Um, so what does the question ask, by the way, guys? To find the maximum amount of profit that we can get. So we need to maximize something. Do you have any suggestion, guys? Otherwise, oh, thank you for the follow. For the follow, by the way. Quit quests. Welcome, welcome in. Welcome in. Uh, Otherwise, I'm gonna ask AI, guys. Oh, we have sorting, guys, and we have max heap. Oh my gosh. Does the problem say you have to pick them in sequential order, or can you pick and choose projects? Like, the question doesn't, indicate anything about order. You can literally pick any project you want. I said something about sorting, and I said that since order doesn't matter, we we shouldn't sort items, something like that, right? But here in the hint, they say we should sort by capital. But I thought sort by profit. No, no. I said that if we sort by either of it, like a profit or capital, doesn't matter. We should also match. And I didn't tell anything after that. Maybe I should have continued my chain of thought. All right. Let's see. Let's suppose we sorted the capital. All right. And for us to be able to start any project, we should have, like, let's see, like 0 1 1, right? At least one project should be 0 or should match with the capacity. Like, this is our definitely our starting point. There is no way other way on. Starting point. So this is for sure. Maybe a min heap to get the cheapest ones first. um cheap Cheapest, you mean by capital, right? Yeah, yeah. um but why do we need even, a heap? Like, we sorted by capital, and we should pick the smallest one, apparently, and that smallest one should, be smaller or equal to our capacity, because otherwise we can just start. We just can't start it. Yeah, the ones that cost you the least amount first. Yes, yes. So this is our starting step. How about, let's say we start with capital 0, which gives us capital 1, and now we have capital 1. I mean, yes, our capital is now 1. Our W is 1. Now fun part starts, because after the initial phase, um, we can we can now pick other projects too, because mm, they are available based on given our capital. But now which one? Now which one? Sorting is our approach. Like, um, we sort the capital, and we decided our starting point, initial point, and then after having some capital, um, what should we do? Now we need, like, now we care about two things at the same time. Actually, this question resembles two guys knapsack 0 1 question very much, because there we had values, we had capacity, and like we have items. Like today, the first question we have solved was this, like item 1, item 2, item 3, and each has some value and capacity, and our knapsack has also some capacity. And the way we define our function is using the index and then the capacity. This is the definition of our capacity. And the thing we maximize is, like, either we get the value, like we get the value of the current item, and we delegate our sub problem to you know to the remaining part. And this is one option, like, or, and we don't take the item, we don't get its value, and we again delegate our sub problem to here. And also the capacity remains same, and here the capacity decreases basically. Capacity minus capacity I, or 1, let me say, I don't know. Or maybe we have capacity I. Yes. Well, this is hard one. So um like this, like I find this question very similar to the next knapsack problem. Let me write it down. Like, literally knapsack problem with greedy. I don't know how. Similar questions, and um knapsack 0 problem. So we have almost same thing over here. The only difference is that in knapsack we have like initial capacity. Like we have initial capacity here, but the capacity is changing. Capacity is changing, guys. I mean, um, like, guys, we need to think. Come on, guys, we can do it. We can do it, guys. Please believe in yourself. So, like, let's see what we know about uh Gridio, right? Like, we need to do some extremes, right? Oh my gosh, we need to know about extremes. Like I said, sorting is not an option here, but it is actual. I don't know. Like in the hint, it says sort the projects by capital value. And we also discovered that our initial, like a starting point, with with our same as our um, initial not capacity but capital. Like, this is the start point. or or maybe our rule, I don't know, like I want to do I don't know, guys. Like, you remember city A, city B problem, right? There, we moved everything in city A. And in the previous problem we have solved, we tell that we just start using, like, we just start with using ladders right away, like, and not what was it, not temporarily but tentative, I guess, tentative, right? seems like get all Seems like get all the nodes you can afford, all right, and choose the one that has most profit. This sounds reasonable. This sounds quite reasonable. Yeah, yeah, yeah. This sounds amazing, man. Get all the ones you can afford. Oh my gosh, and choose the one that has most profit, and repeat until you cannot. Like, hippopotamus, hippopotamus. Like, yeah, yeah. Like, it sounds quite amazing, by the way. Um. So basically, we sort by capital, and we fetch the ones that we can pick, basically, and we can pick only the first one, and we get its profit. And then in the next iteration, um now our capital is 1, and the projects that we can pick is these ones. And for these ones, what should we pick is, since we have, you know picked this already, now we should pick the highest. Yes, yes, like, that sounds amazing, man. I don't know, man. Like, that sounds good. Pick the highest profit, right? Pick the highest. Yes, that that's sold, man. Hippopotamus. Hang hippo. You just sold it, man. You just sold it. That's all. Let's see. My amazing engineer friend, my amazing engineer friend Hippo told me that, like, all thing we need to do is um get the projects that we can pick, basically. All right. This means that all the projects that are equal or smaller or equal to our capital. All right. All right. And then among them, pick the one with the, highest profit, and then keep this until you cannot afford anymore, basically. Like, my amazing engineer friend Hippo told me this, and this sounds amazing. And now, like, now that this question seems quite easy to me. I don't see any reason why this question is hard, listed as hard on LeetCode. Like, this is easy, guy. Like, this is easy, right? Um, is there something else we need to know, or this is the, core logic? Hippo, like, you are great, man. Like, I don't know why I couldn't came up with this idea, but this seems quite reasonable. Like, amazing approach. I mean, like, we didn't I think we didn't share the question. Let's see. Like, your solution is amazing, man. Amazing. uh I don't know. Probably easier because you've been using heaps a lot. We've been using So heap basically gives you the minimum or maximum. Like, I know how they work. We also have, again, studied like a heap sort, right? I even watched a video of heaps. I know how to, bubble it up, bubble it down. And the core idea, at least the knowledge we need to know about heaps for this problem, is that, like, it literally give you the minimum, or maximum as you reach in O1 in O1 time complexity, which is amazing. But the thing is, how you create. Oh my gosh, you and Hippo are 100% right. That is the correct greedy, and your confidence is justified. Don't let me take it away. Pick the highest profit project you can currently afford. Yes, bank its profit. Repeat up to K times is the exact optimal strategy. The what really is that simple. So here's the honest answer to is there something else? Yes, but it doesn't. The logic is the how. The problem is rated hard for a reason that has nothing to do with the greedy insight. Oh my gosh, guys, I even failed at the first first step. Let me show you the gap. Your logic implemented literally, it's too slow. Write out Hippo's logic as a plain code and count the work. Repeat k times, scan all end projects. Um, I guess it tries to show us the heap. Or rather, if you use heap, then it is done. Two sub problems. Among affordable projects, pick the highest profit. Yeah. What structure gives you the max element of changing pile in all again? Alright, max heap. Alright. So, um, so the shape that falls out. Yeah. Only again, not yeah. That's why it's hard. The grid is easy. Grid is easy, guys. But you needed two structures: sort and min heap by capital, and max heap by profit. Also, we need to make it the correct connection between these two. So there is some implementation details as well. And the insight that capital only grows to make it fast. One more thing worth knowing, and why is always take the max profit affordable optimal, not just greedy looking, because profits are non-negative. Taking the biggest profit now is strictly best uh, on both axes at once. So Hippo nailed the logic. The heart rating is the data structure design. This is your yeah. Mm, all right. So well done, Hippo. Well done. Yeah, it's just an order tree that always gives you the min or max. Yes. Oh, so optimization is a real issue. Um, uh, no. Like using heap. Like if we use heap, we already optimized the problem. So you done it. You done it, man. But maybe the another part will be like we use heap twice. One min heap, and one max heap. Um, like a min heap by capital and max heap by profit. Like, mm, I mean, how do how do we make sure that the capital we have chosen? I don't know. Maybe I slightly like it. Too bad if this was an interview, I would never get the solution. No, like you would, Hippo, you would. You literally told me, pick, you know, like after sorting, we need, we literally use, we literally get the profit from the ones, uh, we have enough capital. I'm not good at interviews. I forgot how to work. Like greedy, like we're gonna make greedy. Good. All right. So next time I see this question, I will typing the code. All right, because I have some unclear parts, but I um I got the main idea. Let's see. One more question. Course schedule 3. Anyway. So again, we have similar structure. Let's see if we can come up with you know this. Again, we needed to sort here and apply heap. So we know what we need to. Oh my gosh, we know what we need to do. Let's see. This is literally now um, a practice. Let's see. Um, it said min and yes. Um, so min heap for selecting the capital because we need to pick the smallest capital available, and then max heap for max profit. Like for us to be understand it fully, we need to code it. But I wanna solve another one. Let's see. We have the similar question over here. We know what to do. We're gonna use heap, min or max heap, and also we have thought that we have seen that sort part too. We need to do some sorting, all right, and heap. Let's see. There are n different online courses numbered from 1 to n. You are given an array courses where courses indicate that mm, duration last name indicate that ith course should be taken continuously for duration days and must be finished before or on last day I. All right. Why do you keep picking hard? Like I didn't do it. AI do it. I just ask it to give me, I just ask it to create me a grid list with all subtypes that I can see during the interviews. So it created subtypes and it added 10 questions in each step. Your brain at least hurts. My brain doesn't work. So hurting is good. All right. Um, you will start on the first day, and you cannot take two or more courses simultaneously. So, all right, return the maximus number of courses that you can take. So, this is duration. Maybe I can use a little bit, smaller. So, um, this is duration. This is last day. Day. What kind of day is this? Um, Last day. All right. So basically, if we draw that line, if we start at day 100 and it ends at day 200, and we have another course starts at 200 and ends at 1300. So we can take that course and then take this course too. I don't like having to think this much. Like you're right, but we should complete this greedy, right? I don't like if I wasn't streaming right now, I would be sleeping. I would watching some maybe Game of Thrones or maybe watching some YouTube shorts. I don't know. I don't know. Now we need to complete this greedy topic. We need to solve 5 to 10 questions from each subtype so that we are familiar with everything possible basically. Some same I need an app. Yeah. So like it's been 8 hours. Like maybe this question, we can take a maybe lunch break. Yeah. Um, let's see. So we have this course A, and we have course D over here, and also we have some other course. Like actually, I have solved some interval questions. Maybe it is better we now review them. So 2000. All right. Return the maximum number of courses that you can take. Mm, there are totally 4 courses, but you can take 3 courses at most. First, take the first course. It costs you 100 days, so you will finish it on this day, 100th day, and ready to take the next course on the next course on the next day. So we cannot pick at the same day we end. Second, take the third course. Oh, so basically, guys, like the problem I have solved before. There, we were able to pick. I mean, we were able to start our next interval, like starting from here. Actually, I can maybe here, right? Let's see, maximum subarray, jump game, gas station, merge intervals. Yes, yes. So let's see, merge intervals. So we have merging intervals. So here we merge basically, right? Yes. So when the starting point of next interval is smaller than the previous ones, and we just merge. Like this is what I have studied. And another interval problem that I have solved is insert interval. Let's see the animation. Um, all right. So what is the answer here? So basically, what did we do different than the previous question? I don't see any difference, to be honest. So I guess there is not too much that difference, right? Append, skip, merge, one pass on sorted input. Sorted. All right. All right. These are the questions that I have solved. And I guess here. No, here. No. I guess not here, not that, and here. Course schedule. All right. Um. So we take the third course. It costs 1,000 days, like a 3 years, right? About 3 years, and this you will finish it on. Yeah. So after the 1,000 days more, we're gonna finish at that day, and we are ready to take the next course at plus 1 day. So third, take the second course. It costs 200 days, so you will finish it. All right. So as a third, as a last course, we picked. All right. So um, return the maximum number of courses that you can take. So let's think like simple, right? Basic. What would happen if we pick the courses with smallest duration? No, it doesn't sound good. For us to maximize the number of courses, what is the core logic here? Um, I mean, the main constraint is the end of the current selected course. I mean, um, like we want to have more courses like as much as possible. um, One constraint is we cannot have multiple courses simultaneously, and another one is um, you know um, after completely finishing a course, and then we can start a new one. So here we need to make some choices. Like, I'm having some hard time understanding whether it is a greedy problem or a DP problem, to be honest with you guys. Because as I see choices, see you, senor. Welcome, welcome in, Americano. How are you, man? How are you? Now we are solving this greedy problem, course schedule 3. We know what to do. We need to use heap and we need to sort. Let's not think that much and uh, try applying these, right? Try sorting. So for sorting, um, sort by starting or end. Let's sort by start. Oh my gosh, do I need to draw everything? I know I don't need to draw everything. I can just, guys, click on this one and and let AI draw this. Come on. Um, I need you to draw the first example as intervals, fast and simplest. All right. Just give me the first example. First example, but sorted, and also give the example with sorted by the initial and sorted by the end date, because we may need to have them sorted by either of them. I mean, we may need to sort them by start date or ending date. Welcome, welcome, welcome in. Um, oh my gosh. Today we are greedy, guys. We are greedy. We are greedy. Where is my ice drop, guys? Crafting visual. Oh my gosh! Like if I drew that, it would be faster. Come on, man. Draw it fast. Draw it fast, man. Architecting three stacked timelines with label intervals and deadline markers. This is exactly what we halfway mark for 17 hours. Amazing, guys. Amazing. We've done an amazing job today. This is awesome. Like our goal, guys, solving as many questions as possible here. Like we can solve, maybe like we can continue with the next topic. We can solve 3 questions there, and then we can start from over. We can review a few questions. While we are solving, we can try generating some animations there. Like we have 7 groups, 7 subtypes, guys, and in each of them, if we solve, let's say, 3 to 5 questions, that is enough. I really want to listen throughout the entire duration and solve with you, but something came up. Sigusa, Senora Duca. No worries, man. No worries. No worries. I will create some summaries, right? And so that you can review, all right? In our most probably, see ya, Amika, Amika. Um, in our next stream, I'm gonna dedicate some time to generate uh, you create some summary videos. I tried generating animation for the bricks and ladders, but it got stuck and used all the tokens. Which model you used? Like a cloud? Most of the time it creates correctly. Oh my gosh. That's interesting. That's interesting. Like I got good questions like 9 out of 10. And when it makes error, like I say, you made an error there. Also, you need to guide it such that it should create building it starting with small and simple, and then after making sure. Um, but you didn't use Blender MCP, right? I guess it used JavaScript or something, right? I'm using Blender MCP, and Blender MCP works smooth, you know. Um, what were we doing, guys? We were, I think, yes. So yes, this is what we need. This is what we need. So let me take a screenshot. So we've been waiting for this. All right. Let's take a screenshot and put it there. No, I was having it make a React animation using artifacts, but it got stuck because it got confused about using minhip versus maxip. Perfect reason why we shouldn't leave everything to AI. I might be biased. Yeah, yeah. So like you should control it, but it gets better every day. So we know that we need to apply heap, right? And we know that we need to sort. So sorted by first value, which is duration. So if we sort by duration, this is the course, this is the first course, um, this is the second, this is the third, this is the fourth, and I don't understand. I like this starts from 1,000, but this is not 1,000, guys. Like what is this, man? Sorted by like Claude, are you dumb or am I? Here, the first example draws as intervals. Each course is shown as a bar whose length duration, whose right edge sits at the deadline. So deadline is this, but this is the start date, and the start date isn't. I think you may have gotten some stuff wrong, and please be careful about the start position, start date of courses. Because, for example, the course for course 3, the start date is 1,000, and in the graph, in the um, in the thing you created, the start date is like around 30. I mean 300. So, and also for course 3, the start point seems to be at around 1,300. So be careful about it. Like it literally created wrong graph. And Americano Beans redeems rosemary oil sniff to make my brain cells function a little bit better. Thank you. I appreciate for it, man. Thank you. So that I mean I need it. I need it. See you yet again. I'll return if fate wills it. Thank you. Thank you, my man. Thank you. Thank you for dropping by. Take care. Take care. It's good to see you. I mean, take care. Oh, So clarifying question versus, oh my gosh, like if I drew it by myself, we would have, the graph already. Come on, man. Come on, Claude. And we don't have the fourth course in this one. Come on, man. So we need to apply heap and sort basically. Um, let's say which one would be picked. Pick. Our goal is a maximum number of cores. What is the limiting factor? Um, what is the limiting factor here? So we basically would attempt to. I mean, it would be great if we pick the smaller. I mean, small courses with smaller duration, so that we may have more chance to have some others, right? But also we need to care about the start point as well. So there are two things we need to care about, and I think one of them is for maximizing, or maybe some function of twos is the thing we need to maximize. Return the maximum number of courses that you can take. How should we maximize this? Picking the longest courses first, or shortest courses first. After sorting, we should start with the smallest day. I mean, we should start with course with the smallest, right? Or maybe we shouldn't. Imagine that with the course with the smallest uh, start day is the highest, has the highest, or longest course. So obviously we shouldn't pick it. Like, how did we solve the previous question? IPO, um, like this is for this IPO, we literally picked like sorted by capital, and we have picked the ones with highest profits. So we literally create our available options, and we picked the highest from them. So here indicate that ith course should be taken continuously for duration, yes, days, and must be finished before. So you will start on first day, and you cannot take two or more courses simultaneously, yes. Return the maximum number of courses that you can take. We need to maximize the, so like we should pick a course and its end shouldn't be far away. All right. And for our next course, its start date should be one greater than its end date. And also for some courses that overlap, for example here we have this one and this one, like we cannot pick these two at the same time. So for overlapping courses, basically if we have one of them, we cannot have the other one. This is an observation. So basically, each course should, you know, stand alone or independent, right? They they shouldn't touch each other. Um, yeah, because if they touch, this means we can pick only one of them. And our goal is to maximize the number of courses we take. And we know that sorting is a correct option for us. Let's say we sorted by start date, and let's say we start, we start picking courses, you know, but when they overlap, I don't know, man. Like, I don't see a reason why we need to use minheap. Minheap says that among like minimum, but in term like which value, based on which value we created this heap. Most probably duration. Most probably duration. Our heap should be about duration, and maybe there can be some available durations, right? Available. But what do you mean by available? Available courses. Because let's say if we pick that one, and let's say we have another course, then picking this eliminates this option. But in the previous question in IPO, actually there we had that constraint too. Like, we should pick a um a what? We should pick not capital but project. We should pick a project and get its capital. All right. Um, we should get its capital, and then now we are able to make a choice. For this we have a constraint too, and that constraint is start point basically. And as we pick a course, it changes. But which course should start, we don't know. In the previous question, start like initial point was initial point was clear. All right. Here we don't know where to start, I assume. Actually, maybe we know it because we cannot start from here, right? If we start picking the course 4, it will mean we didn't select any course from the previous, right? Um, so if you pick the smallest, like a interval with the smallest, then we should be careful about our next option, because next option start point you know shouldn't be smaller than our endpoint. So maybe here we may use a heap. But the thing is now, like, I wonder the situation where we have like a should we start with the smallest start day, like should we start with the course that has smallest, or maybe the correct approach is this, maybe correct choice is this, like, we don't know. Because maybe our first course has like a start at day 1 and goes all the way to the day 2000. But another course starts here at day 2. All right, at day 2, and maybe at and day 3. All right, and then maybe we have another course on day 4, and it ends at day 5, so that we can select many questions. So our solution should, understand this, should cover this case apparently. So our greedy approach. So we know that we need to use min heap. So min heap should be created on the duration or start point or end point, or maybe we may have like multiple heaps, but I don't see any reason why we need to use any of them, because I don't have like a clear reason. Like, I mean, how should we how should it, like, how would it decide? Maybe guys, we I should read a book about greedy. I don't know, because we literally may have um this situation, this case, and our approach, our greedy approach should cover this. I don't know. I don't know. What do you see? What do you say, Hippo? Like, you are better. Like, you better. You good at this. You are good at this. You are good at um this greedy. So like our first course, could be like this. Something something heap somewhere. Exactly. This is exactly what I'm thinking. Something something heap somewhere. Exactly, man. 100%. 100%. Let's see what AI will tell us. I don't know. It's been 30 minutes. Uh, so did we create? Anyway, let's create the documentation first, and then we'll start with getting the courses closest to deadline first. Sort them or whatever. So uh, you are telling me that basically starting in reverse order and sort them based on their end, basically going backward. Let's see. Yeah. My eyes. Yeah, because we want to take courses that will expire soon first. What do you mean by expire? I mean, do you mean about, I mean, their duration or expire date? Expiration, expire date. But I don't think it is the way. Like, we want to take courses that will expire. We want to take courses. I mean, yes. So the duration. We are talking about the duration. So we need some courses that with small duration, so that we can. All right. Or this sounds logical. This sounds logical. Um, we literally, we want courses with short duration, not duration. What do you? I mean, but we want with short duration, because if the duration is short, and then we can start the next one, and then we can start the next one, and then we can start the next one. You mean deadline? Uh, so I don't think deadline can help us. You mean sort by deadline, not start date. I think this is what you mean. Um, so if we sort by deadline, uh, let's say we have this, we sorted by deadline. So now what we should do, like, we need some sort of overlapping system, right? If they overlap, we shouldn't pick. I don't know. Let's see. Like, so now the problem is this, and my engineer friend Hippo told me that maybe we can use, like, maybe we can sort by deadline expire, like we, because he said that we want to take courses that will expire soon first, like, um and for me, the thing I know here is it would be great if we have courses with a short term, all right, short duration, so that we can pick a lot of, I mean, we can more courses. Like, we need a one line definition for our greedy problem. Like, we need to define what we need to maximize, right? um Maybe duration can be a key for us, but other than that, like, I don't know how are we supposed to apply sorting and then heap, because heap means, like, heap will give us, like, if we have min heap will give us the smallest one, each one we want, each one whenever we want. But here, which minimum, I mean, which minimum we need? For example, if you have three courses, one is Monday to Tuesday, one is Tuesday to Wednesday, and one is Monday Thursday. If you do not sort deadline, you might take Monday Thursday class instead of the other two. And since we want to maximum number of classes, we want to take the two shorter ones instead of the big longer one. Yeah, we need to do that, but I'm trying to understand your approach. Let me copy. My friend Hippo said this too. I don't know, man. Like, I don't know. We should take a break for 1 hour straight. All right, my eyes started getting, itchy. Like, I don't spend that much of energy solving knapsack problem or backtracking or tree. also, I also do not guarantee I'm right. Oh, I see. So yeah, no, no. There's like no worries, no worries. It is good that you show your idea. That's why we can discuss and we can see from different angles. This is how we learn, basically. I'm glad you are doing that. Um, Mines are not, You and Hippo have both right pieces. You just haven't seen how they snap together. Let me give you the one-line definition you asked for, then show exactly which heap and why. One-line grid definition. What we maximize the count of courses. So this is what we are maximizing. And among schedules with the same count, keep the one that uses the least total time. So there is room for future courses. That second clause is the secret of this problem. So, like, we have found this part, but we didn't part this part. So the second clause, oh my gosh, the second clause is the secret of this problem. It is not enough to count. You keep your chosen set time cheap, so later courses can still fit. Hold on to that. It's what the heap will enforce. Why sort by deadline? Maybe we can make it even even bigger, right? Appearance, zoom in. Yes, bigger the better. Um, what happened, man? Oh, let's see again. Why sort by deadline? You said you said by deadline. Hippo is right. Here's why. Here's the why. The deadline is the hard wall. A course is useless if it can't finish by last day. Yeah. Process courses in increasing deadline order, and something magical happens. Oh my gosh. When you are deciding on a course, when you are deciding on a course, every course you have already chosen has an earlier or equal deadline. When you are deciding on a course, every course you have already chosen. Like guys, like this is quite recursive. You have already chosen has an earlier or equal deadline. There's an earlier or equal. So we basically sorted. Yes, yes, yes. So they all must finish before this course, before this course's deadline too. What do you mean by that? Oh, since we sorted, yeah. But it says every course you have already chosen. It's not about only magic. Magic. Um so it is not about only sorting, but also um or the or the choice, and also about our choices. So if you make a choice, we literally, like guys, we need to make a find to connect the dots, like between recursion, like a post order and DFS, and greedy. Because if you do that, I don't know. Let's see, guys. Um, I am trying to understand greedy problems, and they are hard. They are hard. They have like there are multiple like various sub problem types. For example, like this one. What I need to know is like is are there any books about greedy, because like I am having really hard time understanding it, all right? And because for example for recursion, I have read a book written by a professor from a college, and he said that most of the students are making this mistake, trying to uh, keep each stick frame in their minds and then solve it. So I was making that mistake too, and right after I read that line, then that clicked. Then I started understanding, because it is the it is this is the time where I stop working, or I stop seeing those problems in an iterative way, and I started using recursive way instead, all right? I wonder, is there like are there any books about greedy? Because like i'm getting I'm getting like ideas after seeing the solution, after seeing the solution. um but for example in this question, which is um course schedule 3, although even I know the one liner hint, which is sort by deadline, max heap, pop longest if over deadline. So like I should be able to solve this question as soon as I seen even this one line, because this explains a lot, all right?
like I'm quite familiar with the recursive idea and pre-order post-order. Let's send it. I think grokking algorithms has a chapter on greedy. Yeah, yeah. Let's try. Let's try. Um, because that book helped me a lot about. So like I can easily understand the backtracking problems, problems, and then tree problems, some graph problems, all of because of I understood recursion. But here I think I need to grasp the idea of greedy, because greedy is for me now like trying the lowest, the highest, and then some formulation logic like maybe 2 pointers or something. I don't know. For example, there was a question like called water, like a container with most water, and there we were using like a 2 pointers inward, and we were moving the smaller pointer inward. Like this was our logic, and almost in every greedy problem there is a different logic, all right? But I'm trying to understand how can I get a core logic, all right, and then I can apply that core logic into various greedy problems, so that I don't need any map or something, right? A common sense guide to data structures and algorithms has it too. I was reading this one before, and I enjoy it. Let me um, let me take a screenshot. I guess I need to read some books, man. Like, let me paste it over here. OCR and some text. Well, not text. Books. Come on, man. Come on. Um, and there is also cracking the coding interviews book. I have a lot about it, but haven't got around. Yeah. I have heard about it too. Um, I have bought a book from another people. Like there were like 150 questions, common asked questions, and I have started solving them. But I haven't read the cracking the coding interview. Um, maybe we can get a list of questions from that book, cracking the coding interview, and maybe we can read it. I have so many books I still need to read. Yeah, I have to. It's normal. Let's see what AI will tell us. Like, because in uni, I thought that grid is for stupid people. I thought grid is so easy. Then why do we even see it in our algorithm course, all right? And I still, see the consequences of that thought. Grid is not easy, man. Maybe grid isn't. Maybe is the hardest one. Um, Most probably is not the hardest one, but like if you don't know what to do, then it becomes hard, right? Because now I do what I need to do on backtracking, on dynamic program, on tree, on binary search problems, sliding window. I know what to do, even though I can't try. Currently, I can't even try. Real talk first. Oh my gosh. I bought all these books for when I did my masters. Oh, and the essay course ended up being basic. Yo, wonderful, amazing, wonderful. Congrats, completing your masters. That's nice. Real talk first. Greedy doesn't have a single mechanical recipe the way recursion does. With recursion, the click was stop retracing stack frames, trust the subproblem. There is no equivalent one linear that solves every greedy problems, and that's exactly why it feels like every problem has its own random logic. 2 pointers inward, sort by deadline, maxip. But there is one unifying idea that plays the same role for greedy that trust the subproblem played for recursion. So
Once it clicks, all of your color categories collapse into one mental model. Move. The core idea is safe choice plus exchange argument. Stop asking what is the locally best move. That's the naive, often wrong version of credit. Ask instead, is there one choice? Is there one choice, guys? I can make right now that I can prove I will never I will never regret. Um some optimal solution either already makes this choice or can be rewritten to make it without getting worse. All right, like this is where we have used tentative approach. Useless degree in Japan. No, yeah, yes. I see. Like, actually, to be honest, like a few days ago, a senior engineer that I, give some respect, also told me that some degree. I mean, maybe master. I don't know. Yes, after master we have PhD. Some master degrees, in Turkey, they don't mean a lot unless they are so specific and niche, unless they are in niche area, or unless you applied a company where they are exactly looking for the knowledge you have. So yeah, yeah. So basically you need to find the correct company for it, and if you find it, uh, then I think it will be better. It's not even niche, it's software engineering degree. Yeah, yeah. Let's see. we're gonna solve We're gonna solve these greedy problems, and our lives will be better. All right. This is the promise. This is the promise. All right. Hopefully, nobody want a degree on experience. Yeah, yeah. They value experience more, but they value lead code too. This is what I know. I've seen I got lots of interviews, and they ask this type of questions, and I failed, and I couldn't get the job. So that's why I decided understanding these parts basically, because I've seen lots of remote jobs asking this from around the globe, and even in Turkey, yeah, they ask this. So this is another college entrance exam for software engineers, basically. If yes, you commit to it and recurse on what is left, and that's the whole engine. The technical name is the exchange argument. Gradually transform any solution into one greedy found without hurting its quality. The sibling technique is greedy stays ahead, where you show the greedy solution is always at least as good as the optimal one. Really? Greedy never falls behind. Alright. So the reason every problem has different logic is that the safe choice is different each time, but the proof shape is always one of those two. The two pointers, heap sort by and stuff isn't the logic. It's the tool that finds the safe choice fast for that particular shape. Let me reread your own example through this lens. So, container with most water, the safe choice, like the move the shorter, yes, it is, but until coming to that point, it takes time. To move the shorter point inward, why is it safe? Because area is bounded by shorter wall. Moving the taller one can only keep or shrink the width limited area, and so you can never lose the optimum by discarding the shorter wall. That justification is an exchange argument. You weren't doing two pointers trick. You were making probably safe discard. So of course, mm, what happened? Oh my gosh. Yes, probably safe discard. So Course schedule 3, you know the one liner, sort by deadline, max heap, pop the longest if over. The derivation, process courses by deadline, keep the set you've taken. The invariant is for the K courses I've committed to, I'm using the least total time possible. So like this part is what I thought, and um this part is what you just said. Like we need to combine these two. I'm using the least total time possible. When a new course would blow its deadline, swapping out the longest course taken keeps the count the same. Gosh. Here's the picture. This worth burning into memory. The canonical exchange on interval scheduling. Why grid works? The exchange argument. Any optimal solution. 01, 02, 03. We have G, 02, 03. G. I guess we can create an animation for it. Your practice loop, the recursion click equivalent. For every grid problem after you solve it, or after you read the solution, force yourself to write one sentence. The safe choice is X. All right, let me take a screenshot. The safe choice is X, and it is safe because swapping it into any optimal solution doesn't make the solution worse. If you can't write that sentence, you don't owe the problem yet. Same rule as your recursion book. Memorizing sort by deadline heap is owning the tool. Writing the swap sentence is owning the logic. Do this for 15, 20 problems across your categories, and you'll start predicting the safe choice before you see the solution, which is the thing you are missing right now. There are no famous books about greedy, but one chapter of book is the closest thing. This is the one. It teaches greedy exactly the way you want. Through the greedy stays ahead, an exchange argument, lenses with internal scheduling as a running example. It gives the intuition behind algorithms more than any other algorithms book, and what it covers covers brilliantly. Grokking algorithms. Yeah. So let me take a screenshot of these books, and I'm gonna read the related parts from them. Book and books slash reading. What was the stream code? I will copy chapter about grid algorithm from my um it is this one. Hippo, welcome. Grid algorithms, yes. Hello. Oh, like the synchronization is good, man. You type and let's so we have now so thank you, but I wonder if you create a skill like a prompt for creating a skill um for like a making cloud a tutor but especially for greedy. All right. When I am like when we are studying greedy problems, I want that skill to be fully dedicated, fully customized for greedy problem, and give me that prompt. And also I will give my AI to make an online search and find the related parts from these books and find the correct intuition, especially you know the safe choice is X, and it's safe because swapping into any optimal solution doesn't make the solution worse. So I'm gonna add this. And also the thing about so is there one choice I can make right now that I can prove I will never regret? Some optimal solution either already makes this choice or can be written. So and this one. And also you said something about say I don't know. You said something cool about the choice and regret. I think something. What was that again? What was that again, guys? Um, it used a term. Um, anyway, it can answer. This may sound sound like a strange term, but here's what it means. A grid algorithm is that in each step chooses what appears to be the best option at that moment in time. This will make sense with a basic example. Array max. Let's write an algorithm that finds the greatest number in an array. Greatest number in an array. One way we can do this is to use nested loops and check each number against every other number in the array. Um, when when we find the number that is greater than every other number, it means we have found the greatest number in the array. As is typical for such algorithms, this approach takes n squared time. Another approach would be sort the array in ascending order and return the final value from the array. If we used a fast sorting algorithm like quicksort, this would take n log n time. There is a third option, which is greedy algorithm. And here it is. Let's see. I think using a maximum integer, right? Yes, greatest number. Because this rule will like this is invariant. This is invariant. Because in each step, in each iteration of for loop, this is true. As you can see, the first line of our function assumes the first num assumes like this is a good word assumes the first number in array is the greatest number. First number is the greatest numbers. Now this is a greedy assumption. Hmm. Greedy assumption. So like in the question, like in that question we had that we made that assumption to like a um uh what was Einstein problem. What was it? Yeah, furthest building you can reach. In Einstein problem, here again we start using ladders immediately. All right, they kind of same, right? And now this is greedy assumption. Um, that is, we are declaring. the first number to be the greatest number, because it is the greatest number we have encountered so far. All right, all right. After he write, we're gonna continue reading it. So um, let's see. Um, where is our, yes, here. So all right, let's try creating a new skill for the dedicated for greedy guys. We have our tutor mode 2 and tutor mode 3. Now I want tutor mode greedy skill. For this, I need you to create some web agents and find about these books and how they teach greedy. And I need you to give me a skill where when I ask a greedy problem, he will teach me the core idea. All right, because I really want to learn this greedy approach. Because in each greedy problem there can be some different aspect to it. All right, and I want to capture the idea of greedy, because greedy is like, after greedy, like in greedy we have options too, but there's only one optimal solution, so we don't apply DP or backtracking. But in backtracking and DP, we need to explore every options, right? And like, I'm practicing for interviews, so I really need to learn this greedy approach. All right, let's see. So basically, make online search, find those books, understand how they teach, you know, greedy, and teach me so that I understand. All right, let's see. We need a special skill. All right, and but as Hippo said, like, we do some greedy assumption that clicked some stuff, but um like, I guess this will be even more clear after we solved like, after we do our second loop in our greedy problems. Like, as I said, like, solving 3 to 5 questions from each subtype, I suppose will be enough, quite enough. Let's see. Oh my gosh, Hippo is still writing. Oh my gosh. Let's see. Thank you, man. Thank you. Um, yeah. So now it created some web agents. Um, I needed to read those sources and understand and get the core logic from there and create a skill for us, so that you know it can guide me how to think. All right, because the recursion idea I got is was that from that book. All right, it is this is quite important to read those books. I mean, this kind of um, books. Let's see. And while it is cooking our new skill, maybe we can just open this and see the question. Oh my god, see the question and wiggle, wiggle, subsequence, wiggle subsequence, paste it. All right,
and also a few examples because we need them in this type of questions. All right. Wiggle, wiggle, wiggle. Merge triplets to form targets. Oh my gosh. What kind of questions are these, guys? No, no, no. We're gonna handle this, guys. We're gonna be faithful, alright? As Michael Scofield said once said, be faithful, right? To his brother. Have some faith. Yes, yes. He said, have some faith. Because when he was a child, his brother told him, have some faith when uh, when they were going through some, hard times, and when his brother is in prison, and when he was trying to get him, out of this prison, uh, there was little time until his execution, and Michael Scofield told him that have some faith, brother, have some faith. So yeah. Dota 2 Senate, guys. What type of question is this? Oh my, Vamushinde, guys. Um, Entschuldigung, Entschuldigung, guys. So let's see. Ich bin 15 Jahre alt, guys. Ich bin, ich bin 15 Jahre alt. Um, these are examples. All right. Eliminate max monsters. Amazon and Microsoft ask this. Let's see what type of question is this. Let's see. Eliminate maximum number of monsters. Maximum power. Like in Crisis 2 game, we had like a maximum power. We had some suit, and that suit, was making us, some superhuman. I really enjoyed playing that game. At least the idea was good. A suite, basically, a nanotechnology suite. I guess now, like, after the break, we can continue with the last subtype, which is custom sort frequency. And then we can start from over, and maybe we can start generating some animations. All right, animations do help. Yeah, we can go over the problems, we can create animations. How much RAM I am using? Maybe we can instantiate 2 more Blender process, and they, we can assign a role them, a goal, and they can create those animations. Let's see. Oh, so now I guess, guys, our skill is kind of ready. Let's see. So everything confirmed. I have grounded research and directory layout. Now I will write the greedy tutor skill, keeping your draft spine but hardening it with what the books actually say. Hello, welcome in. H2 beat. How are you? I hope you are doing just fine. We are studying greedy problems. I even created a special skill for understanding greedy. Can I hire you to help me finish a small PC app that I made with 2 prior coding experience with Codex and Visual Studio? No prior. Small PC app that I made with no prior experience with Codex. Yeah, we can talk. No need to hire, man. What's the issue? Like, share the GitHub link, and like after the stream we can, look at it. What's the issue?
What the research changed versus a generic greedy tutor. Yes, so the three web agents pulled the pedagogy, not just problems, from Kleinberg, Tardos, Wayne, Preston slides, and this one Erickson and Stanford. Yes, yes, yes. The skill bakes in their consensus. The issue is I don't know which language. Which language did you use? I mean, Python, Java, Node.js, TypeScript, Electron.js, C Sharp project. The unifying idea you've been missing. Every book says the same thing. Greedy. Find the choice you'll never regret. Oh my gosh, that's the life, man. That's the life. Find the choice you'll never regret. Once some optimal solution already makes or can be rewritten to make without getting worse. Con consultation costs one cent. Yeah, yeah. Yeah. That would be great. Yes, yes. One subscription. Thank you, Paul. That is a good idea. Yeah, definitely. So this greedy choice, um, greedy choice property and optimal substructure. Ericsson best local choice blindly plow ahead. This is your trust sub problem equivalent for greedy. Yes, the greedy versus DP line you ask about made precise. Both need optimal subtraction. The difference is greedy makes the choice before solving any sub problem. And exactly one sub problem survives. Where DP's dynamic programming choice depends on many sub problem solutions. Um, yeah. So greedy makes the choice before solving any sub. Like I like this line. Greedy makes the choice before solving any sub problem, and exactly one sub problem survives. All right. Let's see. Let's paste it because I really like this idea. This line. So the two proofs shapes when to use each exchange argument. Exchange argument. Like what is that, man? Like exchange argument. Like do we exchange some money or something? Some knowledge or something? Optima same size differ in cost. So versus so exchange argument is optima same size differ in cost. Um, greedy stays ahead. Optima differ in size. Oh my gosh, guys! Like I think, guys, this is something essential. Let's paste it over here. So number one trap, all three handouts flag. Don't prove greedy by naive contradiction from many optima exist, so the swap must show no worse, not strictly better. We are not. So does it mean we are not looking for a better option, better choice, but no worse? Counter example, first habit. Erickson's drill 6 out of 9 plausible rules fail is built into hint ladder. Kill bad candidates before finding the safe one. So I can say this for gas station problem. Like in gas station problem, like we applied this like a literally. The one idea plainly. The reason greedy felt like a random tricks. Yes. Like it is like this is how I feel right now. The reason greedy felt like random tricks. Nobody told you the data structure is the last step, not the first. Every problem is the same move underneath. Is there a choice I can make right now that I will? Oh my god! Like I keep hearing this, but what does it mean, man? Is there a choice I can make right now that I will never regret? How am I supposed to know that, man? Why would you? I mean, why would no optimal solution ever do better Oh my gosh, like there are too many words. I don't understand it. The heap, the pointer, sort, monotonic stack only appears after you have justified that choice. The skill forces that order on every problem. How to use it? Just name a greedy problem and gas station grid, and it auto triggers opens. Oh my gosh, man. Let's see. Let's see. Let's give it a try, and then maybe we can take a break, guys. So activate tutor mode greedy for problem. Which problem? Which problem we were talking about, guys? Not IPO. Course schedule. It was this one, right? Yeah, yeah. No. Yes, right? Most probably yes. Let's see. And let's see what Hippo told us, written for us. Um. Oh my gosh, guys. Oh my god. He's still writing. Um. What's going on, man? Um. Oh my gosh. Um. Yeah, yeah. We will read it. Let me copy it in case anything bad happens, and paste it over here. I don't wanna leave. I don't wanna lose this knowledge. Um. All right. Goal: take the maximum number of courses. Yes, where each course takes duration days and must finish on or before its last day. Yes, so this is and must finish on or before its last day. Yeah. If you process courses on one deadline at a time, earliest deadline first, what is the one commitment you could make and later undo? Like, I love this undoing. Like, this is just amazing. Like, we just undo. Like, it's like it's kind of like backtracking or something that you would never regret making. Oh my god. So the thing I wonder is, how am I supposed to know how to sort based on, like, we sort based on what? Do we sort based on um I mean, maybe the start point? Like, you immediately assume that I know how to sort it. I mean, like, this is another knowledge. You cannot assume. All right. First, give your reasoning why we sort by the earliest, like why we sort by deadline. Yeah. So start with that. Come on, man. Um, let's see. What happens to my mouse? Let's close that one. Oh, it happens again. What did we um what did we what do we have? Yes, all right. I guess it seems valid. Let's present. Come on, man. Let's see. Let's see the reasoning behind it. Fair. That's the right thing to challenge. I shouldn't assume the sword key falls out falls out of the sky. Yes. Let me reason it instead of asserting. start with the one hard fact about this problem, guys. You can only take one course at a time. Yes, hard fact. They are sequential, no overlap. Yes, yes. So we've done this, guys. We thought about it. They cannot overlap. So everything lives on a single timeline, starting at day one, course after course after course. A course with last day D has a wall. All the time it occupies must sit before day D. All the time it occupies must sit before day D. Yeah, because if it is the last day, so all the time it occupies. Yes, yes. So like you don't need to tell us. It is obvious. Now the key question. Forget sort. Just ask if I lay courses on that timeline left to right. Which courses wall am I most likely to crash into first? Um. Oh, subscribed. Thank you. Thank you for the subs, man. H2 beat. Thank you. I appreciate it, man. We don't have any, alert alerts for somehow. So now you can ask the question about you can ask question about your issue. Now we can chat about it. Jokes aside, thank you for the sub, man. Um, so now the key question. Forget um, forget sort. Here we go. Yeah, yeah. So now the key question. Forget sort. So like let's see. Let's lay those courses, right? Let's lay those courses. And which course wall am I most likely to crash into? I mean, the longest one. Oh. I mean, the longest one, right? The one with the smallest last. Oh my gosh. It has the least room to maneuver. Hmm. It's the wall. Its wall is closest. A course with a huge deadline barely cares where it goes. Haha, no issue yet, but might need someone who knows more than me to help me. Not for free, obviously. Do you have a Discord? I have actually, um, but I don't use it very much. But I can share the Instagram or X account that I just created for my streams. Let me share their links so that we can communicate more there. Insta will do. All right, let me share the Instagram. Um, yes, I am human. uh, Let me type the number. I guess it is. All right. Let's see. Oh my gosh, I already have done this. Hold on, guys. Let me find the profiling. So, um, why it is last day, but it is not, um, with the like as Hippo said, it is not about the duration, but it constantly tell me that about it is about last day. But we're gonna um, we're gonna understand it. Hold on, guys. Why don't we have? All right, let's wait. At least let me share the Twitter. Goto setup that Discord is measured. Yes, yes, like um, everyone wants it. So yeah, yeah, we'll do, we'll do. Now I'm waiting for message to come from Instagram to WhatsApp. Not not normal SMS. All right, let's try adding this Instagram. So everyone wants it. So we're gonna upload the very question selfie. Oh my gosh. Upload a photo. Maybe it can take a photo or something, right? Or we can share a photo from here. Like last time um I could open my Instagram account without an issue. You submitted an appeal. Yeah, yeah, yeah. Hmm. I think there is an issue with my Instagram account. This this is strange. All right. Like you can send a message on Twitter H2beat. Currently Instagram account is not available. Um yeah. Okay. Because like on Instagram I was using Instagram without an issue, but I guess somehow I don't know. I guess it take me like a bot or something, but I will fix it. Gotta set up this Discord. Yeah, yeah. So here, the one with the smallest day. So as Hippo said, we only care about. Actually, I didn't understand that part. So let's continue. So here's the reasoning for the sort key in one. If I process course in order of earliest deadline first, and at the moment I'm deciding about a course with deadline D, I have already considered every course that also had to finish by D or earlier. Nothing, guys. Don't worry about it, guys. Don't worry about it. Don't worry about it. What we are gonna do is now activating our superpower, right? Thank you for the explanation, but I understand nothing. So I need you to connect my Blender MCP and suggest me some like animation ideas. And I will pick one and you're gonna generate an animation because I don't understand anything at all from what you just write. Not you just written, right? Like I'm a visual learner and I need, visuals, guys. Um yeah. Let the blender cook. It usually takes about an hour to review your information. Alright, so alright. In about hour, maybe I will be able to share my Instagram H2bit. So and we're gonna solve your problem right away. So idea one. The timeline will why sort by dateline? Alright, courses are colored bars dropping onto horizontal timeline end to end. Each course has a vertical deadline wall at its last day. We add courses earliest deadline. Alright. The heap, the real trick, the heart of the solution. We greedily take courses onto the timeline when total time, um, when the total time overflows. When the total time overflows, a deadline wall. The longest course already taken lives. Right. So thank you, they are brilliant. I need you to use idea one and idea two. We have some camera angle knowledge written in our Blender camera documentation. You can start applying the idea one, and then when it finished, our camera can change its direction and look at that another place, and there you can show us the idea two. All right, we're gonna handle this, guys. Um, let's see, and also I was able to create multiple Blender processes at a time, but how I was doing that? Mm, do I have a note about Blender? No, I think we can ask AI. But we shouldn't render uh, more than one. We shouldn't render um animation, multiple animations at a time. So I want to run my Blender headless so that I can create like a multiple animations at a time. I had a way of doing that, but I forgot. Currently, I have one open Blender MCP that is running on, I think, 9876 port. And what, like now, it will be great if we create another headless session. I mean, another session with headless, and we can set it port, set its port, and I wanna basically create another animation. Um, how can we do that? Just show me the way. Don't do it, but just show me the way. Let's press enter and hope for the best, guys. So now, all right. Now it started creating animation, and while it is creating, we can read what hippo. Oh my god! And he is still writing. Oh my gosh, hippo, what are you doing, man? Let's read some of it. Our grid algorithm and didn't pan out as we hoped, but we shouldn't give up yet. Often we need to tweak grid algorithm a bit to get them to work. Let's see if finding a pattern may help. Mm, it usually does. As we've seen before, the best way to find a pattern is to generate lots of examples. So let's come up with some examples that example arrays with their largest subsection and see if we discover anything interesting. When analyzing these cases, an interesting question emerges. Why is it that in some cases the greatest sum comes from a subsection that starts at the beginning of the array, and in other cases it doesn't? In looking at these cases, we can see that when the greatest subsection doesn't start at the beginning, it is because a negative number broke the streak. Oh my gosh, guys. The pattern is if the negative number causes the preceding subsection's sum to sink to negative number, the streak is broken. I feel like running state greedy type here. Like we have subtypes, and this resembles to a running state, like a cadence and jump game family. I kinda understand these. Let's see, my man. the found the trail. You have done this before. There is a Blender parallel text dictionary. Let me pull up how you set it up. Mhm. It's not background, headless in the literal sense. It's an independent interactive Blender instances, each with the Blender MCP add-on server on its own port. So open a second Blender instance. Just calling this one. Yeah. Let's create a Blender node. Let's save it. And let me create those processes, and then we can take a break. It's been almost 2 hours, I suppose. Oh my gosh, this is 3 p.m. guys. Time goes fast. We need to be even faster than that. All right. Um, we're gonna handle it. We're gonna handle this with animations, all right? Because with animations, there is no like we can understand it easily, right? Um, so run this command in that new Blender. Point its add-on yes. Yes. Open a second cloud code session in the matching workspace. Yes. So yes. So yes, this one I was looking for. So all right. So basically, guys, I should just open another terminal, and there, let's open another Blender process and see if my PC got shut down or not. No, don't worry. We can handle it and change the port to 77, right? Yes, connect the MCP server, and then guys, clear it and run. All right, now we are in here. Yes, so let's call it Blender 2. Change the color, make it red, and make it um, Blender 2. Which animation do we want, guys, in Blender 2? I think it would be great if we have an animation for. Did you understand, Ipo? Mm, maybe. Furthest building you can reach. Maybe we can start creating animations for this problem. So let me open the Ipo problem. Um, I wiggle subsequences, course schedule, Ipo. Yeah, we need an animation for that. We need an animation for that. I need you to present some ideas, like animation ideas. Use our Blender MCP port 9877. I guess we are in the right port. And I need you to present some, animation ideas. And yeah, we should create animation for that. I'm trying to grasp the idea of greedy. And greedy problem has different subtypes. For example, it has like a running state, interval scheduling, sort plus pair slash custom match, like a two pointer slash counter greedy, monotonic, static greedy, stack greedy, and heap based greedy, custom sort slash frequency slash misc. And like now, I think these problems belong to heap based greedy. So now I need to understand this. I need to internalize this. So create an animation, like create an animation for that. But first, present us some ideas. Let's see, guys. And then in another session, let's see the RAM usage. Let's see the RAM usage. It is not bad, I think. It will survive. Like, unless we do rendering, there should be no issue. And let me open another Blender session, guys. Oh my gosh, what we are doing, guys? Another Blender session. And yes, change the port to 7.8, I think, right? It was, yes, 7.8. Connect to MCP server. Copy this part and make job 2 to 3, right? All right. Connect to our Blender MCP. I need you to create an animation for this problem. I'm trying to grasp the idea of greedy. All right. A greedy problem has some subtypes, and this is one of them. I need you to represent us as some animation ideas. All right. Before starting, I can pick one of them, and you can start building an animation. Oh, Ichiko Game, welcome. Thank you for the follow. Thank you for the follow. How are you doing, man? How are you doing? We are now like creating animations for greedy problems. We are studying greedy problems, and you know, we will do it, man. We will do it. We will understand this greedy problems. Like, it has 7 subtypes, and after solving 5 questions from each subtype, we should be able to solve any problem, basically, right? Um, don't start rendering unless I explicitly tell you so. Um, Here, which capital water level to trace? Which question we have given to it is one. Distinct projects. So how is it related to water or something? Before the ideas, let me anchor why this problem is heap-based greedy. You have running state. We have a running state. Your capital W. Each project is a pair. Capital needed, profit. The greedy choice is repeated k times. Among every project I can currently afford, grab the one with maximum profit. Yes, repeat. Animation ideas, capital water level. Interesting. So we can, like, this sounds interesting. Which animation concept should I build in Blender? Smooth readable, focus on greedy choice, max available, light on heap internals. Yeah. Yeah, intuition is what we are looking for. Um, don't start rendering unless I tell you so. All right, now our animations are cooking. All right. This one. Yeah, I guess they are just fine. Want to watch it first? All right. So I think our first animation is created. Let's see how well it has done. What was the question again, guys? The question was, I think, course schedule problem, and here we sort by the deadline. I don't know why, but there is obviously a reason behind it. All right, we need to understand it. So maybe I just can um, zoom a bit. You can see it, right? Yeah, you can see it. Naive greedy. So let's see how the animation runs. Let me do this. So all right. So here, guys, the naive grid is doing what? I don't know. Let's see. This is course one. Course one. The duration is 5. All right. And all right. I think we got this course. Yes. And then what? And then our next course comes, which has duration 4. But their deadline, I mean, the first course deadline is exactly at 5, and the beginning of course 2 is again at 5, I think, but we cannot pick two of them at the same time. C2 finishes on day 9, which is bigger than its deadline. What do you mean, man? This is naive approach, I think. Yeah. The fix on overflow, eject the longest course taken. A max heap returns the longest in log n. The fix on overflow, eject the longest course taken. Oh my gosh, guys. Like, do you understand, guys? Even the animation, like deadline 5. Like, I'm trying to understand the start point of course 2, and like, it would be great if we see the input for this um, animation. Like, that's an amazing animation, but could you please add also the input on somewhere appropriate so that we can see the input? Because here I don't know what kind of courses we have, and whether if they have like a same day 5, like where and when is the course 1's deadline and when is the course 2 start point. And and what is the general deadline, overall deadline? Guys, look at the animation. Like, this is this is so cool, guys. Look at the moves. Come on, what is this, man? Like, let's look at that. A max heap returns the yes, so the fix, and on overflow eject the longest course. um like, we need to understand the meaning of this yellow thing that moves to right. I think it represents, like, if it represents the next available start point where we can take a course, basically. But why it is not on day 6, but it's exactly at 6:5, even after the course 1 duration? So, like, this is what I want to understand, basically. So, all right, we literally take the course 2, and now longest taken is 5, so we eject course 1. Yeah, so we move the course 2 there. How is it possible, guys? And we we bring course 3 out of the sky. Like, the point what I don't understand is how can course 2 move to the left? Because, like, courses have dedicated start and end point, right? Ejecting longest freed the most room. Yeah, I guess this is it. This is interesting, guys. Like, we need to understand the overflow logic first. the yellow thing, the overflow logic, the deadlines, and then uh like on overflow we eject the longest one, and then we need to understand how we move the course to another place basically. Like let's see. um so they are cooking, so let me, yeah, they are working, guys. Like on port 9878, I have, like, it doesn't work. I guess it is this one. Oh, we didn't start it, so let's see. Which animation concept should I build um for the Fortus building? Regret heap greedy. For the Fortus building. Like which question was it? This one. All right, all right. The Einstein problem. Entschuldigung, Einstein. Das ist schön, Einstein. Um, yeah. So, like, this is the first question that I've seen heap used to solve a greedy problem. That's all right. That's all right. But the grid idea is what is important. So, which animation concept should I build for um for the Fortus? Let's see. Which animation concept should I build for the Fortus building? Skyline walk, heap insert, leather versus brick duel. I think that's Rick and Morty. I don't know how that relates to this. Hmm. Ah, yes. Sorry. I thought that is a woman, but this is uh Morty, right? Like here we see like here. Oh my gosh. Yeah. It can be. And yes, how is this related? um, Not Skyline Walk, but leather versus brick duel. Like this is, or regret heap. Mm. Or guys, all of them. All right. Let me take a screenshot. Right. Let me take a screenshot. Um, let me paste it over here. Right. We can have all of them. We can have we can have all of the animations basically. All right, guys. Um, let's see the animation we have. Um, So input courses duration line. C1 is 5 to 5. So starts from 5. But it doesn't start from 5. It starts from 0 basically. So I guess animation has something wrong. So it was when a course overflows at that line, eject long. So yeah, so let me also color these guys red. All right, let's paste it. And thank you for the animation, but the thing is, like, C1 course does not seem right because, like, it literally starts from 0, like 0 index, right, and goes until the 5. But the thing is, like, it should start from 5 and then go more 5, like go by 5 more, right? Like, how do we represent course 1 over here? And also I don't understand the deadlines. So deadline for C1 is 5 and deadline for C2 is 6. Yeah, and also it is for also C course 2. um I thought in this question we have, oh, in this question we don't have a start date for our courses. What we have here is like a real duration and a deadline, right? Oh my gosh. Oh my oh my gosh, guys. Like we don't have the start. But why did I think about start dates? I mean, why? Like duration and last day. Interesting. So the I even told Cloud that it generated wrongly, right? It generated yes this one, and I told him or her that you created wrong. Let's see, let's see. Mm, so this duration. This is deadline, right? This is also deadline. Yes, this is deadline, and this duration is yes. So this is uh yes. So this is course three. We have deadline of this one, and this is all right, guys. Um, like we have deadline, but we can, and also when we start a course, it will continues. But then it means that like we can start this course like maybe day 02, right? But if we start at day 0, then we wouldn't able to get C1. So we can select courses basically anytime. I mean, start courses basically anytime. I mean, before the deadline and before the duration. I mean, before the deadline plus the deadline minus duration day, right? But we can start anywhere. All right, all right, all right. Like even like Cloud created this graph correctly, but now I get it. Now I get it, guys. Yeah, yeah. So I got the question wrong. So guys, maybe we can take a break for. I mean, it's gonna be my lunch break, and when I come back, I may need to create a not link list, not link list guys, um, but LinkedIn post. All right. So it may take 20 minutes. I don't know. Like it takes too much time, basically. Um, yeah. So let's see. Let's see. So we're gonna continue. Like after the break, we're gonna continue with. I mean, I'm gonna continue with creating a post, and then we're gonna continue creating more animations. Right? Animations are great. Animations are amazing. Um, yeah, yeah, yeah. So while they are generating, we can save the file. We don't need to create. We don't need to render them right now. Synced animation is enough. But after the break, I mean after the post, we can continue. Like a jump game, gas station. Yeah, yeah, we know this one. We can review. We can review. And then merge intervals, insert interval, meeting rooms too. Like I wanna solve like this one, right? Construction by height. Yeah, we can do this. Assign cookies, task scheduler, hand of straight, bots to save people. Yeah, yeah, yeah. Like I guess we have one, two, three, four. I mean, 4, 5, 6, 7, 8, and 9, and 10, and 11, and 13. So the number of questions may vary. For 42, yes, we have 9 and 10. 3, 4, 5, 6, 7, 8, 9, 10. Yeah, yeah, yeah. Remove k digits, remove duplicate letters. Oh my gosh, guys. Yeah, so maybe we can continue from the orange one. Sort and pair, custom match, opportunity cost, and competitor. We can continue from here, the orange one. Let's see, guys. Let's see. So, guys, now I'm taking break for at least. I guess we can make use of 1 hour. Let me check the Instagram. Um, no, it is still same. Let's see. Um, let's check the Twitter. All right. Hmm. Follow back. All right. That's awesome. Now we can take a break, guys. For I guess 1 hour would work because if some food and then a bit resting and then some exercise. Let me pause the Pomodoro and make it 50 minutes and see you after the break, guys. We are big guys. Who needs a break? All right. If you study LeetCode, then it should be enough, even more than enough. All right. We're gonna we're gonna handle this, man. Let's continue. Let's resume our Pomodoro, right? Resume. And we were creating some animations. Let's see. I don't know what I have pasted over here. Let's see. When a course overflows a deadline, let's see what we have just written here, all right? Um, how to represent a course over one over here? All right, so I have a question on like the design, like how, like look at this. Like currently we have, like actually the thing is, guys, I learned that the courses don't have their start time basically, all right? We can set this up basically. What we have instead is, the duration and then end time. All right, this is what we have. Let me know. Let me start the tracking. All right. Um, this seems good, I think. Right. All right. Let's see what AI will tell us, and then we're gonna continue with these amazing guys, amazing greedy problems. All right. We're gonna cover them all. We're gonna be fluent, greedy fluent. What I'm looking for is being greedy fluent. All right. I'm kinda AI fluent. All right. Now we're gonna be a greedy fluent. Let's see. Let's see. Let's see. Yes. That. Oh my god. Is the click? Like, look at this AI, guys. Like, this is cool, guys. Like, this is uppercase letters, and look at oh my god. Because in here I have that expression. All right. The oh my god is the click, and you just got the most important thing about this problem. Let me confirm. There are no start dates. The entire input per course is duration and deadline. So this information we know, like we only know this information, right? So how does C1? How does C1? Yeah. How does C1 get its position on the timeline? Yes, like that's the big question. How does it do that exactly, guys? How does it do that? I guess as hippopotamus, as hippo, hungry hippo, once told us, we sort the courses by their deadline. All right, deadline. And when we sort in such a way, we automatically get some order, I think. But of course, that ordering has some flaws. All right. Let's suppose you order one. Let's say one course. Oh my gosh. Let's say one course ending here, and then you have another one next to it, but they overlap. So if they overlap, now we need like we can just have them basically, right? Um, let's let's force QE. We will quit. So let's open that again, guys. Um, Wonderful, wonderful, wonderful. So let's suppose we have, let's say this is the endpoint, right? Not end game, not endpoint, but deadline. So we have this over here, and imagine we have another one, you know, but its duration is kind of long, all right? And which like this would give us you know the overlap situation. So you basically either can pick that one and that one, but in the animation I suppose we don't have these either, right? So each course finishes by its own deadline, no global deadline, run back to back from day zero. So this is not a greedy approach. We'll see. Is it done? Yes. So let me let me let me run the animation, guys. So this is the name approach, but what does it do actually? It placed, yeah, earliest deadline first. That could be one way. Um, but we have another deadline, and deadline is for course both course 2 and 3. This is deadline for all of them. But after placing the first course like this, the next available place for us is starting from here, right? Meaning we can't just position based on the earliest deadline, because deadline does not have the information we need completely, right? Because there is some another case that breaks that approach, uh, which is which is that which is a duration, I think, because we have, like, if we don't have any duration, we could just place them all. I mean, run. I mean, federally, right? But we have their duration, so um, if you, I mean, if you place the course, if you pick the course with the earliest deadline, then you know get this place basically from occupy. You basically occupy this place, right? And by occupying, like by selecting this course here, while you are occupying this, and also you make the remaining courses, like the next start point is starting from this end, even +1, right? um yeah, so this is not a good way, I think. So I didn't get the yellow part, but we will get into that. um yeah, C2 finishes on day 9, and it's deadline day 6 actually. Yeah, so its duration is 4, and when we place 4 here, actually the another part that I might have gotten wrongly, like that might be the starting point, because I think like on this deadline file we can literally start, I mean, we can start another the next course. But in the first in the first when I try solving this question first, and for the first time, I thought that we cannot do that. So this means that I got a few parts very wrongly, right? First part is about the deadline. I thought this is a start and this is the end point or deadline. Somehow I don't know, but we don't have anything about the start point. So this is the whole point. Actually, we're gonna um let me update the topic. We're gonna actually we don't even decide on start point. We basically decide on the end point, and the remaining part is just is just getting occupied. That's all. We don't do any selection with start, I think, right? Yes, we don't know. We don't. Like, I thought maybe we are doing some stuff here about in terms of the beginning, like a starting point of this course too, but I guess we don't. So update topic. The topic is greedy problems. Studying. The topic didn't get updated, but alright. That's interesting. Um so yeah, so these are the two things that I got wrong. This is naive. So yeah. Now the fix on overflow eject the longest course taken. So like we've seen this before, guys. We've seen this like occupying for like a temporarily occupying a place, right? I guess we had a term called, what is it called, guys? It was it was starting with T again, not temporary, but tentative. We basically tentatively, you know, select course one, and so I guess, guys, this yellow line, the yellow slice, meaning is like means that our our next courses end point, I mean start point, will get until this, um all right, because if the start I mean if any part of the next course, you know, is behind this point, this basically will mean that they are overlapping. So this is not something we want. That's why we need a variable to hold this information, right? And like we place the C1 again, and we place C2 right here. All right. Um, 5 plus 4, I think, and it is 9. Yes. And we try to update the yellow thing, but deadline is, you know, deadline is passed. So instead of placing course 1 here, by the way, why did we pick course 1 in the like, after all, you know, why not C1 but like I mean C2 but C1? mm, I guess like it has like its endpoint is, you know, ahead of the remaining parts. So, but how are we supposed to handle this now? Like, if you place it like that one, two courses. So basically, guys, we don't even place the course one at all. Yeah, like we just don't. Because if we did, I mean, if we did, um, only we can only get one course. We can get only one course, right? But you know, ejecting it, um but what do we like, what do we mean by ejecting? I mean, like discarding it completely. I mean, we don't, um like we are not able to place it anywhere. Like, do we know, like, are we sure that we cannot place anywhere? Let me check the stream. Yeah, yeah. So um now maybe we can discuss about the meaning of eject over here. There are some points I don't understand. Uh, so longest taken is 5. So we need to have a structure for holding the longest taken. I guess yes, guys, because we have a max heap. So max heap. But why do we start with C1 at all? What is the reason behind it? That's interesting, guys. That's interesting. And we play C2. Like, this shows the next position that the next course will, you know, can close, like how much that it can close. and and actually we make course 3 start from day 4, right? And we check if it exceeds the deadline, right? like we can use two different approach here. One, maybe like a adding the duration to like these yellow slides, which means the next available start position. um and maybe we are doing the same thing here. Like yellow slides mean the available start point, or let's say start point, right? and um and we literally put C1, like curse 1 here, and the next available start point is here, and we pick C2. And when we do that, if you do that, like the deadline is crossed. All right. Now the thing I don't understand is why, like, how do we exactly select C1 here? What is the logic behind it, right? Like the animation is good, but so thank you for creating this beautiful, amazing animation for us. Now I need you to save it, all right, and save it somewhere safe, all right. Maybe even you can save it here in the related problem, all right, in our LeetCode folder. I need you to save it, and then I need you to explain in action 2 um, why. I mean, how do we select course 1 and place it over here? Or maybe it is random, like maybe the order does not matter, like because we literally maybe randomly pick a course and update the next available start position and then the try next one, and when things go south we extract or evict the longest one. So that's some logic too. Like we literally extract the longest one. So like I think I remember that thing from water, the container with most water, and there we don't move left pointer or right pointer inward. What we move there is like moving the smaller of these two. All right. And here like we have the same logic here. Like forget about data structure. Like using heap here is not important. The important part is like a knowing which one to evict, basically. But now my question is that how do we select these courses? Is it random? Um, and what does evict mean? Does it mean like now the course 1 will not be inside our answer? Like I'm thinking like DP, dynamic programming, or like maybe exploring our options. Like this greedy is quite like greedy overall resembles to backtracking and dynamic programming very much. So I need some clearance. Let's see, guys. Let's see. Um, and also maybe we can look at the other animations we have. Like maybe, guys, I can show you. mm, I can show you the other animation as well. So let me zoom in a bit. Let's see what we have here. Oh, that looks fun. That looks fun, guys. But how about the camera angle? Let's see. Let's see. We're gonna handle. We're gonna understand this, man. Let's see. We can also, guys, like anyway. Hmm. Um, maybe about this one, right? We don't need to be full screen. because now we have lots of things and I need to navigate to write a lot. So yeah, so let's see. Let's see. Is the order random? Does order matter? No, this is the whole game. We process courses in earliest deadline. Sorry guys, sorry. Earliest deadline. So like the reason why we have course one in the beginning is not because it is course one. It is because earliest deadline. Like it has the earliest deadline. That is why. So it's just coincidence. So uh, yeah, we have it. Uh, our question was course schedule. Maybe we can save it over here, guys. Earliest deadline possible, right? Um, that is not optional. Let me prove it. And also we need to understand why we, sorted by that field. I mean, that information. Earliest deadline first order. And now it's gonna explain this. So course A, let's say duration and deadline, duration at deadline. So basically, guys, if you have if you have these two information like a duration and then um like a deadline, you may think about like sorting based on this one or this one, but of course this is not that's just memorization. We need to do this logically. Optimal, take both. So optimally we need to we should take both, but um A on days 0 to 2, B on 2 to 4. Answer should be 2. Deadline order. A then B. Take A, clock at 2, clock at 2, and takes B, clock at 4, random wrong order. B and D, take B. But if we take B, it will overcome. I mean, pass over the endpoint deadline of A. So we shouldn't first get B, right? Um, A's deadline is to overflow, evict the longest. So same eviction rule, same courses. Wrong order loses a course. So the order is the load-bearing decision. Sorting by deadline is a what makes evict the longest safe. I didn't understand, but it says something important. I mean, we need to understand this very carefully. Why? When you are deciding about a course with deadline D, sorting guarantees every course that also had to finish by D. Uh, by D has already been considered. So total time spent so far is valid budget. What does evict mean? Does C leave the answer? Yes, evict removes C1 from the set of courses we are taking. Oh my god, this is something serious, guys. This is something serious. So, like, actually, we have kind of same approach in container with most water, right? As we move our pointers inward, we basically shrink our area, um, answer field. I mean, answer subset, right? mm, answer set. So like this decision is quite important. But here the subtly we are sensing the count doesn't drop. When C2 overflows, we swap. C1 leaves, C2 stays. We had one course, we still have one course, but now it's 4 day course instead of 5 day course. So we have used 4 days instead of five. We bought ourselves a day of a room of free for free. This free day is exactly what let's see three fit later. So eviction isn't give up a course, it's trade. The greediest course, time greediest course for a cheaper one, keeping the same count but spending less time. Your own words. Forget the data structure. The heap isn't important. Yes, yes. The important part is knowing which one. Yes, yes. So, like, this is my words. So, this is a safe choice. State it correctly. Frame it yourself and say it loud. The safe choice is when I overflow, evict the longest course I have already taken. It's the safe because I was going to lose a course anyway. And dropping the longest frees the most time for everything after. No optimal schedule does better. Like we have seen this safe movement, but safe choice, but like we're gonna understand this, guys. We're gonna understand. So the heap is just the tool that hands you. Yeah, yeah, the longest I have taken. Yeah. The container with most motor connection. Beautiful instinct, beautiful. And it's the same family of move. In container, you discard the shorter wall because it can never be bottlenecked. Be the bottleneck. Keeping it can't help you. Here, you discard it. You discard the longest course because it is the worst use of time. Keeping it can't help you. This single question is the spine of grading. Which element can I throw away with zero regret right now? With zero regret, guys. So the single question is the spine of grading. So you have now seen it in two different costumes. One difference worth noting. In container, you discard to make progress. Here you discard only when forced by an overflow. But the identity, the probably useless element, move is identical. So greedy resembles backtracking and dynamic very much. I need clearance. Yes. This is the most important confusion to kill because the eviction looks like backtracking, but it isn't. Here's the line. Explore alternatives. Yes, in backtracking. Try option, undo, try another. So in greedy, we don't explore alternatives. Oh my gosh. One choice per step. Can a discarded item come back? Yes. Backtracking undoes. That's the word. In greedy, yes, guys. Like I like this. I like this. Because as we do in gas station, in container with most water, when we eliminate something, there is no way for it to come back again. So we will eliminate. We literally eliminate that option, right? We are serious. Greedy is serious, guy. Greedy is serious than I thought. Greedy is serious. I mean, more serious than I thought. Let's see. Let's see. Do we keep multiple candidate solutions? Yes, in backtracking. In greedy, no, one running solution. The eviction is not let me undo and explore a different branch. Like this is exactly how I was seeing it. So like I was wrong about it, guys. I was wrong. So let's see. It's a one-way final swap that prove uh, i- that we prove is correct before making it. We never ask what if, like this is how Americano and I thought today, right? So we ask what if that way? What if we had we thought about we thought about you know in some case like what if we had this one before that one? What if we had what if we had that kind of input? But in greedy, we basically don't worry about we don't need to worry about this type of stuff, right? Our approach already covers different cases casually. All right. What if I kept C1 instead? So we already know the answer is that's never better. Like look at it, guys. That's never better. That's never better. I think I'm gonna use this phrase a few times in my streams. That's never better. Like this is the if someone asks me what is greedy, I will say, I mean, stop, man. um, like how do you close that one, guys? That's never better. That's never better, guys. Save it. So since we made sure that that's never better, we can easily say that like now we can extract that solution from our set basically, right? And put it into trash. All right? We don't care about it at all. That certainty is what lets greedy not explore. Like guys, we are not exploring, guys. Like I've been thinking we're exploring for some time for ingredient, but we are not doing exploring. We are literally eliminating options, our choices, right? Backtracking explores because it cannot prove the choice. Greedy refuses to explore because it can. Oh my gosh. Why do you do that? Because I can. Greedy refuses to explore because it can. Oh my gosh, guys. Like, look at it, guys. Like, I really like the term we are using for them. I mean, the phrases, like how AI describe it. So, greedy refuses to explore because it can, guys. Because it can. Let's see. Your earlier own words were spot on. In grid we have options too, but there is only one optimal choice. So we don't explore every option. Yes, so this was like I shouldn't be too hard on myself, guys. Right? Because I literally mm, said this, right? The eviction doesn't violate that. It's the single optimal choice at that step. So we basically have a single option, right? We maybe guys, maybe we can I can just maybe copy and paste it over here. Let's see. So the comprehension check. Answer these two and you own it. Which shape proof shape is this? The answers can have different sizes. We are maximizing a count in Turkish and English. One sentence. Why is processing in deadline order the thing that makes a week the longest save? Oh, yes, that's a good question. But before that, before answering those questions, did you save our Blender file, my man? Let's see, guys. Let's see. My man, my man. In Blender 2, that animation seems amazing, but we may have some issue with the camera angle, right? Could you please make sure that we are using some beautiful, amazing camera and camera movements, please? And also make sure that you save our file, right? Make sure you save our file in our corresponding LeetCode folder so that we don't lose it, right? So today, guys, we're gonna learn greedy. Easy, easy. We're gonna learn it, guys. There is no way around, right? Yes, saved and verified. I confirm. Yes, 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 which is amazing. Your two comprehension questions are still open whenever you want to close them out. Which proof shape, exchange argument. Yes, 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 exchange argument. So this is what I was looking for. Exchange argument. Let's save it over here. Let's even give it a color of red, man. Show that we are serious. Exchange argument or greedy stays ahead. Greedy stays ahead. So here in greedy we make, like, we don't make choice, right? Or we make the obvious choice. Like, it's not about we make a choice or not. It's about we make optimal choice, right? One optimal choice. Hint: solutions can have different sizes. We are maximizing it. Like I don't understand, guys. Um, it's question number two. One sentence. Why does processing in deadline order make a week the longest? Safe. Why does processing in deadline order? I like these questions, like, are looking amazing. I love them, but I didn't understand them at all. And I guess you are like in one of the questions you are basically asking me that why do we sort by deadline? Yes, like I'm asking the same question again. Could you please again clarify that, guy? Clarify, my man. Like, it is quite important. Like, we can sort by duration, we can sort by maybe start point, but we don't know the start point. So most probably it is, duration or endpoint. But in some of the grid problems, we do some sorting operation, maybe like using a formulation or something, right? Instead of using a single parameter or argument, we may use maybe we can create a formulation, and based on the result, we sort our input based on that formulation, right? So that's why I'm asking. So because in some of the grid problems, we may sort them based on a rule, right? So you may say, like, what are you expect? Yeah, what do you expect to, which let's say, which, like, argument or value, I mean, you plan to sort by, right? Use it for sorting. So obviously it can be, duration or endpoint, I mean, the deadline. Like, but I need to know the reason behind it, all right? Because it can be anything. I've seen it, guys. Like, it can be anything, basically, all right? And also during the interview, I need to be able to explain my reasoning. Like, it wouldn't be nice if I say, like, these are two arguments and we should sort by one of them. So, like, this is not a good explanation, right? Like, I wouldn't like that person if I see. So let's see what we have here, guys. Totally fair. Let me drop the jargon. Just answer the real question, mother father. Why deadline and not duration? First, reframe which key do I sort by even means. It's really this question. If I line courses up in this order and go left to right, will I ever regret a choice I can't take back? So that's a good question. That's a good question. But, like, you wouldn't ask This type of questions in your daily life, right, guys? Like, I don't imagine someone who is asking this question to himself or herself, right? If I line the cursors up in this order and go left to right, will I ever regret a choice I can't take it back? You find the right key by proposing a key and trying to break it with a tiny example. Let me break duration for you. Then show why deadline can't be broken. Like, maybe we need another animation for seeing the meaning of sorting by this key, basically, right? Like, what is happening if we like what is happening when we sort our courses by this? What do we get from this, right? Try sorting by duration. Shortest first, watch it fail. Oh, like that's a good way. Trying and seeing it failing, that's a good way. So, right answer is to take both. I need visuals. Now sort by duration. B is shorter. Sorting by duration lost a course. The short course B hogged the early timeline, and the urgent course A, the one with no room. All right. Now the intention for why deadline always works. Picture a shelf. Some boxes have a sticker. Must be placed within the first n centimeters. Within the first n centimeters. Duration. How wide the box is, how much it needs. So deadline, the sticker, where it is allowed to be, the constraint. If you place wide but unrestricted boxes first, you block the boxes that have nowhere else to, like, you block the boxes that have nowhere else to go. So you place the most restricted boxes first. Smallest sticker first. Mm, I mean, I mean, earliest deadline first. I guess this is the formulation, right? The urgent ones claim their space before the relaxed ones can steal it. Claim their space. So deadline is the thing that limits where a course can live. Duration just says how much space it eats. You sort by the constraint, not the appetite. 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 So, appetite. Now here's the part that resolves your is it duration or deadline? It is both doing two different jobs. Deadline decides the order we process courses, and duration decides who to evict when we overflow. So you were right to feel both matter. They do, just in different moments. Deadline orders the line, duration picks. Yes, yes, yes. Your formula question: when do you sort by